Sorry for the interruption. Actually, if you want to go for the trip or spouse program, you can register at your own convenience at this time. Some people's name I have already who have made. Program will be to Pannagiri, Udaigiri, and then Dhulagiri. Tomorrow plan is fixed depending on the interest.
Good morning to all, and welcome to this 90th meeting of the Indian Academy of Sciences. Before we start the proceedings, I'd like to invite people, the dignitaries, to the dais. So, the president of the Academy, Umesh Wagmare, the previous president, Professor Partha Mazumdar, Professor Ram Ramaswamy, the past president. Yes. Professor Sripad Karmalkar, Director IIT. Professor Hiren Ghosh. And Professor Raghunathan, the Treasurer of the Indian Academy of Sciences. And Professor Gunanathan, who is the convener of the local organizing committee from NISA. Thank you all, and please do take your seats. So, as I said, I'm Renee Borges, one of the secretaries of the Indian Academy of Sciences, and I'm really delighted to welcome you today to the if I may just ask people to be a bit silent because this room voices carry. Thank you. So I'm very, very happy that today we host NICER and also IIT, which is a co-host of this event. We're really delighted to come together, bringing together lots of institutions and participation from many institutions. As you know, the Indian Academy of Sciences is committed to serious scientific research as well as science outreach. So we publish many journals, as all of you are aware, and we are also deeply engaged in science education and outreach. Usually at our academy meetings, we also have satellite events that reinforce our commitment to science education and outreach. I think with these few brief words, we've got a very exciting program for you over the next 2.5 days. I'm sure that you've had an opportunity to look at the program, and you will realize that our program has been constructed to really reflect all the disciplines of science, and I hope you enjoy the next 2.5 days. So with these few words of welcome, and I would like to invite Professor Hiren Ghosh to make a few remarks.
Good morning. Welcome everybody here on the dais, of the dais, dignitaries and respected senior fellows, current fellows, and the students. We are very fortunate that we are organizing this academy meeting here, 90th annual meeting. Particularly in NISER perspective, it is very, very important. This is a relatively very new institutes, and this kind of academic program always give an academic boost to the institutes. You might be knowing that NISER is having a BSMS in integrated PhD, postdoc, and all kind of programs. We have 4 different major school: physics, chemistry, mathematics, biology. And in addition to that, we have computer science, social science, art and planetary science. And recently, we have conducted a DE conclave, and observing our growth, actually, DE again wanted to expand it, increase our horizon. The new type of engineering school also will be coming, maybe engineering physics, biomedical engineering, and also other engineering department might come. So we are extremely happy to organize this meeting. I'm sure the coming 2.5 days will have a great time. 2 days will be organizing here, and half days will be organizing IIT Bhubaneswar. And I'm sure you'll be enjoying. I hope you'll have a very strong interaction with our faculty, students, and other members. So I'm not extending much. Here I'm going to close it and welcome again. If you have any problem, anybody, please directly you can contact me or Professor Gunanathan. I hope you will have a great time. Thank you very much.
I'll now like to invite Professor Sripat Karmalkar, Director of IIT Bhubaneswar, Bhubaneswar, they are a co-host of this event.
Along with Professor Hiren Ghosh, it is also my privilege to welcome you all to this event, which is being co-hosted by NICER and IIT Bhubaneswar. I was a faculty at IIT Madras for 30 years before I came here as a director 2 years ago. At that time, before that, I knew about NICER, IOP, and so on, but I did not know that these institutions are so close by, particularly IIT and NICER. So after I came here, I found an opportunity to visit NICER, and then I always felt that the two institutions should be collaborating much more than they have done in the past. And so from that point of view, I'm really pleased that we got a very good opportunity to organize this event together. I had come across various Indian journals of repute, and I'd never imagined that I will have an opportunity to host a meeting of the academy which publishes those journals. So I think as a director, I feel fortunate. Otherwise, I don't think I would have got associated with an event like this, because I'm basically an engineer and my background is in the area of semiconductor devices. Let me give you a quick idea of IIT Bhubaneswar. It has a very large campus, 940 acres, third largest in the IIT system. And we have about 3,000 students and 220 faculty. And we also have about 50,000 trees planted, various fruits, flowers, and so on. So please do find some time to, explore the campus when you come to IIT Bhubaneswar. And like any other IIT, we are in different areas: education, research, and then consultancy, and so on. Two unique features of IIT Bhubaneswar, apart from these, is that last year we have started a program, integrated teacher education program in BSc, that is BSc B.Ed program, where we are trying to train school teachers in physics, chemistry, mathematics, and our particular IIT also has included economics. So BSc B.Ed in physics, chemistry, mathematics, and economics. That's something unique. So far, no IIT had started such a program. Apart from that, we also have started an activity in research and entrepreneurship. That is an area entrepreneurship is an area which is being talked about a lot. And in a couple of years, we plan to build a 130 crore research and entrepreneurship park. So that is another unique feature of IIT Bhubaneswar. In the area of science and technology, we are in all areas. Specifically, I would like to mention green hydrogen, and then semiconductors, and artificial intelligence. We are trying to build kind of, you can say, a globally competitive work in these areas. So that is a brief introduction about IIT Bhubaneswar. I have gone through the program and it is really exciting. I wish I was not a director so that I could have attended many of these sessions, and that I will be missing. and I feel sorry for that. Thank you, and I welcome you all once more.
I now invite the President, Professor Umesh Wagmare, to introduce the Fellows, Associates, and the special invitees.
Thank you, Renee. One of the important goals of the annual meeting is to promote exchange of ideas and interactions among the fellows and also local scientist community and public at large. So a part of the inaugural session is usually to introduce those who are present here as invited participants. So I will call upon name of the ones who have to be introduced, and I request you to stand up in your seat so that the audience and others can see you. And we won't have enough time to introduce in detail, so I'll just call upon the name, and you are encouraged to have deeper interactions later during the sessions. Myself, Umesh Wagmare, I'm the current president of Indian Academy of Sciences. Among the former presidents, we have with us Professor Ajay Sood, who is not in the auditorium at the moment, but he's on the way from the airport, and maybe he will join us in the next 15 minutes. Professor Ram Ramaswamy from the Indian Institute of Technology, Delhi. I will now introduce the council member, and first of all, the previous president, Professor Partha Majumdar from the Indian Statistical Institute, Kolkata. Professor Rene Borges, who is the secretary to the Council of Indian Academy of Sciences. Professor K. Vijay Mohanan Pillai, he is a secretary to the Council of Indian Academy of Sciences, and he's not with us at the moment. He's gone to receive Professor Ajay Sood, so maybe they both will join us in the next few minutes or 15 minutes. We have Professor V.A. Raghunathan, the treasurer of the Indian Academy of Sciences. He works at Raman Research Institute at Bangalore. Professor Swagata Dasgupta, member of the council and working at the Indian Institute of Technology, Kharagpur. We have here, luckily, representation from DST this year. This is the 90th year of the Indian Academy of Sciences. And we have invited Dr. Manoranjan Mohanty to join us here. He is an expert in seismology and has contributed to lots of important activities of not only DST, but ANRF now, and also the Office of Principal Scientific Advisor to the Government of India. He is presently the advisor and head of AI division of the Department of Science and Technology, Delhi. I will now introduce the local representation at this meeting. I'll start with the local fellows, hosts and associates. Professor S.K. Acharya from KIIT University, Bhubaneswar. Professor A.C. Dash from Bhubaneswar. Okay. Professor G.C. Kundu from KIIT University, Bhubaneswar. Professor J. Maharana from the Institute of Physics, Bhubaneswar. It looks like many of them are probably on the way but are yet to reach here. Professor Bedangadas Mohanty from NICER, Bhubaneswar. Professor U.C. Mohanty from the Center for Climate Smart Agriculture, Bhubaneswar. Professor Tapan K. Nayak from NICER, Bhubaneswar. Professor Sudhakar Panda from NICER, Bhubaneswar. And Professor Sujit Roy from IIT Bhubaneswar. No, none of the local ones are here, unfortunately. But I do hope that they will join us in the due course of this meeting today. I'll now introduce the local associates, Dr. Bishnu Prasad Biswal from NICER, Bhubaneswar. Dr. Priyadarshi Chaudhary from NICER Bhubaneswar, Dr. Nirupam Karmakar from IIT Bhubaneswar, Dr. Satyaprasad P. Senanayak from NICER Bhubaneswar, Professor Dr. Umakanta Subuddhi from IMMT Bhubaneswar. No? Okay, well, but I'm glad that they all are expected to be with us, and we are trying hard to enhance the participation by young generation and particularly the associates of the academy. I'm now pleased to introduce the local host, and particularly Professor Hirandranath Ghosh, who's the director of NICER Bhubaneswar, and he's also the fellow of our academy. Professor Shripad Karmalkar, who already spoke to you, the director of IIT Bhubaneswar. And they are accompanied by a large team of organizing committee members, and particularly the convener, Professor Chidambaram Gunanathan, with us on the stage. And I also take this opportunity to thank all the local hosts and organizers and volunteers. I'll now start with introduction of the outstation fellows who are present here. Professor G.V. Anand from Bangalore. Professor Hemalata Balaram from JNCSR. Professor Gufran Baig from the National Institute of Advanced Study, Bangalore. Professor K. Bhanu Shankara Rao from IIT Hyderabad. Professor Sujit K. Bose from Kolkata. Professor Subhash Chaturvedi from the Indian Institute of Science Education Research, Bhopal. Professor Dipankar Chowdhury from IIT Mumbai. Professor Debashish Chowdhury from Dehradun Institute of Technology, Dehradun. Professor Sushanta Dattagupta from Kolkata. Professor B.S. Dayasagar from the Indian Statistical Institute, Bangalore. Professor Ashok K. Ganguly, the Director of Indian Institute of Science Education Research, Berhampur. Professor Vinod K. Gaur from Bangalore. Professor Ashwini Ghosh from Kolkata. Professor Subir K. Ghosh from Kolkata. Professor Subrata Ghosh from Kolkata. Professor Anil K. Gupta from the Indian Institute of Technology, Kharagpur. Professor Ramakant from the University of Delhi. Professor Tarun Kant from Hyderabad. Professor Anirban Kundu from the University of Calcutta. Professor Kailash C. Malhotra from Noida. Professor Meena Mahajan from the Institute of Mathematical Sciences, Chennai. Professor Ashish K. Mukherjee from the Institute of Advanced Study in Science and Technology, Guwahati. Professor Parthasarthi Mukhopadhyay from the Indian Institute of Science Education Research, Berhampur. Professor SVS Murthy from Ahmedabad. Professor Premchand Pandey from IIT Gandhinagar. Professor Tanmaya Pathak, IIT Kharagpur. Professor Rajiv Patnaik from Punjab University, Chandigarh. Professor Amit K. Patra from NARL, Gadanki. Professor K.N. Raghavan from Kriya University, Sri City, Andhra Pradesh. Professor P. Ramaraj from Madurai. Professor R. Raghavendra Rao from Bangalore. Professor T. Narayana Rao from NARL Gadanki. Professor Rajesh Ravindran from the Institute of Mathematical Sciences, Chennai. Professor M. Sabu from Calicut. Professor M. Sanjappa from Bengaluru. Professor K. Shankara Rao from the Indian Institute of Science, Bangalore. Professor Jaydev Sarkar from the Indian Statistical Institute, Bangalore. Professor Kulinder Pal Singh from the Indian Institute of Science Education Research, Mohali. Professor Ashok Kumar Singhvi from Ahmedabad. Professor S. Shivaram from ISER, Pune. Professor Binod Srinivasan from IASc, Bengaluru. Professor Rajesh K. Srivastava from Banaras Hindu University, Varanasi. And Professor Saraswati Vishweshwara from the IASc, Bengaluru. I will now introduce outstation associates. Dr. Sharan Adhar from IIT Jodhpur. Dr. Haider Ali from TIFR Center for Applied Mathematics, Bangalore. Dr. Govindarajan Anand from IISc, Bangalore. Dr. Shubham Banerjee from Naipur, Guwahati. Dr. Debashri Chakravarti from NIT Suratkal. Dr. Prabhabhan Chakravarti from SRM Institute of Science and Technology, Katanalakpur. Dr. Udita U. Ghosh from the Banaras Hindu University, Varanasi. Dr. Sukanya Ghosh from the Central University of Kashmir, JNK. Dr. Debabrata Karmakar from the TIFR Center for Applied Mathematics, Bengaluru. Dr. Pankaj Khanna from IIT Gandhinagar. Dr. Pankaj Kushwaha from ISER Mohali. Dr. Rusa Mandal from IIT Gandhinagar. Dr. Archak Mittal from IIT Mumbai. Dr. Divya Nair from IIT Delhi. Dr. Monalisa Pal from the Banaras Hindu University, Varanasi. Dr. Swalpa K. Roy from Alipudur Government College of Engineering and Management. Dr. Amiya K. Samal from Banaras Hindu University, Varanasi. Dr. Suchana Taral from Pondicherry University, Puducherry. Dr. Aishwarya Venkatesh from the CCMB, Hyderabad. I'm really glad to see large participation from the associates, and one of the objectives is also for you to interact with the senior fellows and accomplished scientists and benefit from these interactions in your activities. So I encourage you to please come forward a bit, don't sit so behind in the hall, and have good interactions. I'll now introduce speakers and who are fellows and associates in this. I'm sorry about that. Thanks for rising and introducing. Yeah, actually, I was going to ask at the end if I have missed someone, please do get up. And yeah. So I'll now introduce the speakers in this annual meeting who are fellows and associates. Professor U.K. Anandavardhanan from IIT Mumbai. Dr. N.M. Anupakrishnan from IIT New Delhi. Professor Sanjeev Galande from Shivnadar University, Delhi. Professor P.G. Kubedran Amos from NIT Tiruchirappalli. Dr. Sugam Kumar from BARC, Bombay. Dr. Ramajayan Pandian from IIM Jammu. Professor S. Umapati from IISc Bangalore. Dr. Sriram Varahan from CCMB, Hyderabad. We also include some non-fellow speakers in the meeting, particularly in the symposia, and I'm delighted to introduce those now. Professor Abhilasha Joshi from NCBS, Bangalore. Professor C. Murali Krishna from TMC, Navi Mumbai. Professor Nikki Kuhar from the University of Delhi. Professor Supratim Rai from the IASc, Bangalore. Yeah, now I again apologize if I have missed some of you. And if you belong to any of the categories that I called upon, please do rise and introduce yourself. Professor Chandravas Narayana. I'm sorry, Chandravas, that was a rather bad miss. He's the convener of the first symposium today, and he's the director of Rajiv Gandhi Center for Biotechnology. And seems to, I apologize, but everyone knows you, I suppose. And yeah, okay, so that brings to the end of introductions that have been planned today. There are many more fellows and associates we may have in this meeting who will arrive later. The list given to me was based on the arrival information given by each participant. So that may have caused some confusion, and I apologize again. Thank you.
Uh, Thank you, Umesh, very much for that introduction. And now we move on to the presidential address, which would be given by the President Umesh Wagmare. So I request the dignitaries on the dais to please take your seats over there so that Umesh can give his address.
Here will be good. Thank you. Thank you, Rene. And do alert me when it's crossing 40 minutes. Yeah, that's here. Oh, thank you. So I join my colleagues and also the local host in welcoming you to this annual meeting. And The tradition is that the president gives a technical talk as an inaugural address. But before I start my technical talk, I do wish to make a brief set of general remarks. The Academy in the last year, particularly noting this is its 90th year, brought together representatives from various academic sectors in India, including universities, state universities from different parts of India, vice chancellors, 2 junior faculty members, and of course other research institutes along with its fellows and associates, and had a brainstorming session. Is that some? It's gone, okay, thank you. For a brainstorming session on strengthening the R&D ecosystem in the country, and in particularly focusing on the universities and integrating all the stakeholders into a single sort of cooperating community to enhance the synergy in expertise of various stakeholders. And indeed, it was a very successful exercise, and we came up with a document on what government should do possibly through ANRF, and also what the academy can do possibly working with ANRF to achieve some of these objectives. In particular, we proposed, this is in a semi-proposal mode, we proposed that we could set up a cloud in science and technology in India, which will have accurate information, data on human resources, capabilities, infrastructural resources in various parts of country, about their regional information, as well as industry and other stakeholders, government funding bodies as well. And the idea is to possibly benefit in the future from this data, which I think is the wealth, to use possibly even artificial intelligence in identifying the patterns and opportunities for synergistic interactions, getting people connected together better from various backgrounds. And that's the cloud, which will sort of be a smart cloud. I'm not going to go into details. Set up regional hubs, which will also help in maintenance of the cloud and implementation of some of the activities region-wise. And thirdly, work with ANRF possibly to initiate a postdoctoral fellowship program, a faculty mentorship program, which will enhance the relationship between our fellows and the university faculty members, and a program to expand and improve pool of PhD students for universities. And this was based on the gaps that we found out from universities by carrying out a survey which reached out to more than 200 different individuals from different universities. Of course, this is something which is up for discussion, an open discussion, and I invite all of you and others to please come for the business meeting of the fellows, which is scheduled at 3:50 p.m. on Saturday, and contribute to this discussion and see how, and if at all, the academy should take these things forward, in what way. So I'm now going to get started with the technical presentation. This is about sensing vibrations using quantum geometry of electrons, and not all the terms in this title may be familiar to you, so I will take enough time to introduce these ideas. The work is done by my PhD student, Bhuvaneshwari, and in fact, I even acknowledge that the idea was seeded from her discussion with me, and it's really nice to have a student like that. Second author is Mandav Deshmukh. He is an experimentalist and also a fellow of our academy based in TIFR Mumbai, and the funding for the work came from J.C. Bose National Fellowship and the DST. I'm particularly pleased to present this work at this 90th year meeting. It's a proposal using first principles theory. My work is essentially based on first principles theoretical analysis of materials particularly. And in this theory, we assume no experimental information in our analysis. Yeah, so it's a very unbiased way of understanding materials and coming up with predictions which are verifiable in the lab. And in this case, we are proposing a new class of spectroscopies which are based on quantum geometry. And we will demonstrate in the context of vibrational spectroscopy particularly in 2D materials, although it's applicable to wider classes of materials and other types of excitations as well. And this is really very interesting time to present this work, because this year is the 100th year of first experiment which demonstrated Raman effect, and we have a symposium lined up for you just after this. My talk will sort of serve as an interesting preface, in the sense it's not a Raman spectroscopy. In fact, what we show is it's much more than a Raman type of effect, but based on physics, which is very different, and that physics is about quantum geometry. So I'm really pleased to be presenting this work also in celebration of the work of C.V. Raman, who's our founding president of the academy. This is a picture you all probably have seen in popular science articles, where a body emitting light, which is behind the very heavy gravitational object, emits a light which sort of bends and reaches the earth. And this effect is called gravitational lensing, or bending of the trajectory of light. Hi, good morning, Ajay. I take a little break of a minute to introduce Professor Ajay Sood, the Principal Scientific Advisor to the government, who have joined us. Thank you, Ajay, for being with us. And this talk particularly may be interesting to you as well, I think. Although a bit elementary. Yeah. Okay, so this you may have seen, that light bends its trajectory while passing by a very heavy gravitational body. And this is not because this heavy body attracts the photons, which are massless, but it's because the space-time in which the light traverses its path is curved. So curved space-time is the key to this effect. The question we ask is, can this be seen for an electronic trajectory? Yeah? And that's what will sort of motivate us to learn about what is quantum geometry. So first I'll give you a very simple introduction to quantum geometry of electrons, and particularly in a crystal. These ideas can be generalized to other systems as well. Okay, so all of you know electron as a particle, if it has a momentum p, which is mass times velocity. It also acts like a wave, and the wavelength of that wave gives a momentum p, which is Planck's constant divided by wavelength, and it can be translated into h bar times k. K is wave vector of electronic wave. Yeah, and that wave vector acts like a momentum. In the sense, you see the classical kinetic energy is given by p squared by 2m, and energy of a quantum electron in free space is given by h bar k squared by 2m. So remember, k is a momentum, quantum moment associated with momentum, and it's a quantum number of a state. This is electronic state, which is essentially a wave, cosine x kx plus sine kx. So k is the wave vector. It's a continuous quantum number of an electron in free space. So what happens if you place this electron in a crystal? Well, in a crystal, you have periodicity. You have a periodic potential. These are nuclei generating this electrostatic potential filled by electrons, and they satisfy this periodicity condition. You will expect that the wave functions of electrons should also be periodic, like this I have shown, which are centered on the atomic site. And what was shown by Bloch's theorem is, in fact, there are infinitely many energy eigenfunctions of electrons in a crystal called Bloch function, which has, of course, this periodic part, which is shown here by red, which is called un of x, and it's modulated by a plane wave, which is e raised to I kx, which I just introduced to you on the last slide. It's a sine and cosine wave. Okay, so in this case, k is also a quantum number, a continuous quantum number, which belongs to a reciprocal space unit cell, and it gives you what is called as crystal momentum, because wave function is slightly modified from the free electron case. Okay, so here also h bar k is crystal momentum, and it is a quantum number of electrons in a crystal. So energy of a nearly free electron in a crystal is what we will see now. This is the energy of free electron, parabolic energy, and if you place these electrons in a crystal, the energy as a function of wave vector k is shown here. Their gaps open up, at certain special k points. You will see why they are special, and at the zero center of the space. And this is called the Brillouin zone, in which basically you can look at the energy spectrum of electrons, and it periodically repeats in the reciprocal space. So this box is typically called as electronic structure in so-called non-interacting sense of electrons in a crystal. This box is the Brillouin zone, and electronic structure is typically like this. Okay. So far, I hope you are with me, and if not, you can just quickly stop me if necessary, if there is a question. So example of electronic structure, this is called as gamma phosphorine, which is very similar to graphene. And if you calculate its first principle electronic structure, you get basically a set of electronic bands, which are called conduction band, separated by a gap from the valence band, which are occupied states of electrons. Indeed, this is semiconductor, but life is very interesting in materials too. If you place two layers of this phosphorine, you get a metallic state. Okay, and that's because the electrons between one monolayer of phosphorine interacts with electrons in other layer of phosphorine, and these bands, you see the conduction band and valence band overlap. So electrons from occupied states can readily jump into unoccupied states and give you electric current, and that's how gapless electronic structure means it's a conducting electronic system. All right, very nice. So electronic structure, unfortunately, as I presented here, has no information about quantum geometry. Of course, after you develop a lot of intuition, you can at the best guess that there may be something interesting, but band structure or electronic structure like this has no information about quantum geometry, and that's basically just energy versus wave vector. So geometry comes in when you realize that periodicity of a crystal means that wave functions or states, quantum states of electrons are having periodicity in real space as well as reciprocal space. So if this is the Brillouin zone, and if you imagine electron moves along this wave vector along y direction, you know, when it comes here, the state here is periodically equivalent to this state. So it forms a closed loop. Yeah. So the Brillouin zone in which the crystal momentum lies is periodic in reciprocal space. So as a result, you can close these two sides and these two sides, and what you will get is a donut. Yeah. So when an electron goes from one end of the Brillouin zone to other end of the Brillouin zone, which is the domain of its quantum numbers, it actually closes a path in the space of quantum numbers k. Yeah. And this trajectory can be accessed by applying electric field. You can apply electric field and move an electron in this k space and pick up some interesting features. So electron going across the Brillouin zone is a closed path. And that brings me to the idea which indeed very fascinating. This was the idea introduced by Pancharatnam, who was one of the youngest fellows to be elected at the academy at the age of 25 in Bangalore. And he came up with this idea of geometric phase in the context of optics. So I'm going to give you one demo, so please look at me. Imagine that this pointer, if you all can see, imagine that it's a vector or a quantum state of an electron. And I'm going to keep this vector perpendicular to my arm and move my arm without bending straight up, bring it to the right and bring it back. What you will notice is it picks up a 90-degree rotation. Whereas the way I moved, I didn't change the angle of that vector with respect to my arm. This transport is called as parallel transport in geometry, differential geometry, and the phase that it picks up depends only on the solid angle subtended by this trajectory. Yeah. So whether I go up and down, as long as I calculate the solid angle, the rotation will depend on that. And that's why this phase is called geometric phase, and later in the electronic context was introduced by Zach and later by Berry. This aspect of quantum mechanics, by the way, this is going to be 100th year of quantum mechanics also. And interestingly, this aspect of quantum physics was missed until 1984. Yeah, and Pancharatnam had these ideas in optics in the classical sense, and then Michael Berry, he popularized and adopted these ideas in quantum mechanics, and they have amazing features now, which is what I will come to next. Okay, so this is geometric phase, going back to Pancharatnam. Okay, so if you look at a block electron, It has a geometric phase, and what its geometric phase gives is the average position. Don't worry about this mathematical formula. This is just to communicate to you that there are ways of calculating these phases using numerical or analytical methods, but the geometric phase along XYZ direction gives you average position of electron in XYZ unit. This is a non-trivial result. I will not be able to go into those basic technicalities of it, but I have slides ready if anyone is interested. Yeah. So very fascinating result. Geometric phase of a block electron along a given direction in space gives you the average position of the electron along that direction. Yeah. And this was, by the way, developed for a very important reason to calculate certain things like polarization. So what happens is, if you have an electron and apply electric field to the left, due to the negative charge, electron will move to the right. This is K space, by the way, these are the quantum numbers of electrons. And what can happen is, if the electronic structure has a conical feature as shown here, this is the energy of electron at that particular K vector, the electron can bend. That's the sort of first message I want to give you. And this is like the gravitational lensing that I talked about. And I'll now make this little more clear why this happens and why this is a geometric effect. Normally, you would expect electronic trajectory to bend when moving electron is subject to magnetic field, because Lorentz force will give transverse force on electron to make the trajectory bend. So if you consider two-dimensional block electron, you have the Berry phase you can calculate along x direction, you can calculate it along y direction. And what is interesting is Berry phase calculated along y direction depends on kx, and the Berry phase calculated along x direction depends on ky. Okay? And if you go back to the mathematical formula, the Berry potential or Berry connection is given by this, Berry phase is given by this, and Berry curvature, which is the very important object now. That's the first sort of quantum geometric concept I want you to take home about. Berry curvature is the curl in reciprocal space of this Berry connection. So what Berry curvature says is, if you have non-zero Berry curvature, yeah, and if electron moves from this point to the right side, right, because of the electric field acting on it, its y position can change. See, Berry phase is giving you average position along y direction. So as electron moves to the right, if Berry curvature is non-zero, it will start moving upwards as well. And that's the transverse direction, and that originates from the curvature of space of quantum numbers of block electrons. Okay, so applied electric field causes change in momentum along x direction, and shift in y direction arises from the fact that you have non-zero Berry curvature. And this is like a Hall effect. Hall effect, all of you may, or some of you may remember from high school physics. If you apply magnetic field to a conductor and current is flowing along x direction, you develop a voltage along y direction in the transverse direction, and that's Hall effect. Hall effect depends on the presence of magnetic field. Without magnetic, you won't have Hall effect. But here, Hall effect is happening even when the external magnetic field is zero. And that's basically the statement that non-zero Berry curvature acts like a emerging magnetic field in a crystal, which emerges from the geometry of quantum electrons. Okay, so this can be taken forward if you have a metal and you have occupied electronic states surrounded by this Fermi surface, and if you integrate the Berry curvature over this occupied electronic states in this K quantum numbers, you can get phi, and that Berry phase basically gives you this is called off-diagonal conductivity or Hall conductivity, and it's called anomalous because this Hall effect arises even in the absence of magnetic field. Okay, so that's the sort of basic idea, that Berry curvature gives rise to unusual or anomalous Hall effect even in the absence of magnetic field. So Ex causes current along y direction, and as shown here. Wonderful. So I think most of the background is set up. Here are some sort of pointers, at least for the physics audience in this auditorium. So this is called geometric band theory or electronic structure, and this is analogy with electromagnetism. So Pancharatnam phase or Berry phase is like the Aharonov-Bohm phase in quantum mechanics, very popular in first course. Berry connection is like the vector potential in electromagnetism. Berry curvature is like a magnetic field strength, like that's what causes the Lorentz force. And Chern number, which is the integration of the Berry curvature in the whole Brillouin zone, is like a Dirac monopole charge, which gives rise to magnetic fields. And all of you know that magnetic monopoles actually don't exist in nature, but this gives you geometric aspects of quantum electrons, allows you to explore physics like something which doesn't really exist in nature, like magnetic monopoles. Okay, unfortunately, the bad news is symmetries are very constraining. Okay, if you work out symmetry, you will find out that the Berry curvature is an odd function of its quantum number k. If you use time reversal symmetry, if the crystal has inversion symmetry, it's an even function of k. And if both symmetries are present in a crystal, you basically can show that Berry curvature is identically 0. So most interesting compounds, materials you have, like silicon, metals, and others, will have basically very boring geometric curvature or trivial flat quantum space. Yeah? So indeed, it's not so encouraging at this stage, and that's where our idea started spinning. So that now the next important development in the last 7 years is the development of nonlinear Hall effect. So it says that, well, anomalous Hall effect requires one to have broken time reversal symmetry. Then you can have non-zero Berry curvature and interesting science. But you can break certain symmetries of a crystal by applying external fields. And in this case, if you apply electric field, you shift the Fermi surface of electrons in k space, the quantum number space, and that breaks the inversion symmetry of electrons. As a result, you have imbalance in the occupied states in this shaded wedge as well as here, and imbalance between that, which is measured by the first moment of Berry curvature, can be non-zero even in time reversal symmetric system. And then there is a theoretical prediction by Liang Fu and Sodeman, which showed that you can have second order nonlinear Hall effect. So Hall current, which is current along y direction, is quadratically dependent on electric field along x direction, and the proportionality constant is given by d, which is the imbalance between this occupied states. Basically, it's called Berry curvature dipole. They are giving you mathematical expression here, and that's also readily calculated within the framework we work with. Okay, so if you have this effect, when you apply electric field with a frequency omega along x direction, it is going to create Hall current, which is at 0 frequency as well as second harmonic. Yeah, very interesting again, and it completes a consequence of quantum geometry of electrons. Okay, so this was the background, and the advantage of nonlinear Hall effect is the fact that I'm comparing here the anomalous linear Hall effect, where the current is applied flowing through left to right, and the Hall current comes along y direction, but they both are at the same frequency. So those two vectors add up, and you get electric current which is in the oblique direction, which is not so simple to measure. But the nonlinear Hall effect, even if the current is flowing with frequency from left to right, the Hall current is at a different frequency, 0 and 2 omega. So that is always perpendicular to the applied current, and hence easy to measure, unlike the normal Hall, anomalous Hall effect. Okay, so this effect happens when you have a non-zero Berry curvature given by capital lambda or d, and this is possible when you basically don't have, when you have a non-zero Berry curvature overall. Yeah, and this is rare because you need time reversal symmetry. And this nonlinear effect was demonstrated in 2019 by Pablo Herrero's group in MIT in two-dimensional tungsten telluride. It's a wild semi-metal, and I'll come to that in a minute. But it exhibits non-zero Berry curvature dipole, and hence this experiment showed that actually does, as the theoretical prediction of nonlinear Hall effect is indeed validated. Yeah. So this is the background to our work. And what Bhuvaneshwari did first is to establish that indeed the tungsten telluride monolayer has a non-trivial Berry curvature and dipole, and this is the calculated result of Berry curvature contour plot in the quantum space of electrons kx, ky, and you see it has a polarity, which is what gives you Berry curvature dipole, and this is the origin of basically nonlinear Hall effect in this. And the key is to have non-zero Berry curvature dipole, you need a system with fairly low symmetry. It should have only one reflection plane symmetry essentially. Yeah? So nonlinear Hall effect indeed is very powerful, but still a bit restrictive. So what we asked a question is, Well, let's not worry about systems which have lower symmetry in the average static sense. System can have lower symmetry in a dynamical sense. Right? If, for example, if there is a vibration, the basic idea in our work is given here. You have a fairly nice symmetric system with a hexagonal structure, and if you induce a vibration in this where the red atoms move to the right and green atoms move to the left, you will see that this vibration generates a dynamical state, a temporary structure of this hexagon, which has a much lower symmetry than this. It has a mirror reflection plane here, but it loses the C6 rotational symmetry. Okay, so this is to convince you that indeed when you have a dynamical excitation like a vibration, you can lower the symmetry of a structure. And then the Berry curvature can be non-zero. So vibration is a time-dependent oscillation. So it causes oscillation in Berry curvature dipole. Just like AC electric field will induce dipolar oscillations, here vibrations can cause Berry curvature dipole oscillations, and these oscillations will create oscillations in nonlinear Hall current, which can be measured. Yeah, and that's the key in our work. So dynamical lowering of symmetry basically induces a time-dependent oscillation in Berry curvature dipole with a frequency omega 0, that is the frequency of vibration. And as a result, you can, again, this is a mathematical expression, but again, very easy to interpret. It creates a Hall current, nonlinear Hall current, which has two components. The first one was already shown by Fu and Sodeman, which is the normal Berry curvature dipole dependent term, which gives you second harmonic generation at 2 times the applied frequency and rectification, which is the frequency equal to 0. But these are the terms predicted by us. These terms are in addition to the peaks that you expect, and these are basically dependent on the derivative of Berry curvature dipole with respect to u. And these terms include modulation of the AC frequency with vibrational frequency and also of the rectified signal with the AC frequency. Yeah. So so this can be possible even in the non-centrosymmetric crystal or centrosymmetric crystal. So even if this is 0, this can be non-zero, and that's where we win in sort of generalizing these ideas and making them applicable to very wide range of systems. So we propose this Jiquez spectroscopy, geometry of quantum electronic structure, transport spectroscopy, and the spectroscopy involves experiment like this. You have a sample, you apply electric field along this direction Ex. It's an AC field, time-dependent AC field, and it induces vibrations or oscillations in Berry curvature dipole, and you measure frequency-dependent Hall current, as simple as that. Yeah? And what we expect from this is, if you look at the spectrum of this Hall current as a function of frequency, this is the normal nonlinear Hall current at rectified signal and 2 times omega c. But our prediction is that there will be additional peaks. One is at omega 0, particularly when omega 0 is larger than the operating frequency, and the 2 peaks which are side peaks like Stokes and anti-Stokes. That's where the connection with Raman comes in now. Yeah? So there are Stokes and anti-Stokes peaks which arise from this modulation of vibrational frequency on top of operating AC frequency. Okay, if the applied frequency is larger than the vibrational frequency, then these 2 peaks become the Stokes and anti-Stokes, very similar to Raman spectroscopy. But you also have additional peak here, black peak, which is to do with the rectification signal modulated by vibrational mode. Okay, so this is transport mode of Jiquez spectroscopy. You can also do optical spectroscopy using these ideas, in which case you have a sample shown here. You shine light, instead of AC frequency, you shine light with a frequency omega L with electric field, which is along X direction. And what we predict is it will emit light, which is polarized with electric field along Y direction, and the spectrum will be given here. The first part is, of course, predicted by Fu and Liang, and these are our predictions. If the frequency of light is low, you will have 2 peaks which are centered at the vibrational frequency. So the beauty is, this peak is like an infrared absorption peak in IR spectroscopy, but the origin is very different. And these 2 side peaks are the Stokes anti-Stokes, which are peaks sidelining the vibrational frequency as opposed to light frequency in Raman spectroscopy. If the frequency is larger than the vibrational frequency, then you get Raman-like peaks. This is the center. frequency of light, and these two peaks are the Stokes anti-Stokes, but you have additional peak in vibration at the vibrational frequency. Yeah? So indeed, these are having similarities with IR and Raman, and then so far it was basically theoretical analysis. Now we need to convince you that indeed it happens in real world, and we don't do experiments, we do theory, which is as good as we can do for connecting with experiment. So first thing we did is to work on the system which is already studied by Pablo's group in MIT. This is tungsten telluride non-centrosymmetric structure, and you consider macroscopic oscillation of the material. This is like engineering, civil engineering or other structures that you have oscillations of the sample, normal mode of oscillation, which is given by this. In the physics jargon, particularly vibrational spectrum, it corresponds to longitudinal acoustic mode indicated here, and the frequency basically depends on inversely on the size of the sample that you have. So if you have, you can engineer that frequency, and if you freeze in this vibrational mode, you basically see that electronic structure near the Fermi energy starts oscillating. Yeah, these are strains of 1 and -1%. So electronic bands oscillate. But this doesn't tell you about geometry yet. Yeah, so then we go on to calculating the Berry curvature dipole and establish that Berry curvature dipole is a linear function of this particular vibrational mode, and which means we will expect spectroscopic signature in the manner that I explained. Basically peaks at these places, and the selection rule of the spectroscopy is basically the Berry curvature dipole derivative with respect to strain is non-zero. Yeah? Okay, so these are our predictions specifically for this strain mode, where we apply gigahertz frequency, which is relatively easy to operate in the lab, and measure the Hall response as a function of frequency. And by changing the applied frequency, you can move the peaks. And that gives you additional handle over measurement, right? By changing operating frequency, you can really make sure where the center of those two peaks is and detect the vibrational frequency. Okay, so indeed omega AC helps track the phonon peak precisely. Then we show the centrosymmetric structure. Centrosymmetric means it has its center of inversion, which means it doesn't have nonlinear Hall effect. It has no Berry curvature dipole to begin with. But, and that's what we show as a function of these two modes. One is an optical mode, BU, and one is LA mode. Even in the centrosymmetric structure, you can induce Berry curvature dipole with strain as well as the vibrational mode. The scales are different. The curves overlap, but the scales are different. So don't worry about the numbers. But the key is, indeed, in this case as well, we expect to see G-Quest spectrum, and this is the experimental setup. And we show that we predict two peaks surrounding the vibrational peak at 3.74 terahertz, and the separation between them is basically 2 times the applied frequency. Okay, so this is sort of something easy to measure as a spectroscopy, but it also has additional potential to be useful as a technology, because now your signal is in gigahertz frequency range, and what you produce basically is in the terahertz frequency range. So if you have a frequency modulated signal in gigahertz, you can transduce it to the terahertz frequency range. So that's really a powerful scheme. And indeed, at the moment, basically our idea of dynamical lowering of symmetry works beautifully well, introduces a new type of spectroscopy. But at the same time, my friends in condensed matter physics will still complain that, well, these ideas still are restrictive. They're applicable only to materials with narrow electronic band gap, and also those which have the potential to develop quantum geometry. Otherwise, these will be very weak effects. Yeah? So we now overcome this. Learning from the surface enhanced Raman scattering, we show that if you have a quantum material with non-trivial quantum geometry, you can use it as a substrate to measure vibrations in another material. So we take example of hexagonal boron nitride, which is a large band gap insulator, which will not have quantum geometry. But then we have graphene interfacing with it, which has Dirac points and possibility to have quantum geometry. So this is the vibrational mode of HBN, and this is graphene below it. And what we show is the Berry curvature dipole of graphene actually linearly varies with the amplitude of this vibrational mode, which means that the symmetry allows the vibrational mode of HBN to be active in the spectroscopy, but the quantum geometry doesn't support it. But then you can use another substrate with a non-trivial quantum geometry to detect these vibrations. That's why we call sense the vibration of the neighboring body. And indeed, the experimental setup that we propose is shown here. You have this sample of bilayer. You shine light with a frequency omega L and measure the emitted radiation with a perpendicular electric polarization. And this is what we expect. You have frequency of vibration, which is corresponding to the rectification signal, and then Stokes and anti-Stokes peaks associated with 2 times the phonon frequency. Please remember, in Raman effect, you get omega L, 1 times omega L. Here it's 2 times. So you color change and add on to frequency modulation. Okay, so this is what we show in, this is the vibrational mode, you see, and dynamically it breaks the symmetry of the overall system, and as a result we predict that this is what you should see. If you change the frequency of light in terahertz frequency, you can measure these peaks. This is the IR-like feature, and these are the Raman-like features. I think I have 5 more minutes, right, Rene? That includes. Okay, good. Then I can go a little slow. Yeah. So now we have a complete set of predictions for a centrosymmetric compound, tungsten telluride, which doesn't show nonlinear Hall effect normally. And the experimental setup is here. We propose to use the frequency at 2.52 terahertz because this is a commercially available laser. So we hope it will be available for some labs. And the emitted radiation as a function of frequency is shown here with a perpendicular polarization. So you will first see that there are 3 peaks, omega 1, omega 2, and omega 3. They are the 3 vibrational modes of this centrosymmetric tungsten telluride that come as infrared-like peaks, like infrared absorption peaks. The peaks are at the vibrational frequencies. But if the vibrational frequency is smaller than the frequency of light, omega 1, you will see that the 2 peaks are basically surrounding the 2 times omega L, and vice versa for omega 3. Basically, these 2 peaks are symmetrically placed with respect to omega 3. Yeah? So we have similarity with IR as well as Stokes and anti-Stokes peaks of Raman spectroscopy. So it's a rich spectrum, and we do hope it will be useful in sort of studies, and particularly much wider set of systems. So this is, so far everything I said is based on semi-classical physics. It needs to be worked out in quantum mechanical analysis, which we haven't done yet, but these pictures may be familiar to the Raman spectroscopist. Basically, if you have a ground state of electrons, then the first vibrationally excited states and so on, the Jigway spectroscopy, when the AC field is smaller than vibrational frequency, essentially means absorption of phonons and emission of phonons, and that gives rise to the asymmetry in the peak heights. If the frequency of operation is higher than the vibrational frequency, you have virtual transitions to higher states, which basically lead to absorption of a phonon or vibrational mode and emission of vibrational mode. These pictures are very similar to what you see in Raman, but the physics of these is very different. And you can also have rectification, which basically involves just emission of a phonon and absorption of a phonon, which gives rise to some of the peaks. So let me tell you now the similarity between Raman and what we have. In Raman spectroscopy, what you depend on is the dielectric constant of a medium or a polarizability of a molecule, and how that changes by the symmetry breaking vibrational mode. If you consider propagation of electromagnetic waves in a medium, you always generalize this dielectric constant to a frequency-dependent dielectric constant, and which has an imaginary component which depends on conductivity of a medium. And in this case, we rely on the off-diagonal conductivity, and that to second order off-diagonal conductivity, which is governed by the Berry curvature dipole. And we have an entirely new set of spectroscopies called quantum geometry of quantum electronic structure-based spectroscopies. Okay? So fundamentally, it's very different from Raman, but it has, of course, capabilities of Raman, Brillouin, and IR spectroscopies put together. So this is to remind you what Raman does. You have a light coming in and emitting a phonon and undergoing a reduction in the frequency of light. You have light absorbing a phonon, giving rise to increase in the frequency of light. In this spectroscopy, this is Raman, which has been around for 100 years. In the spectroscopy we propose, you have 2 photons or applied quanta coming in, and phonon gets emitted, and it undergoes reduction by the phonon frequency, and likewise 2 photons come in and give rise to anti-Stokes like peak. but at 2 times the frequency. Yeah, so they are different in not only the frequency spectrum, but also they are fundamentally different in the origin. Raman comes from polarizability. This, our spectroscopy, originates from quantum geometry of electrons. So, and the interesting thing is our spectroscopy is operatable in light mode, light spectroscopy, as well as Hall circuit spectroscopy. So we have some wider range of applications possible. Let me summarize my talk now. We introduced G-Quest vibrational spectroscopy in the 2 modes, transport and emission modes, and which combines capabilities of IR, Raman, and Brillouin with similarities to their features. Secondly, it may be generalized to other types of dynamical excitations like magnons or plasmons, and that's something we are taking up. In fact, magnons may be measurable even at a lower order Hall effect because of the symmetry breaking associated with them. And now we also show that quantum geometry ideas, which were earlier thought to be relevant to very narrow set of systems, will be widely applicable to many systems, and we expect them to be even richer in 3-dimensional crystals. Everything we did so far is in 2D, and we feel there are exciting opportunities possible in 3D. I acknowledge my co-workers, Bhuvaneshwari and Mandar Deshmukh. Mandar is now engaged in experiments, and he actually has found some of the signals in the transport mode of the spectroscopy. And we are quite excited about it, but we don't fully understand this experiment yet, so that's work in progress. Thank you very much for your attention. Sure, sure.
Yeah. Can you tell us the approximate value of Vx you use, electrical field that you apply? And number 2, will temperature play a role in your effect? And will that not be a very critical constraint on observing your effect?
Temperature effects may change the line width, but okay, I'll use this mic. Yeah. So I don't think temperature will wash away these effects altogether, because the ideas are essentially same as Raman. In fact, higher the temperature, you may have more vibrational excitations, and it may make it easier to observe some of these effects. Now, the electric field used in the Hall measurements, I don't have exact value, but it's about a micron size sample and a voltage of about 5 to 10 volts. So that's roughly the electric field I can tell you, which Mandar is using in his measurements. In lasers, of course, you have higher intensity electric fields, densities, which are possible, particularly the terahertz laser that I pointed out. Sure.
When you are very near to metallic state, you will also have an electric field generated by the electrons themselves,
Yes.
induction electrons. Will they not hurt you?
Yeah, no, the frequency response is in a different domain. See, the beauty of this is, unlike Raman, in Raman, basically you have frequency of light, omega L, and the vibrational peaks come below and above that. In this case, it's 2 times omega L, and in that sense, it's really out of the normal responses that you measure in the lab.
Umesh, thank you. Very fascinating talk. This WTE2, which you said TD phase, is a 3-dimensional Weil semi-metal. But do you take into account, or does it make a difference if your cones are tilted? Because these are tilted in this TD phase. So that does it introduce additional feature?
Well, it will change some of the features, sure, but the basic concept here is. I'm sorry. Yeah, the basic point is the Weil point acts like a magnetic monopole. here, the source of Berry curvature. And if a small gap opens up, in fact, it becomes little more spreaded around it. And in graphene, that's what happens. If you take pure graphene, Berry curvature is non-zero as a delta function at k points, and it cannot be really leveraged. But moment it opens up a gap, it has observable consequences. Now, the opening of a gap will also lead to asymmetry in the Dirac points, but it won't be it will introduce interesting features. We don't know the exact, specific details, but
So as such, what you are saying is also true for type 1 while semi-metal,
absolutely.
which are three-dimensional already.
Yes,
So the same feature should occur there,
absolutely. It will be even more rich is what my expectation is.
like
Ajay.
tantalum arsenide or
Arsenide will
something.
be an excellent case to take up. Yes, yes.
Nice. Thank you.
Thank you.
Yeah, Dr. Ghosh was asking. No, I was asking for you. I asked a question.
Umesh, this connection between the geometric phase and you said the average position of the electron. Is that peculiar to two-dimensional, physical dimensional systems, or
Okay.
it's a general result?
No, it's a totally general result. And in fact, I had slides ready on that, and I can show you offline.
All right.
But basically, it originated from the theory of polarization. Polarization is electric dipole moment per unit volume of a crystal. And this quantity you cannot calculate using just charge density and wave functions.
No, basically my confusion arises from the fact that the geometric phase as such is defined over a curve in the physical space of the quantum system. Now, your average is associated with a curve in the physical space?
It's a space of quantum numbers of electrons, which is what I introduced initially, momentum
Anyway,
quantum numbers of electrons.
I would be very happy to understand that
Sure,
connection.
yeah. Thank you. Thank you, Rene. I'll leave my laptop out.
I now invite Professor Gunanathan to deliver the vote of thanks. This will be followed by a group photograph just on the steps outside, and then we proceed for tea and come back by 11:15 for the next beginning of the session. Yes? So, Professor Gunanathan.
Good morning, all. I feel honored and privileged to propose a vote of thanks on this special occasion. First, I would like to thank Professor Umesh Wagmore, the President of the Indian Academy of Sciences, for giving us the opportunity to host the 90th annual meeting of the Academy and for his active participation in the meeting and presenting the fascinating presidential address. I'm also thankful to Professor Partha P. Majumdar, the previous president of the Indian Academy of Sciences, for gracing this occasion. I, on behalf of the organizing committee, convey deep regards and hearty thanks to Professor A.K. Sood, former president of the Indian Academy of Sciences and principal scientific advisor to the Government of India, for being here and delivering a special lecture. I would also like to thank Professor Ramaswamy, past president of the Indian Academy of Sciences, for being here with us. I would also like to thank Professor Hachan Ghosh, Director NICER, and Professor Sripath Karmalkar, Director IIT Bhubaneswar, for their support in organizing this meeting. I thank Professor Rene Borges and Professor Vijay Mohanan Pillai, the Secretaries of the Indian Academy of Sciences, and also Professor Sri Mahesh Chandra, the Executive Secretary of the Indian Academy of Sciences, for working tirelessly to organize this meeting. I'd also like to thank Professor V. Raghunathan, Treasurer, Indian Academy of Sciences for his support. We are also thankful to Sri Jagadanandana, Center for Youth and Social Development, and Professor Nainjot Lahiri from Asoka University for accepting our invitation to deliver a special public lecture at this meeting. We are also grateful to the cultural team of Dr. Chitranjan Shahani for accepting to perform the cultural program. I would also like to thank all the honorable delegates who blessed us with their presence here. I am also thankful to the Program Advisory Committee members and the invited speakers. I would also like to extend my sincere thanks to the staff of the Academy for their support. I am very thankful to the faculty members and student volunteers of NICER and IIT who helped organizing this event. I cannot take all the names, but I am thankful to each and every one of the student volunteers and the members of the organizing committee. I should specially mention Professor A. Srinivasan, Dr. Nayendra Sharma, Dr. Tapan Mishra, and Dr. Vishnu Biswal for their tireless support. My sincere thanks to the NICER staff for their support. I would also like to thank the caterer for providing us with delicious food and the technical team of the auditorium for their support. We have tried our best to make your stay pleasant. If there were any shortcomings, we sincerely apologize for that. It was not intentional, but we take the responsibility. Please reach out to us if you face any problems during your stay for the next 3 days. Enjoy your meeting. Thank you.
लोग वो कर रहे हैं कि हम लोग हमारा लैपटॉप लगाएंगे and publish work.
अब अगर प्रॉब्लम होगा तो क्या करेंगे फिर?
उसे बार-बार हमें चेंज करना ही पड़ेगा.
करेंगे तो फ्लिकरिंग हो सकता है. देयर इज अ चांस. सो नो प्लीज.
जैसे मैं चाह रहा हूँ यही प्रॉब्लम.
पूरा डी कॉन्फ्लिक्ट जो कि टॉप सीक्रेट you have normally convince people. Anyway, that's fine.
So you have PowerPoint here? PowerPoint, I mean, plug points? Can you plug this for me?
What's that?
Hmm? Let's see.
There is one laptop up there. Anything you can.
And music, we haven't followed this. You know,
So how do we do it?
So I was telling, discussion is also needed.
Correct.
So each one will give a 28-minute talk, 2 minutes,
Yeah.
and plus 5 is there at the end.
Yeah.
So it will be 13 minutes of discussion
Correct.
at the end.
Right.
We will
So-
not stop in between.
Sure.
We'll ask them to remember
So,
what
have
was.
you loaded or? You will load it, okay. Go ahead. What about yours? Oh, you're also loaded.
Yeah, that way it's better. Otherwise, every time laptop will take time to.
Yeah,
Simulate.
the problem is some of my stuff.
Yes, it is very difficult.
We are not published.
Yeah, those things. No, because you're going to start, right? It's okay.
No,
In between is a problem.
I'm going to take all his data.
so
That's
this
okay.
is
I'm retired now. You can take everything I have. I don't need anything from you.
ma'am, yours.
So data is given free.
To everything. As long as my student's name is there. I don't
This
need my name. That's what I said.
Yeah, next 5 years until 2029. Mine is the first one. Yeah. For me, I just need the HDMI.
Oh, only HDMI.
HDMI, that's all.
Okay.
HDMI hai?
We have an HDMI.
Yeah. I just need an HDMI. ना अभी नहीं 5 मिनट ये बात करेंगे. No, you connected. No, it's okay.
Yeah.
Connected.
What you can do, you see, I prepared this. You know, we should.
Yeah. You should do that part.
No, just connect that.
Connect
for
this
second.
first HDMI.
Or for
We
will
can
come this
connect
one.
all these two here only.
Yeah.
Then there will be no problem.
Yes.
We do not need this dock.
This one. For your
Oh,
thing,
okay.
you can connect this itself.
Just for few minutes only.
Yeah.
And then he will come.
I need an HDMI. That's all. Keep it with you.
Yeah. This keeps coming by this Jerome thing, no?
It's detecting.
No, the problem is I'm getting this thing down. Wi-Fi still. Let me close.
Now you can use that.
Oh, just a second. We can see from here.
I'll do.
Can you do that?
That's fine.
Okay, good. Okay. Well, that's fine.
Sir, if your file we keep in this pen drive, then for whole session we use this one.
Actually, this thing I didn't want to.
So,
Some data.
get your microphone. Giving the-
Yeah, yes.
Not for me. I will speak on that.
Yeah. Give me that.
Just start, right?
Okay, ready, huh?
Very.
Shall we start? Is it okay?
5 minutes.
Right,
Put a bell
that's
and
what
then
I'm
make. So both of you can take it.
Yeah. Hey, Chandrabas,
There was time just.
I'll share your talk and you share my talk. Then after that, I'll share my lead. You share it.
Actually, what we can do is all the 4 people you introduce right away. In the introduction itself, you introduce.
Okay.
Then we continue.
No,
That-
questions. Somebody has
Question
to
last.
moderate the question.
Last week, at the end, we'll ask. After the sessions are over.
Oh, is it no questions in
No,
the
in the
It's better to have a combined.
combined
session.
session.
And then if time is out, you can say that, you know, we'll take time.
1:30.
Yeah, so they will start leaving.
We'll start like only after that.
After the
I will
questions.
instruct. Okay. You only say that. See, there is lunchtime. You can discuss. If there are more, let's say,
Questions.
1 or 2 questions we have.
That's what I'm saying. After the talk.
No. Yeah. Don't start now. First he is going to introduce.
Hello, good afternoon.
Welcome back to the Raman session. So I wanted to just give you a little bit of history of scattering Raman processes. In 1923, K.R. Ramanathan published a paper describing scattered light having different frequency compared to the incoming light. That was the first indication of Raman shift, basically. Then that was followed up by K.S. Krishnan in 2025. In some more systems, he showed there seems to be a shift in frequencies in the scattered light with respect to the incoming light. So that is why we are celebrating first observation of Raman effect, or not scattering effect. Today, 100 years of scattering effect. Of course, Raman realized and understood that it is actually related to polarizability, dielectrics, and therefore molecular structure in 1928. And therefore, he announced the discovery on 28th February 1928 in the evening around 7 o'clock. And of course, 2 days later, he submitted the paper to Nature. And by the end of March 31st, Nature published it. I wish they could be as fast today as it was in 1928. Now it takes 6 months to 1 year to process the papers. Now, Raman scattering initially was an extremely difficult, because as you know, is a very weak phenomenon and very difficult to observe at precise details of frequencies and amplitudes. And therefore, it was continuously be a specialized domain of people in physics and chemistry. In 1960s, lasers were discovered, and lasers were able to give you precise wavelength, which was unlike in the past where people used to use white light, either sunlight or mercury, and then select the frequency that you're interested in and then put into the sample to observe the scattering, because you need very precise wavelength to measure the Raman scattering. Lasers became, of course, you are able to change wavelengths, and you are able to change power, and you can even change the time domain, light coming into the system. Therefore, the technology of applications of Raman spectroscopy to all kinds of applications have started evolving. And as it evolved, then detectors and spectrometers got better and better. And I can tell you, even today, there's continuous evolution of technologies getting smaller, more efficient, and broader ranges in terms of both detectors and lasers. So what we're going to show you today, the 4 speakers, is about how Raman spectroscopy has evolved from being a simple measuring of highly specialized areas to applied areas of spectroscopy. And there are 4 speakers. The first one is Dr. Chandrabas, Professor Chandrabas Narayana, Director of Rajiv Gandhi Center for Biology in Trivandrum. Then followed by him, I will give a talk on what I've been doing for last close to 40 years. I started in 1986 on Raman spectroscopy, 38 years now. And then followed by Dr. Murali Krishna from ACTREC in Tata Memorial Center in Bombay, working with the Tata Memorial Hospital, applying Raman spectroscopy to biodiagnosis. And then Dr. Nikki Kuha, who did a PhD with me, and then went and joined Delhi University. And she will talk about some applications in protein folding, extremely fundamental question that she will be addressing. And one request that we have, based on convener's discussion, is that since all of them are Raman related, we will have lectures continuously. At the end of the 4 lectures, we will have a discussion session, maybe 5-10 minutes before lunch. So with this request, I request Chandrabas to give his talk.
Thank you, Uma. HDMI. Well, Uma is. Thank you. I should thank both the secretaries who actually contacted me and the president for allowing us to organize this special session on Raman. And it is indeed, I hope what we have put together will be really interesting to most of you.
who would be liking to use this in their. I don't know. Yeah. Okay. So I also, like Uma, started my Raman journey in 1988. So it's been a long time working with Raman. I won't be actually showing the whole what I have done. I have picked up some examples to excite people. And lately, I've been actually working with Raman in biology, so I will be actually doing that. So since I am the first speaker, I actually take the privilege of actually getting ball rolling. In fact, Raman, when he actually started looking at molecule scattering itself, he actually was the first work was actually a 1921 work where he was actually looking at the color of sea itself. And he published a Nature paper in 2021 while he was actually traveling in the ship across the Mediterranean, and he did this experiment. As most of the people at that time, even Lord Rayleigh, who was very famous at that time for scattering itself, has said that it was the reflection of the sky. But Raman didn't believe that, and he wanted to prove him wrong, and he did the experiment in the ship. And he was very beautifully done this experiment, because whenever you have a reflection, you have to have partially polarized light. So he actually used Nicol prism or Nicol to actually do the polarization. So he said that if my light was polarized, that means it's a reflection, I should actually be able to make it dim. And if it is not dimming, then it is not reflection. So this is a simple experiment he did over the journey, and he actually concluded, in the words are very simple to understand, and he wrote this paper and immediately in the harbor submitted it to the Nature and got it published. And that is where it started, and in the end of the paper he writes, it is something to do with the molecules itself. I will not go into the detail of why it looks blue and other things in this talk, because there is no much time. So in fact, this is how it started. Now, how do I actually show you that Raman scattering in fact happens? It is actually inelastic scattering of light. Like Umesh was mentioning earlier, it is not the same light which is going in. It's a light which is transformed, and you have shifted frequencies. Now, this is an example of elastic scattering. That means no change in color. So the blue light of the laser is actually happening. And you can see here, this is a scattering from the dust particle in the room. And this is a scattering from the transparent liquid, which happens to be cyclohexane. And it is looking white because the scattering is actually saturating the detector. That is your camera. And that's why it looks, otherwise to a naked eye, it will be blue in color. In all directions, it doesn't follow the reflection law. That is Snell's law. Angle of incidence is equal to angle of reflection. Now, when I actually black out the blue, so I have put a filter and I have removed, so you can see the dust particle scattering is gone. I can see the shifted light. And this is basically what Raman actually looked at. And this is what got him the Nobel Prize. So in fact, you can actually do this. Basically, we want to know what are the shifted lights. So you actually put the light into the bottle. You don't even have to take it out of the bottle. And you collect the light through a fiber and actually get it dispersed. So you use a dispersing agent, which is basically the grating. And you take a photograph of it. A normal camera would do. And if you take the photograph, you see this is the shifted light. This is elastic scattered light, which is the green light here. And it is very intense. And then you have shifted light. Now you digitize it. You already have a Raman spectra. So this is basically how the Raman spectra looks like. And the difference between this shifted light and the elastic scattered light is actually the energy of molecular vibrations. And this is what Raman actually discovered. This is the Stokes side, that is the red shifted light. You can also get it to the blue side, which is the anti-Stokes side. Now, this is basically, molecular vibrations are so unique. You have two atoms connected, the only vibration they can do is stretching. And whether it is hydrogen, it is nitrogen, oxygen, any of these molecules would do these vibrations. I have taken an example of HCl and HF. The only reason I took that is to show that different masses actually have different frequencies. And these are all simulated, like what Umesh had shown, there is a simulation of this So when you are actually simulating, you can see lighter atoms have a higher energy of vibration. So that means the shift will be larger. And when you have a heavier atom, it will be lower. So this means that you have a relationship to the frequency and the mass of the system and the spring constant, that is basically your bond strength. Now I have taken water molecule and immediately the number of vibrations actually increase, and there are 3 vibrations. One is a symmetric stretching, asymmetric stretching, and symmetric bending. The only difference between the bending and stretching is bending is actually no change in the bond length, but it is only the bond angle which is changing, and while bond stretching is when you have a change in the bond length. So this is very, very important because the energy depends on how much energy is required for moving these atoms, and that's why stretching is always higher energy compared to the bending. Now I actually take a similar looking molecule which is CH2. Now it looks exactly like the water molecule, so it also has vibrations exactly like that. But only difference is the CH2 cannot be considered as water because it's not independent. It has a R group which is actually attached to it, and because of this thing, it will have additional vibrations, which means it has a wagging, twisting, and also rocking and scissoring. All of these things they are added. So you can see these vibrations are very much related to how they are connected to the different atoms present in the system. Now I have taken an example of carbon tetrachloride. Any tetrahedral molecule like methane, SO4, all of them will have the similar spectra, looking spectra. And this is actually simulated again. So you can see there is symmetric stretching, asymmetric stretching, symmetric bending, and asymmetric bending. So if I actually look at it very carefully, this should have been a single valued peak, but what I see is that there is some wiggles on that. And whenever in spectroscopy, if you have a multiple peak present, whether it is mass spec or your NMR or any of those spectroscopy, just lower the temperature because the width of the peak will happen. And I lower the temperature and I see, in fact, that is not a single peak, but it has multiplicity. Now this multiplicity is because of the fact that chlorine can be having 2 different masses. And I had actually told in the case of HCl and HF that mass actually affects the frequency. Now you see that this is because of the mass difference. Now I can have all 4 Cl35s, all 3 of them Cl35s, 2 of them Cl35s, and you can have 1 of them Cl35 and all of them Cl37s. So that is the reason for this. So what is important here is I can isotopically also have an effect. And in biology, most of the times you can do deuteration or you can do a nitrogen substitution or a carbon C13 substitution in your amino acids and protein. I'm just talking about protein. So you can do those kinds of things and actually see which vibration is because of which moiety inside that particular system. So this is where I wanted to learn. So it actually has very significant effect when you are actually looking at it in biology. So Raman spectra in this whole tutorial I had actually shown is basically a fingerprint of the molecule, and that means it is very, very important that if we actually look at it, it can give you a lot of information about the molecule itself. And once you know the molecular structure, molecular nature, then you can talk about its physical properties and all. And in case of proteins, actually conformational changes and others also makes it very easy to actually detect it, and that's what I'm going to talk in the later part of this talk. So I was actually working in physics for a long time. So from the time I was working with Ajay Sood and then later on went to Cornell, and we have been actually looking at various things in the physics domain. So one of the examples is this, before I came back to India in Bangalore, I actually was looking at a very exotic problem, basically a problem which is there in Jupiter. The Jupiter is one of the planets which has only hydrogen in it. Maximum is hydrogen. And people have been actually conjecturing that it must be liquid hydrogen. And if it is liquid hydrogen, it can be also superconducting, that it actually can be existing. So one of the elemental systems which can be superconducting at such high temperatures and high pressures. So this is what was the thing, and it is still a holy grail of condensed matter. In fact, people are still working on this for a long time. But to apply pressures of that nature, we can actually do it in the lab, which is using this diamond anvil cell, where there are two gem quality diamonds into which you actually put in your gasket and put the sample inside. And since pressure is nothing but force per unit area, you actually reduce the area, you can go to very high pressures. So basically in lab, you can get millions of atmospheres without any problem. But the only problem is the sample is actually less than few microns. So that means you cannot do many experiments with it. And hydrogen, it becomes worse, that you cannot actually do with many experiments. So most of the times, Raman is the best way to look at it, because if it is a hydrogen molecule, it will have a vibration, and with vibration, you will have a spectra. If it is actually becoming a metal, this vibration should break. That means it should actually break and become atomic. And that is when it will actually do this. In fact, our results at that time showed that up to 3.4 million atmospheres, to get you the picture correctly, 3.6 million atmospheres is actually the center of Earth pressure. So in the laboratory, we have achieved that kind of pressures and shown that hydrogen still is not a metal. So this is a very interesting, and over 3 decades, it still stands as test of time, and it still is an expert. So these kinds of experiments is what we were actually working on. But then when I actually joined JNCSR, I got interested that Raman can also be looked at in biology. So recent experiments is what I am going to tell you. But my approach was, shall I use Raman for understanding what can we do in understanding the protein structures? Because one of the major issues at that time is you have the best X-ray crystallography available, best techniques available, best softwares available, but you cannot crystallize all the proteins and get the structure. So can I actually work in between with Raman, because it is a fingerprint, and can I use it? So this is what was my approach, and that is what I'm going to actually demonstrate with a couple of experiments, a couple of examples. And this is the first example. Here, I was actually approached by a cataract surgeon. His problem was that when you are doing a matured cataract surgery, many of the times it is successful, but there are few times that the lens capsule actually cannot retain the lens and the visibility doesn't come back. This is an issue which is there. So he was wanting to understand, is there something happening to the lens capsule while this surgery is being done? Especially they were interested in knowing whether typane blue, which is a staining dye, used for them. I'll tell you why they use this dye, because most of the people go to the surgery when their cataract is mature. And to see this lens capsule, you add the typane blue and do a capsulorhexis, that means a tear in the lens. To see the lens capsule, you have to put the dye, and after that they wash off the dye, excess dye, and then do all the removal of the lens and put back the new lens. Now the question is, this lens capsule loses its elasticity or stiffness, and that is what people were actually interested, and there is no technique in the world which can actually answer this in live, in vivo. So we started looking at it. So what is actually the lens capsule material? It is nothing but collagen, which is basically collagen 4, has triple helical structure. It's a triple alpha helical structure, and it forms a nice little hexamer, and then it actually also cross links. There are sulfur bonds which actually cross link it, called the 7s domain, and forms a network. And this network actually is supported by small proteins at the bottom, and this is what the total eye capsule is looking like. So when I looked at it, I actually realized that it is like a fishing net. Now what I have to actually look at, when the fishing net is fully nice, new, it has all the braids in order, and its knots are evenly present, so it has this elasticity and its stiffness and everything is correct. Now when it actually starts deteriorating, the fisherman actually starts doing cross linkages, and also the braids actually open up. So that is when the stiffness of this net is changed. So I am looking for the same signature in my eye capsule. So what do? I actually take a collagen 4 from the market and I take the human lens capsule, and you can see the Raman spectra is actually identical to each other. And the most important regions which I am going to look at is the amide 1 and the 7s domain, which is the sulfur rich domain, which happens to be around the 500 region. But I will also look at something around this region, because if this 7s domain is actually cross-linked, that will be actually present around 800 region. So this is something which I am actually going to concentrate on. Why do I look at amide 1? Because amide is actually C double bond O NH, which is a peptide bond, which is actually present in all the amino acid complexes, right? And this is actually hydrogen bonded. And depending on the difference in the hydrogen bonding, the secondary structure comes alpha helix or beta sheets or random coil or beta turn, various other things. Now, this is the vibration we are having, different types of vibration associated with C double bond O NH, and this is very, very influenced by the hydrogen bonding itself. So in fact, statistically it has been shown that they collapse onto different regions when they are actually present. And we can actually see the random coils happen to be closer to the 1700. It actually has different ranges, and these are well understood. Now what I do is I zoom up the region of the amide 1 and see for the collagen 4 itself, and I see there are two peaks. Both of them are because of the alpha helical content. One is because of the polar type, and the other one is the non-polar type. Now, when I look at the lens capsule, then I also see the two peaks which are actually present in this system. Now, the immediate experiment is just take the Type-N blue and add to the lens capsule. The moment I put the Type-N blue, because it's a dye, it also gives you a Raman spectrum. So you can see the Type-N blue Raman is present here, and this is actually a superposition of the Type-N blue and the protein. But luckily, the regions of the amide 1 and 7s domain is cleared. Now, what I wanted to look at is what happened when I put the Type-N blue. Here, it was only two peaks. I suddenly see a peak around the larger region 1700, which means the braids are opening up. That means the ordering, alpha helical ordering is getting disturbed. Now, what I do is I do the dilution of the Type-N blue. When I do the dilution, I see that the dilution actually, as you increase the dilution, the effect of the Type-N blue is going back. So there is no change in the alpha helical content. But the Type-N blue as seen in the bottle is this, and 5 times dilution is what the doctor uses. So this is not all. There is another interesting aspect. The Type-N blue is actually exposed to the white light, because surgery you do it with white light. This white light is very important because it actually produces a reactive oxygen, and that's what is happening. So you see, I have 2 concentration as is from the bottle and 5 times dilution. I see a 10-second window when I use 5 times. So the surgery has to happen within the 10 seconds if it is to be successful. But I wanted to also understand if there is a cross linkages. If I am having cross linkages, this is an experiment with goat's eye. You take the goat's eyes capsule and then you do a Hooke's law, stress by strain. So when your stress by strain is there, you will actually have this curvature. And if this is actually shallower, that means it is becoming stiffer. And this is what happens as you actually do only with the light, only with the Type-N blue, or light with Type-N blue, and also with another cross-linking agent, which is glutaraldehyde. Glutaraldehyde actually facilitates sulfur-sulfur linkages, and that will actually cause the stiffness. So basically what is happening is that when you have the Type-N blue and the light, you are having stiffness increase. That means cross-linkages happening. Now I wanted to understand, can I see it in real system? So I do the experiment where I put glutaraldehyde to the lens capsule and I put Type-N blue to the lens capsule, and immediately I see the presence of these 2 peaks, which was not there when it was only the lens capsule, which shows that there is cross linkages happening. So there are 2 things happening. One is the ordering, alpha helical ordering is getting affected, and random cross linkage. All this happens within after 10 seconds. So basically what we told the surgeons is, if your surgery can be done with 5 times dilution within 10 seconds, it's fine. All of us will be very surprised. that they only take 6 seconds to do this whole capsular axis, because once they do that, they wash off the Taipei blue, and I have shown you when you dilute the Taipei blue, the effect is not there. So the whole community now agrees that the only problem comes when there is a delay in this whole aspect, and that is what is the reason for the failure. And this has actually solved a major problem in actually getting the vision back to people with cataract. In fact, next example is all proteins are not easy to look at when you do normal Raman. Many of the therapeutically important proteins are very low concentrations, and as Uma mentioned earlier, that there is a low scattering cross section. So we have to enhance, and this was what was Umesh alluded to, something called the surface enhanced Raman. Basically, if you take silver or gold nanoparticles, and if you actually put light on it, it produces an extra electromagnetic effect, which actually helps in increasing the Raman. And this is very used by people. The whole physics of SIRS is still theoretically not understood, but the use of it is very high. So people have started using it. So we use this nanoparticles. We actually put analyte in this ratio. That means protein plus nanoparticles in this ratio. Mix it, incubate it, then we centrifuge it, take the supersaturated samples and put on a hydrophobic sample, and we do the Raman. Because proteins, when they are dehydrated, it actually denatures in many of the cases. And that's the reason why we want to keep the native state. But the advantage of the SIRS is that when you have no nanoparticles, your spectra looks like this even for 10 to the power of 5 molecules, that is microliters. Okay, and here you can see not microliter, 10 to the power of 5 molecules in 400 seconds gives you this kind of a spectra, but 1 molecule in 0.5 seconds you can get using a nanoparticle. So that's the enhancement factors which we have with Raman. So we were actually interested in using it, and I've been using it for some time, and recently we were actually looking at aggregation of protein. This is one problem which most of the biologists are actually trying to understand. If you understand the aggregation process, you can arrest the process, and hence you can actually cure many of the diseases. So we were actually looking at hen egg white lysozyme. And why is that we are interested in hen egg white lysozyme? Because it is present in most of our body fluids, and this is actually a kind of antimicrobial enzyme, as well as it is actually present for many of the diseases also when they are in aggregated form. So all this Alzheimer, Parkinson's and Huntington disease show lysozyme aggregations. So that is why the aggregation itself is interesting. But what is interesting is that human lysozyme extraction is a very difficult thing, but hen egg white has a large lysozyme. So we can actually do these experiments with that, and that's the reason why we do. Now there are two types of aggregation process can be done. One is you can do an acidic way or a basic way. So if you change the pH, you can actually aggregate. Only difference is when you have acidic pH, you are actually needing temperature to aggregate it. But if you have a basic pH, it aggregates spontaneously. So we chose the basic pH, which is 12.2, where spontaneous aggregation happens. You will have a monomer, then oligomer, and then it actually starts forming fibular arrangements. You can actually visualize it very easily. But our interest is, what is the aggregation process? How does it ride? So we actually started the experiment with 7 pH and 12 pH, and we actually look at what happens to it. So our experiment, we wanted to check with solid lysozyme, which you can get it from market, and you have a 7 pH and 12 pH, and at start of the experiment you can see the spectra looks the same. That means everything is normal. Now when we start looking at it, I am looking at because I am looking at any changes in the conformation. So here is the amide peak, and you can see these amide peaks are because of the alpha helix, beta sheets, beta turns and random coil or unordered structures. So as we go on days, when we start, you can see slowly the spectra is changing, and you have an alpha helical content changing into beta sheets. directly, and it is live. We can see over 10 days, you can see that it has actually changed from alpha helical content to beta sheets itself. Now, using this information, actually I look at it in 7 pH, you can see there is absolutely no change in the amide peaks, while in the case of the 12 pH, you can see a sudden transformation from alpha helical content to beta sheet itself. Now, this was known, and you can see the aggregation process in 10 days. You can see how this aggregation is happening. 25 minutes is over, 2-3 minutes is more there. Okay. So what I am seeing here also is another interesting aspect. While I am actually looking at this, the disulfide bond, which is present at around 500, is actually getting lower in intensity when I have pH 12, and there is no change in the 7 pH. Now this is a very important clue, because in the case of the lysozyme, there are 4 cysteine linkages, and that is what actually stabilizes the structure. These have sulfur, and this sulfur content is actually breaking, disulfide bond is breaking. That means that is the initiation of this aggregation. So we told them, our in-house MD simulation person, to simulate it, and in case of MD simulation you cannot break bonds, so you break it physically, these 4 cysteine bonds, and see what happens in different pH. Now when you do this, you can actually look at it that we are looking at the distance between the sulfur-sulfur linkage. So at 7 pH you can see the black curve has no change at all. That means the sulfurs remain closer to each other, while in the 12.5 they are actually going farther away. That means that is the initiation. Now you look at the structure. At 7 pH it remains in the same structure, while you are actually going in 12 pH, you can see opening up of the alpha helix. So this is basically the starting point, 1. Now we also brought these two physically together, so to see whether they will start aggregating. So when you bring them together, you see that in 7 pH there is no interlinking, while in 12.2 pH you can see they start forming aggregation. So basically the aggregation process is driven by this sulfur-sulfur bonds. Now can I actually arrest it? There is a iodacetamide which actually can stop the sulfur from going and forming a linkage again. So if it is opened up, I can stop it, because it is iodacetamide stops aggregation process itself. So now you see that when I do that, absolutely as soon as I start the 12.2 pH, immediately I put this iodacetamide. After some time, you see there is absolutely no change in the amide peak. That means there is no aggregation at all. So basically, and also we can see there is no change in the 500 peak itself. So basically what I have shown is that the aggregate, we can actually identify the aggregation process, the driving factor for the aggregation process, and hence we can actually say that we can actually tell molecular nature of aggregation itself. So these are 2 examples I have actually shown you that we can use Raman only to use this one. I would like to thank all of you for your attention, but I would like to thank my groups both at JNCSR and Rajiv Gandhi Center for Biotechnology, because they are the reason why I can speak like this, and thanks for them. All this work is done by these people. Thank you very much. So we'll have the question at the end. So I'll ask Uma to give the talk.
Okay, so I would like to thank the Academy, and of course the President and the Secretaries for giving the opportunity to share the excitement of 100 years of Raman. And I can tell you that the Raman community in the world is actually talking about celebrating centenary on 2028. hopefully in India. And that should going to be for Raman spectroscopist, coming to India is like going to Mecca. And therefore, I think it's going to be a big celebration. So I'm going to talk to you today about some work which is more contemporary in the last 7 to 10 years and something more very recent in the last 2 years. So I'm going to talk about ultrafast Raman spectroscopy. You will see that pedagogically speaking, one would say that you cannot do Raman spectroscopy or measure scattering using ultrafast pulses. And I will show you how we do that. And therefore, what do we learn from it? And then we will also show you a technology that we have developed using Raman spectroscopy to identify material hidden in boxes and bottles and envelopes and packets. This is something we are going to now put it at Bangalore airport for trial in the next month or so. I will show you an example. And finally, we have now incorporated artificial intelligence over the last 4 or 5 years, particularly for biomedical samples coming from hospitals. And I can show you one example of how we have used that. Ultrafast, for example, why do you need to study ultrafast? That too at the resolution of vibrational spectroscopy. The most popular is something that happened in the last 20, 30 years is photosynthesis, artificial photosynthesis. People are trying to use sunlight to convert sunlight into energy using artificial photosynthesis, trying to mimic. The rate at which the energy is converted from sunlight to energy is less than few milliseconds, which means the femtosecond time scale the process starts. Similarly, hemoglobin, for example, it takes oxygen, releases oxygen, and takes carbon dioxide, carbon monoxide. The rate at which it releases and takes, and that's why cyanide is poison, because cyanide is absorbed or bound to hemoglobin much faster than, for example, is oxygen. And therefore, to understand what in a chemical structure of a hemoglobin structure, what influences the binding rate is the question that one has to understand. And similarly, retina, in your eyes, there is something called a retinal protein which actually recognizes the signal and sends it to your brain. And again, you want to understand, if you want to do artificial eye, how does it work? And of course, I can give you more examples. In physics, you can look at soliton dynamics, lattice structure oscillations because of conductivity of electron. So what happens at different time scales, which I think most of you know, this is something you are familiar with. And if you actually go faster, the fastest is 10 to the minus 18, which is the motion of electron. But when we talk about femtosecond, is equivalent to a vibrational period. And that's what we are actually be looking at this time using Raman spectroscopy. You can actually watch vibrations happen in real time using Raman. So when you watch vibrations happen, you understand how the structures move, how reactions are induced in any process. So the ultrafast pulse, a femtosecond pulse, can be considered as some sort of a burst of energy, but it has a phase space in addition to a frequency space. So if you actually do the Heisenberg's uncertainty principle, if you compress the pulse extremely small as a laser, what happens is your bandwidth goes up. Basically, this frequency gets broadened when the time gets smaller. Now, so therefore, if you look at Raman spectroscopy, the typical resolution, that the peaks that you are measuring the bandwidth, is about 10 wave numbers or 15 wave numbers. So it is easier to do a spectroscopy with 1 picosecond pulse. But when you go to pulse like 10 femtosecond, the width is so broad that multiple frequencies get buried under the system. Therefore, the question is, can we actually do Raman? So typically people will say, since Raman spectra has 5 to 20 wave number bandwidth, you can only do picosecond. Anything faster than that, you will not be able to measure the Raman scattering. So then, of course, human mind is always better. In 2005, we proposed this idea of doing stimulated Raman. And the idea here is very simple. This is your normal Raman scattering, where you actually look at the scattered light, which has a frequency different from the incoming frequency. That actually is what gives you the Raman scattering. But of course, when you do the stimulated Raman, you actually have two pulses which are interacting at the same time. The frequency difference between these two pulses is the coherence of these two, and therefore the Raman scattering is measured. So we have practically demonstrated that we can actually measure stimulated Raman scattering. Once if we know that, how do you bring in the femtosecond time resolution? So we decided to do this. So what we do is we bring a transform limited femtosecond pulse, which is about 100 femtosecond, and then we bring a picosecond pulse. Now this pulse is very broad, and this femtosecond pulse is very broad. This pulse is extremely narrow. It is possible to get a Raman scattering only when these two lights are present at exactly the same time. Otherwise, you would not get stimulated Raman scattering. Therefore, when this interacts with these two, you will actually get the scattered light. So how do we do the time resolved? So we create the excited state using this pulse, then you create this excited state, and then these two come and interact in the excited state, generate the Raman data. So what you will see here, wherever there are frequencies, those frequencies interact with this pulse. Therefore, you get the scattered light has the fresh bandwidth of narrow frequency of this picosecond pulse, but the time resolution is controlled by the femtosecond. So you can actually do a femtosecond Raman spectroscopy in real time. And so we are the third people in the world to demonstrate we can do this in 2008. And so we can now go and measure them. What is amazing about this is you can't go and buy this in the shop. You can only buy lasers. So we actually built all these systems. We buy a basic system and an amplifier, put them together. Now when you build it, what happens is you have to generate these various pulses that I showed you. Now what we are getting is a femtosecond pulse. This femtosecond pulse has to become a picosecond pulse. You are basically doing a Fourier transformation in the laboratory. You take two gratings and spread the pulse, take a narrow bandwidth that you are interested in, compress it back, what you get is a picosecond. So you start with a 100 femtosecond pulse, convert them into 1 picosecond, and then do the experiment that you are interested. And as I said, you need a broadband femtosecond pulse. We can generate a femtosecond pulse using this kind of facility, and that's what we do. So this is what students have built in the lab. Ajay and I share a lab there, so he knows very well what we are doing. So you can see here, one of them is a white light pulse, which is the broadband. The other one is this is your grating-based compression. There is one grating here, another grating here. The light goes in, gets spread, separated out, and then comes out to this grating, and that gives you the picosecond pulse, which comes here. And then we convert the other femtosecond pulse, which is the excitation. So we have 3 pulses coming at the same time on the sample to generate femtosecond data. I'm quickly going to show you one result. How fast this move here. The idea here is in liquid, the rate of transformation is 20 times of the gas phase. People would imagine in a gas phase, when you are isolated, you hit with light, they can switch much faster. But in reality, when you actually put them in liquid, it goes 20 times faster than isolated gas. So the question was, why does it happen? So we decided to look at that. And so these are all the lifetime of the state that we have created. And this is the spectra you are looking at. This is the Raman spectrum, which is called the inverse Raman spectroscopy. Basically, the anti-stroke site where you have absorption of the white light, therefore you have negative signals. So you have 0 femtosecond, 100 femtosecond, 200, 300. So we can actually measure them and then monitor and do some analysis. So if you look at the analysis of the CC double bond, you see that there's an oscillation of the integrated total area, the frequency, with respect to time, 200 femtosecond to 1.4 picoseconds. And similarly, if you look at a solvent, which is much heavier, much slower, and this is a much faster solvent, you have a different. So although the time period is 220 femtosecond between peaks, but the rate of decay are very different. This is much longer, this is much shorter. How do you understand this? So we try to do some computation and try to see how we can convert this. If you look at the dephasing time, the rate at which the oscillation is happening is about 350 femtosecond, and the period is approximately 250 picosecond. And then the frequency, when you do a Fourier transformation, it comes to about 95, 160, and 222, and same here. What are these frequencies? We can actually calculate and find out it is the torsional frequency of moving. Therefore, the solvents, when they move faster, they kick the torsional frequency. Therefore, the switching one form to the other is controlled by this. This is what is happening. This is the 90 torsional frequency. This torsion is kicked by the solvent energy, and therefore that is why. So we have studied the phase space and energy space, therefore able to explain the source of the signal. And so I'll now switch to some other examples. Go and see real life examples of what's happening. So the Raman spectroscopy now beginning to penetrate many areas. food processing, life sciences, forensic, pharmaceuticals, geology, including space exploration, something we are discussing with ISRO, and cosmetics, of course, and explosive detection. One of the questions that was asked is, can we penetrate a system in a bottle more than the first, transmission Raman spectroscopy is very well known. But can you actually penetrate something that is not transmitting, which is a translucent or opaque container? So, and in addition, that is a depth, and if you look at the technology that is available today, if you want to go deeper into a system, most of them are non-chemical, not structure-based technologies. So if the Raman spectroscopy is a chemical structure-based technology. If you can actually reach much deeper, then you can learn about what are the chemical changes that are happening even in human body. And that's where we started with. So the question is, how do we go deeper? So this is what we did. We went and looked at electrical engineering, electrical communication engineering, how they read radar signals, for example, from the sky, right? So they're all Rayleigh scattering that they are measuring, light coming back from those locations, and therefore they analyze. So we decided to do a Monte Carlo simulation. The idea is that if you look at a photon into a turbid media, you have many different kinds of photons. You have ballistic photon which goes straight to the detector. There are other diffuse photons which actually move around, and then you have snake-like photon which also moves around. So we decided maybe we should use these diffuse photons and scattering media, in the scattering media, or the snake-like photons, see whether we can measure Raman scattering instead of Rayleigh scattering, irrespective of the distances. And that's how we started doing this. The idea is very simple. The principle is very simple. You put light into a particle. It sends one Raman scattering, and then the rest of them are Rayleigh scattering, hits the next particle. Therefore, it also relates to Rayleigh scattering and Raman scattering. So by measuring all around 365 degrees, putting light in all directions, you should be able to measure the Raman scattering in the system. That's what we did, which means, how do I prove that? If I actually put light in the front here, if I have a sample in the back, if I measure the signal in the back, not in the front, I should get the signal of. That's what we did in Monte Carlo simulations. We were able to do it, and then we decided to do it in experiment. And that's what we did. So we took a tube of something like about 1 centimeter diameter here, 5 centimeter diameter here, and then we actually packed 1 millimeter diameter beam here, and then see whether the light can diffuse on all sides. So we measured on the top, and you can see the signal here very clearly is dichlorobenzene. This is ammonium nitrate. This is trans-stilbene. So by measuring at different locations, we have demonstrated Raman scattering is equivalent to Rayleigh scattering, diffuses through the system. Therefore, you can measure them on all 360 degrees. Therefore, you can penetrate any boxes, everything. And that's what we have patented, which is now converted into a technology. And then we can say that, by putting in, irrespective of what the height or the sample is, you can actually detect what is inside. And therefore, this particular example is for the airport. This is the reason why people don't allow you carry water, because hydrogen peroxide looks exactly like water. And therefore, we are now trying to help them to see, you can quickly detect this water or something else. What is the proof of the pudding finally is to take a 10 centimeter long chicken tissue. We asymmetrically drilled a hole, put a 1 centimeter diameter pellet of ammonium nitrate, and then we actually put light on both sides like a tube light, put laser light in all directions, and then measure precisely where these the fibers moving at every degrees at 100 micron interval. And then we could reproduce a signal like this. So we can actually show what is hidden where and what is the size of the material that is hidden, and it can be done instantaneously. And this is the example of how we can go into various applications. Finally, I'm going to talk about biomedical application. So we have been working on this since 2006 on biomedical applications. We have done a lot of work on basic research trying to understand drug molecule interaction, drug cell interaction, efficacy of drugs in cells. In addition to this, we have actually started working on it for various other biomedical areas. For example, in the biopsy, these are all published, so you can look at them. We have done how a normal cancer cell becomes an invasive cell. By the time we can see by looking at the cancer cell, normally what happens is the cancer cell is oblique, which changes into a spindle-like and then start traveling and becomes invasive it goes to different parts of body. So what we showed was, by looking at the changes in nucleic acids and protein dynamics, we know that probably this is going to now become a spindle-like cell. Therefore, we should immediately remove all of it before it converts to become invasive. That we have demonstrated. We have done a lot of work on body fluids, for example, blood, sputum, bacteria, antimicrobial resistance. We have demonstrated about 6 months ago, which is already published. Now we are trying to do it for clinical trials. AMR is a very important disease that all over the world people are worried about, antibiotic resistance for people. If you can identify within 6 months from the time a bacterial infection patient arrives, you can decide which antibiotic you want to administer to the patient. And also we have done, looking at blood plasma, we actually demonstrated we can identify sepsis, which is now being tried in Spersh and Manipal hospitals. And we are working on infections, which I will show you an example. And some diseases which is life dependent, for example, cardiomyopathy and any muscle related diseases cannot be studied with human samples. So you have to go to animal models where a fly, Drosophila fly, is well known to have 80% of genomes are very similar to humans, and therefore that's a good model to understand before we go into studying biomedical. So one can ask the question, in biology you have large number of chemicals being present, and how can you precisely identify what is wrong? So here I have to say, you can see that if you take a cell, the cell contains proteins, RNA, DNA, lipids, and of course there are other components inside. Now the sum of all of these is what is present here. Luckily, since 1960s and 70s, a lot of people in the world have been working on trying to understand what is the protein structure looks like, what is an RNA structure looks like, what is a response for a DNA composition. And therefore, we have some idea of the relative intensities and the frequencies. We can reasonably predict where they belong to, and therefore we can correlate them. The second thing that we can do also is pattern recognition. So for a particular disease, the set of changes that happens in these chemicals are very similar for most humans. Therefore, by looking at a specific pattern, we can actually pull back, and that's where the AI comes very useful. So we have, these two papers are very well known in the literature, well cited. We did this work in 2015, and we realized that we are actually getting into trouble even after multivariate data analysis. We were only getting 60% efficiency with respect to medical samples. So we decided then we should start looking at alternate ways. The AI came into being, and though we decided to apply that. And where is the AI useful with respect to Raman? The spectral profile gets complex, right? So when you start looking at diverse genomic differences between people and demographic differences between people, then the spectral profile can be complex for the same disease. So you need to pull out that particular frequencies and amplitudes for that. Sample variability, which is basically very similar, you can put 1 microliter, 5 microliter, you have to have a uniform measuring methodology. And this variable signals has to be then processed and data curated to go into the AI. So that complexity comes in. And of course, as I said, low signal intensity, and of course the background fluorescence interference. When you have multiple components in a body fluid, some body fluids might give signal. For example, if red blood cells get lyased in a serum or a plasma, the lyase-led signals will actually give you fluorescence background signal. So all these have to be taken care of in the normal statistics, simple machine learning, which doesn't work. Therefore, we have to go into the modern application. There are issues associated with it. There's a tendency to do a overfitting. We're looking for excitement. And of course, there's a data set bias. This is when the AI started in recognition, one of the biases that happened was that the CCTV AI could only recognize Caucasian male. When they applied in the field, they suddenly realized it started failing, and then they realized there was a bias in designing the model itself. Similarly, for example, in biomedical samples, it's easy to sit in one place and design for one particular group of people, while India is so diverse, and therefore you need to make sure that there is no biases in your model. And this is the other problem which we have already developed, but we are still in the process of trying to make sure it's accurate. The idea is that when you do a feature extraction during the AI process, this is 99% accurate. You want to know what are the reasons why this is 99% accurate. And that's called explainable AI. Now that has been very difficult. So sometimes, for example, when you go to FDA, you say this works, the first question they ask, explain why this works. And of course you can't, you can only say mathematically I can pick out the frequency and amplitude which corresponds to the disease. With 3,000 patient samples, we are able to predict it at 99%. Then simply they will say, fine, but still what are the chemical components or biochemical changes or the biological changes that lead to this result? We don't have. So we are working on trying to explain that. And of course, there is always this integration of multiple expertise into technology is always challenging. So how do we do that? So what we do is we get large number of data sets. Let's say you have 1,000 samples. So what we do, we take training 60% of the samples, and then we train the AI by putting a validation data set. They go around continuously, keep coming back, making sure the validation data set training matches, and then we leave another 20% for test data set. And that is converted into a model. So this is about one set of training. Then we do take unknowns, which is not part of our training or part of our validation, part of our test. We take unknown samples, feed them into the model we have generated by this, and then see what is the prediction output. And this doesn't come 99, you have to go back here. Therefore, it is basically, there are a number of models available. There is LeNet, ResNet, UNet, different kinds of AI models which you can try and see which one is the most suitable. And the convolutional neural network is the most popular which we are using. And without convolutional neural network, for example, separating out different components is very difficult. But here you can see with CNN, we can actually separate them out much better. So that's the model that we are using right now. Now what we have done is using CNN, we actually separate the training model. Then we go to generative AI to identify this model, incorporate in the generative AI, and then see. So one example is, for example, the COVID-19. This came up because Dr. Sarman Singh, who was the director of AIMS, while I was giving a lecture, talked to me about the problem they were facing in 2019-20. Large number of patients were coming in October, November area times. Some people had flus, but some people had COVID. Now differentiating the two was very difficult. And then the infrastructure cost, the patient interaction cost is all very high. Therefore, he wanted to know if you have two people with symptoms, can we separate them out? Is it quickly? Can we do it in 5 minutes? Is the question that he said. I said, let's try. So we collaborated with them. They sent us a sample which we developed. And therefore, the technology is to have a rapid, minimally invasive, very less sample requirement. And of course, can you deploy it immediately? So of course, we recorded, you can see that it is not straightforward by looking at the spectra to say whether it is dengue, COVID, or flu, or healthy control. And I must also tell you something very interesting as you go along. Healthy control, normally if you take good volunteers, of course it looks healthy control, but when you go to hospital, the control samples is not volunteers. They are all people who have come with some disease, and therefore you need to redo your training. So the healthy control in your prediction requires the sample comes from the patients, but not from the controller itself. So for example, these are the samples that we actually did initially: 70 flu, 65 COVID samples, and 51 control and 20 dengue. And you can see that the number of days after which the patient arrived, and therefore how we can measure. So we took all these data into consideration, and we just did a simple multivariate data analysis, and you can see we got only 55.07%. And of course, when you actually go into generative AI, you have completely different data. You can see that we can actually get 97.1%, even, for example, such a small set of 50, 60 samples. So now we are actually going into clinical trials with larger number of samples, and hopefully we will get to that point. So the idea is, you take a patient comes up, you take 3 microliters of plasma, drop it in the Raman spectrometer, and of course we write our own software for data analysis, data procuring, data queuing. Everything is done by us, so there is nothing commercial involved here. And so we can then separate them out and show whether who are all flu, who are dengue, who are COVID, and who are healthy. And this can be done in 5 minutes after the blood is taken, because everything is programmed into the system. So this is, for example, are the 2 technologies which are going at the, this is, for example, is for sepsis detection in ICU. This is now being tried at Manipal and Sparsh hospitals. This is going to be deployed at the Bangalore airport starting from 1st December or 15th of December, where this gun is used when you're carrying your backpack or checked-in luggages, they find something unusual, powders, liquids, whatever. They just take it out of your bag and use the gun to check what is inside, and the computer will tell you. The airports have something called SRIs, security restricted items. There are a large number of chemicals and other things. And so if it is one of them, which we are already in the AI, we have incorporated the AI model into this instrument, and therefore it can then come and tell you it is definitely a restricted item or suspicious to be restricted item, or green, which is pass. And of course, this kind of work doesn't come alone. I have to thank my friends. These are all friends in IASc. Kumar Somasundaram from microbiology, and Dipankar Nandi from biochemistry, Annapurni Rangarajan from MRDG, Sigdev from MBU, Naktomba is from MRDG, Deepak Saini from MRDG. Vani Santosh is a chief pathologist at Nimham Hospital, and Geeta Mukherjee is a head of cancer division in Kidwai, and Dr. Kulkarni is a general practitioner in the Ramaya Hospital. So we used to have regular meetings, so I learned a lot of biology from them. And of course, funding from industry partners. These are the students over a period of different generations that you see. They've contributed over a period of last 15, 20 years. And funding from DST, DBT, DRDO, IASc, CSIR, etc. And thank you very much. So I request Murali to
Good afternoon, and thank you very much to Professor Chandrabas and Professor Umapati for giving this opportunity, also to Indian Academy for this opportunity. So, and especially this is the 100th years of Raman, so it's a very important opportunity for us. So, what I'm going to speak to you today is about Raman theranostics. Essentially, quite a few of things are already covered by Professor Umapati about how the therapeutic application people are doing it. And also Dr. Chandrabas has given the the molecular fingerprint comes from Raman. So my life is a bit easy now to just go ahead. But I will be talking mostly about oral cancers and cervical cancers, and mostly into oral cancers because that is our serious health problem. So that's what I'm going to talk about. And also tell about how can we do an in vivo or serum based or exfoliated cell based studies, and what are the future plans. That's what going to be my talk. So when you talk about cancer management, you know that screening is very important. The best is the cervical cancers, where in Western world it has reduced a lot thanks to what you call that pap test. And other side of the story is mammography, which is a very sometimes complicated, especially Asian women it doesn't work. And also we have a lot of false reportings. Both pap test also does, and also is the mammography. When it comes to diagnosis, biopsy is a standard, but the problem with biopsies takes time, and if you do a frozen biopsy is not very good. It will give you 30 minutes information, but it's not really clear cut. And the real difficulty is the treatment. When you do the treatment modalities, you know that surgery and chemotherapy, radiotherapy and all those things, but we don't know whether the patient is responding or not responding or something like that. For example, cervical cancers, suppose you give treatment, you see the tumor is regressing, but after some time it doesn't regress further, and by then already 2-3 months are lost. These are some of the things which can we look into it. These are some of the questions which we try to ask in this. The strategy is like when any disease, especially disease like cancer, it's a long process. For example, like typical cervical cancer, a mouth cancer, it takes about 12 years like that, because it starts at different stages. So each stage they release markers. If you can pick up these markers, we can identify the disease early stages. And in biology, people they do it actually. What people do is basically omic research, whether proteomes or genomes, people are doing it actually. So my feeling is what generally we are doing is probably metabolomy. We are looking at metabolic studies, what we are doing, because it is because if you look at genes or proteins, there are quite a few. It's very difficult to look at them. Whereas when you look at metabolites, they are far few. So if you can look at metabolites, maybe life could be easier. So what is the procedure? What we generally do is you shine the light and light comes back. It may be scattering, maybe fluorescence, maybe absorption, whatever it is. And suppose you study this, it should tell you about the snapshot of this one, molecular snapshot. It tell you what's happening here. So idea is any change in the tissue architecture, morphology, biochemical composition should reflect in this. And what should tell you is basically metabolic fingerprinting or a snapshot, and should tell you about how it changes from normal to disease condition. This is the kind of philosophy which we are working on that. And as discussed nicely by Professor Mapati, the most important point of the analysis is data analysis. And we all know about univariate. Typically we know absorption versus concentrations, which people have been doing typically in the labs. But when you go to simple systems like this, when you go to large data sets like Raman or something like that, it's very difficult to identify what is what. So this is where you have to use multivariate analysis. Idea is to cut down the spectrum into components and use them, their scores. That's how the entire analysis takes place. And what we use, again, Professor Mapati was talking about it, the model building. Once you build the model, and any unknown spectra can be matched and told yes, it's matching or not matching. That's how one can do it. Either it can be a simple single model system, it can be a multi-model system. That means you build multi-model, different disease condition, disease cancer conditions, all these things. Take unknown spectra and see where it fits, whether it match with 1 or 2, 3 or what's happening. So that is one way we can work on that, and the classifications can be done. So basic methodology is simple. You take the spectra, then look for that, just to try to see a simple supervised and unsupervised classification like PCA, where you don't need to train the system. You just put a PCA scores and try to see whether they classify or don't classify. Then go for a testing and development using mostly by the supervised modes. We generally used PCLDA. PCLDA is a very lowest level of analysis because it doesn't squeeze the data, it doesn't do anything. And if it works, anything will work better than that. So that is one reason why I try to use PCLDA, because it's just PCA scores are used for this purpose. Then once you do a leave-out class validation, because whether you can do a test data or you can do a leave-out class validation just to use the same data, see whether it's working or not. Then finally is this one, validation. Validation by blinded data is the most important. And I add one more structure to it, is look for the data operator, reproducibility, operator bias. Try to change the doctor, because I have that advantage, because we get a lot of registrars, a lot of interns, so we can ask one set of doctors to record spectra sometimes, some other doctor to record spectra, because we can't touch the patient. So they come and record spectra. And also every data, whatever the data we get, we also ask multiple students to look into that, so that we know that we are not fudging the data, you are not fooling around, and whatever the data we get, they are real and it works. It's reproducible and time tested. So this is how it says, patient has come, we recorded spectrum and just analyzed it, and this is how the data is presented. So when the spectra comes, these are some of the pre-processing steps we do. Interpolation, that is fixing, because this is especially for the in vivo machine which we set it up. It records from 400 nanometers to 3500 nanometers. We use only fingerprint, so we have to interpolate. And we do first derivative generally. Now we don't do for the commercial instrument. First derivative is basically cuts it gives a baseline correction, and it's again baseline correction effects will not come. Suppose if one student is correcting one way, other student correcting other way, that doesn't reflect here, because the slow moving process, the background gets automatically 0 by the first derivative. Even though first derivative known to add noise, but it reduces the subjectivity. The whole idea is to make it more objective possible. So that's why we go for first derivative, and normalization basically to remove the intensity related problems, so that spectra basically goes by not by the intensity of the spectrum as a whole, absolute intensity, but it's a relative intensities, and not day-to-day things don't interfere with that. This is where we have to take all these precautions to it, because it's more to do with the disease diagnosis. So these are the different steps. Finally, we come to this conclusion here. Then we have our own softwares to analyze all these steps, like PCA and PCLDA. Generally, we do it. Then do the class validation and predictions, as I said already. And how we present data, either a scatter plot or a confusion matrix. Confusion matrix, diagonal elements will tell you the right predictions, and wrong predictions or false results will come in the non-diagonal elements. Ideally, non-diagonal elements should be 0. That's how the good classification, good model is working. Then there is 2 ways we do in this analysis. One is called spectra-wise, other is called patient-wise. What does it mean? Spectra-wise is what we do. Suppose when you are recording on a patient, we have both in vivo measurements and also ex vivo measurement. When I'm doing ex vivo measurements, I will go for patient-wise data. When I'm doing in vivo measurement, I go for spectra-wise analysis. Each spectral point, I give validation to it. I take it as an independent spectrum. For example, when I record spectra on a patient, 5 points I have recorded here, 5 points on the other side. Each spectra I have taken it as an individual component. The reason is, when you go for a cancer patient or something, surgical boundaries, all those things have to be identified. So that's why each spectra will be valid. But when it comes to the ex vivo samples, like blood sample or a serum sample or a cell or a saliva, see, you are just recording spectra on a 3 microliter sample, and you have a lot of spectral points to be identified. So in that case, it is better that you take spectra at several spots and average it out, so that you got one spectrum for one sample. So you have got a representative spectrum for that person. Otherwise, you might miss the biomolecule. That's the idea, what we do. So these are some of the very old data. In 2001, first time we demonstrated, yes, how normal tissue will be different from the malignant tissue in 2001, and we found that this is consistent, it works. Then we went on doing it on different conditions like pre-malignants and other things of the oral cancers. Then we went on the cervical cancers, then breast cancers, all our biopsy tissues. I'm not talking about all this data because of time. Then went for ovarian, then stomach and colon. Now this is what I want you to look at it. What is this? Now we have different models for breast, normal, malignant, cervix, normal, malignant, colon, larynx and oral. These are the different models. Now I have taken breast normal 25 spectrum, oral malignant spectrum. Now you see, normal spectrum matches only with normal. It says Y. It says with N with everything. Same with oral malignant. It says yes here. It says no with everything. So this way you get it should say yes with only one particular group and say no with every other group. That's how it works. And also we tried with, this is basically a limit test, very low level of analysis that time. We also tried with different things. For example, PCLDA, PLSDA, QDA, CART. Wherever you do, the classification efficiencies are good. In the worst experience we have with cervical malignant, there we had a little tough time. But other cancers, we got almost 90, 95 kind of classifications. So that is where we thought it's time to do something better. Because biopsy based, we are already paining the patient. What is the use of it? So we tried to see whether we can add a fiber to it and try to do a fiber based instrumentation. Fiber can be built, but it takes a lot of time. So we have to look for a in vivo Raman machine. This is a kind of machine we have to look for it. So this is the instrument we coupled, which is a 785, and it's a very simple instrument. And we have, this is the one they wanted to give it. Sorry, Bob, we didn't like it. So we got a fiber probe like this. And in fiber probe, the fiber probe problem is it gives 5 millimeter focus point. So that has to be made with a spacer like this. So this is what modification we have to do it. And the questions what we asked is these two. Oral cancer diagnosis, when the patient comes, it's very straightforward, we know it. But problem comes here. when they come with a lot of pre-malignant conditions, when it goes to a kind of a dentist, it's very difficult there. So this is the point we wanted to work on that. See, these are the small areas we don't know. These has to be identified. And the second problem with mouth cancers is what is known as field cancerization. Because most of the people, they're tobacco users. So entire mouth is already affected. So now it is affected, plaque has gone, and the first cancer has come. This has been identified. It has been removed. But this plaque can give another cancers which need to be removed later on. So around 50% of the oral cancer subjects come with a second cancer. So can we tell people that you have a second cancer possibility to them? This is the second question we asked. So this instrument is very good. It can give spectra in 8 seconds and there is no movable parts. These are some of the advantages of this instrument. And this is how patient is counseled and spectra recorded. And again, I am not going to show all the data, just tell you some of the things what we did. And for example, this is the cancer field effect where the spectra on the contralateral side can be picked up from the healthy people. That's the first step of changes that can happen that we could pick up. And this I want to show you. When we recorded spectra, we got spectra on the patient lip and tongue and buccal. Now the problem is, should we treat them as independent sites? Should we treat them as single site? That was the question we asked. When you look at from healthy to tumor, they are different here. The moment you go here, they are no more different. They are all mixed up. So that's where we thought we don't need to build a model for each subsite. One cancer subsite of oral cancer should be enough that we can work it on. So when you pull the data, these are healthy people. These are the people with contralateral abnormal, that is already patient when we cut spectra on the other side, and also tobacco user and pre-malignant conditions. You see, the crosstalk between these two groups is almost zero. Healthy person can be picked up almost 99% without any difficulty. We can pick it up. That is the present status. We also looked at, is it possible to look at surgical margins? Is it also possible to look at the, like second cancers? How we can do it? Suppose a patient comes, when we record spectra here and spectra here, do they match? That means there is a possibility of that patient can come as a second tumor. So that person has to be under watch. And also we did on cervical cancers, some of the studies here. Here the problem is in mouth we get a contralateral, but in cervix you don't get a contralateral. So we try to see, can we use a control vagina as a subject? Because when you see this spectra of both are matching, that means healthy. They are not matching, there is suspicion. So that makes life very easy. So this is what we demonstrated here. So where we can identify a control. So this is good if you go to a camp or something, you don't need to have all the difficult things. Just record 2 spectra and spectra are matching, 5 not matching, next stage. But at this stage, what we realized is getting patient and recording spectrum and all those are very difficult. So that's where we went for the serum, saliva and all those things, because they are easy to bring collect sample and work on that. So this is the serum based studies. I'll show you one data here. So at this stage, our sensitivity is around like 83%. This is whole data. Now it has improved. And also we put a pre-malignant and a disease. Disease is a brain tumor. We can identify a serum of a brain disease versus head neck disease. That we can identify. That's what we are there now. And also we can identify the prediction. I will talk about this again. This study was repeated by this girl after 7 years, and we get similar results. There is no change. We can identify, definitely. And also cells. So I will talk about one cell study here. This will be interesting. Here we have 4 groups of cells. For example, we have oral cancers, control people, tumor people, cervical cancer control people, and tumor people. Why we took this cervical cancer and oral cancer, sir? These are from the same type. They are squamous cells. Typically, by pathology or cytology, they should be similar. They can't make out differentiation. But we can classify them as a tumor, also site. So that is the advantage with Raman, because Raman gives you the molecular fingerprint, so it can be used to classify that way. So that is an advantage with there. We also did salivary Raman, because what we found is when we try to go to a patient, for example, you ask him to scrap. Some people are ready to give blood, some people are ready to get a scrap of the thing, so that you can get a, like I don't know whether I have it. You have to use a brush like this to get the scrap of the cells, and some people don't want it because it hurts them, and some people don't want a needle because they are scared of needle. So we thought, why not we go for slightly different one, saliva. Advantage of saliva is anybody can give, and it doesn't generally like blood. We don't need to worry whether that guy has any other disease, HIV or something like that. That we don't, contamination is not a problem, and you can collect it even from the child. But only problem is it's a very dynamic. For example, what you eat, it reflects. So with all these things, it's possible to develop a model, develop a method, how you collect sample and how it works. That was the question you asked. But it's a very interesting sample, this one, because by circulation it gets the biomarkers, and also because saliva is on the tumor, so it also gets markers. It's interesting. And the sample is very interesting, very doable, very poor patient compliance. Only thing what we have to notice is that dynamic stage will it hamper. So one solution what we found is, you take early morning saliva after asking to wash repeatedly 3-4 times with water, not with any other thing, just a water, then we can do it. And also we wanted to see whether it is, what is good, centrifugation is good, supernatant and the pellet is good, or just a lyophilization is good, or just air drying is good. What we found is air drying is the best one. What you do is just put one drop, wait for some time, put another drop, then because it's very, saliva is a very weak sample, we have to kind of make it better that way. So it works, and we can see, we can classify healthy and volunteer versus tumor very nicely, almost great. But where we stuck is here, tobacco. When you get a tobacco habitual, and our success rate is not great. We are about 70%, something like that, not like this. This is what we are trying to solve now. So now we are in the model we are doing now, last check of evaluation and validation, both by on human subjects, also animal models. For example, this is a study which is repeated, this study. In this study, what we said, suppose a person comes, at the time of registration you took sample, and when it's discharging you take another sample. Which sample is good for finding recurrence? Because in one case tumor is still there, in another case tumor is removed. So what we found is sample collected before surgery doesn't give any great classifications, but after surgery it gives classification. And this is same whether it is recorded by Aditi Sahu or Panchali, or different people are there, you can see. We have added Atul here. It doesn't have any operator bias and student bias. The data is same, and it is 7 years old data. That is, patient has come, is gone. We have been following them for 7 years, and this is the data, and we still get good classification. We can identify just based on sample collected 7 days after the surgery. We can tell the patient can come back or will not come back. That is our success rate so far. And now what we are doing is, as I said, we are good with healthy people, but that's not our target. Target is to identify the tobacco people, because those are the people who go to convert into tumor. It's not that healthy people, no tobacco habits, get cancers, no. Because of the tongue bite, cheek bite, all the teeth is sharper, they also get cancers, but they are few. But tobacco people get more. So now its idea is how we develop a method where we can identify a tobacco guy from the tumor, from pre-malignant. So for that, what we did, we took spectrum. This is leukoplekia, OSMF. OSMF is a very common, this one which has conversion rate high, and all these people. And we took same subject, we took serum, same subject, we took saliva. Now what we do, we record spectrum, we analyze. Now we club them together and see what happens. So data say like this. If you do that, the classifications are not great. Healthy people 85%, But the moment it goes to tobacco versus cancer, they are not good. Both saliva and serum, they are not good. But the moment you do a fusion, then it goes very good. For example, mid-level fusion, you can almost go up to 93%. That's where our classifications are improving. This is what we are trying to examine further. And another point also we are trying to see, these are basically, some people say you are measuring, comparing apple versus orange or something like that. But this nobody can question. But this animal is clean here. Around this time, it start getting tumor. Suppose now record take serum sample from blood sample from eye from the same animal. What happened to that? So you can see these are the different stages. Generally, by 10th to 11th, 12 weeks, we can see the difference actually. You can see the mild tumors coming up. But by Raman, you can see by 5th week, we see the difference actually. This is serum sample. By 5th week, we get what is the advantage is, as for some of my friend told me, each week of this one, this animal model what you used, is 1 year of human being. Suppose 14 years to get full cancer for a human being, and by 5th year, 5th week we are picking up. So 5th year we should be able to identify. That means still there are pre-malignant conditions. Probably there still can be, if they stop the tobacco habits and all, they might go back. That's the idea of this one. And also tells you that yes, it works. Serum does work. We don't need to really go for in vivo. And another point what we try to do is, suppose there is a big tumor, some can be small tumor. How does it make a difference? Does it big tumors are easy to classify? How do we do that? When you paint it, sometimes tumors come as multiple. Sometimes 2, 3, 4, sometimes only 2. So we divided 4 versus 4 below, 4 above. That 4 as a control, you put it, cut off. What we found, whatever you have, whether you have more cases or less cases, there is no difference. By 5th week, you can pick it up easily. That is the advantage. So that means whether tumor size is big or small, the moment it varies from the healthy, it can be picked up. It doesn't matter. So we did other things. I'm not talking about all these things because I already gave a brief. We also did COVID, antibiotic resistance, agriculture, reflexology, all these things. So this is one thing I want to tell you why I stopped in vivo. Because we stopped because of this problem. This is the flow it looked like. We tried to modify like this, it worked. When we try to do something different, it's not working. But we have this head, which we discarded last time. Now we want to use this with a fiber probe to work on. So the idea is to try to develop a polycrystal fiber and work on that, because polycrystal fibers don't give any Raman signatures. There is no nonlinear effects. So we should be able to get a good spectrum. Because earlier spectrum we have to cut down around 1100 wave number, because after that we get all the silica lines. So now things might improve. That's one idea. And also data transferability. For example, what I record spectra, somebody can use it. So this is one thing we are trying to do. People are doing this. They try to say that what kind of modifications one has to do here. So we are doing that. So one idea is to, like Professor Mapadi said, try to look for extract the features and try to see. What we guys are doing is we try to introduce variations by artificially and see whether we can do it. That is one thing we are doing. And also, this is the important question, identification of biomarkers. Because unless you show the molecule, people don't like it. And especially biology, I work in CRI, we are full of biology people. They always ask, what is it? Tell me the molecule. So now that also you are trying to see, both by MCR calculations or by comparing with metabolomics. These are the two ways we are trying to see whether we can do Raman spectrum and whatever the spectra we record and whatever the modifications happen, whether mass spectroscopy with metabolomics, does it support or does not support. That is one thing we are trying to do. These are some of the things. This is my group. Thank you.
I can hold it. Thank you. Good afternoon, everyone, and thank you so much. Before beginning, I would like to thank your organizers for giving me an opportunity to present my work here. This work I have done with Professor Umapati in his lab. I'll be giving a brief of some work, Raman, which has already been discussed, and especially I've worked on the protein samples, like biological samples, and there I'll be specifically talking about protein. Let's just get going. Good afternoon, everyone. So today I'll be talking about understanding protein folding using Raman spectroscopy, where I'll be giving two examples where we have taken two specific protein problems and identified something which is already known, but looking in a different way using Raman spectroscopy. Like problems are not, I'll say that new, the problem is already being tackled by various spectroscopy, fluorescence and other. But how in Raman we are trying to find out something new. So just a small introduction for everyone. Raman spectroscopy is the vibrational spectroscopy is a collective term for the Raman and infrared, where we measure the vibrational energy levels associated with the chemical bonds. And as the name suggests, it is like with the chemical bonds, it is very specific and unique and represents the fingerprint spectra of the molecules. Another advantage of this spectroscopy, if I specifically talk about Raman, this is non-destructive, non-invasive. You take anything, you shine light, you collect the Raman spectra. That is the beauty. Everything gives you, you don't need a specific probe, you don't need a label. That's a beauty also. That is sometimes a difficult point also because everything gives you a Raman. You don't know which specifically thing you are targeting. And in biology, from the past decade, I think a lot has been done and interesting problems have been understood using the Raman spectroscopy. I'll give just very small brief how in biology Raman spectroscopy is coming. You get very specific, unique Raman spectra for these bioassemblies. I'll not talk about now biomolecule. I'm talking about like assembly in the terms of not just like protein amino acids. If you put together all amino acids, you get a protein. You get very specific spectra for the protein, which is very different from the amino acids. You get very specific spectra for DNA or the lipid or all type of molecules, which are very unique to the different biomolecules. Even very small changes, like if you have a protein, it has not denatured, just a small changes there. If you can say just two domains are drifting a little bit apart, you'll see these changes you can probe in the Raman spectra. Very specific, unique signatures you can see. You can look at the hydrogen bonding, like in proteins, it's all about hydrogen bonding of the backbone, amide bond, that can be probed using Raman spectroscopy that we will see today. Apart from that, co-solvents effects, hydration layer effects. I'll talk about hydration layer as well today, where these Raman spectroscopy and one more term, Raman optical activity I'll be using, that can be used to understand these. So this is one slide to understand how Raman spectra of the different biomolecules look like. If you go from lipids, DNA, RNA, protein, there are some specific unique signatures that are different for each biomolecule. And if we completely look at a cell which is made up of all these things in different concentrations, you can identify all those spectras there. Now, coming to the structure of proteins. That's what we are talking today. The structure of proteins is in the 4 parts. Primary structure is nothing, just the linear array of the amino acids. And in a protein unfolding or denaturation, the primary structure of the protein is never changed. It is always same. Protein usually does not degrade. in the terms of their bonds breaking are not there. Secondary structure is that when these linear chain of the amino acids which have come together to form the amide bonds, they make some specific structures where the amide bond CONH back bond make different kind of hydrogen bondings to give different kind of structures. So you get beta sheets, alpha helix, turns, those kind of structures evolve. And you get very unique Raman spectra for these different kind of secondary structures. Even you have same linear structure of the amino acids. Like if you have the same primary structure, but if the same chain has folded into beta sheets or alpha helix, you will get specific, unique, different spectra for the beta sheets and alpha helices. Tertiary structure is when these secondary structure elements come together and make bonds, mostly hydrogen bonds or other bonds. Then you get tertiary structure. That is also very sensitive. You can probe in Raman spectroscopy. Quaternary structure, when you have more than one domain of protein, how these two different domains come and interact together, that is the quaternary. If you have just one domain, then your tertiary and quaternary structure are of course same only. So this is the Raman spectra of the lysozyme in water. You can see such a rich Raman like information. There are lots of peaks are there. Amide bond specifically, there are 9 normal modes for the amide bond are observed, A, B and 1 to 8, which gives a lots of information about the backbone and specifically the hydrogen bonding pattern in the spectra of the proteins. And we don't see in the conventional Raman spectra, all the bands, the amide bands are not intense. Mostly what is seen is amide 1 band and amide 3 band. Amide 1 band is a very broad, intense band which comes from 1600 to 1700. Amide 3 goes from 1200 to almost 1300. Apart from that, we get signature peaks from the various aromatic side chains like tryptophan. You can see here phenylalanine, tyrosine, tryptophan, very specific. The ratio of these peaks changes whenever there is a change in the hydration or the hydrogen bonding pattern of these bonds. Then you have disulfide bonds which are very unique in various kind of proteins. You get very nice signatures at around 550. And whenever there is a change in the dihedral angle of the SSS bond, you get changes in this region here. Then you have CC stretch also, which is very for this alpha helices, and secondary structure is different, which you get around 900 to 960. So this is a typical Raman spectrum of a protein. This is lysozyme. So in lysozyme, you have helices also, you have beta sheets as well, and you have this random structure. So you are seeing the spectra for everything. So it is not easy to completely elucidate the structure of a protein just by looking at the Raman spectra of a protein. However, if you look at some changes, the understanding the changes from the Raman spectra is easy. Just by looking at this spectra, we may not be able to tell exactly what is the status of tryptophan or how these phenylalanine or other tertiary residues are there in the Raman spectrum. But if you compare, you take the lysozyme, you hydrate it, you denature it, you can see nicely the changes, and those changes could be understood very well from the Raman spectra. This is another example how Raman spectra is important. There are 2 different proteins we have taken. One is BSA and another is lysozyme. BSA is mostly helical, 66%, with others at random structure. Lysozyme is 40% helices, sheets, and plus random structure. And you can see very clearly distinct signature changes in these 2 spectra. That's how this Raman spectra is very different for the different kind of proteins. And this thing we can use in understanding the protein folding or any other phenomena here. So this is amide 1 band that I have been talking a lot. Amide 1 band mostly comes from CO stretching, around 1600, you can say 1650. As proteins are a very complex molecules and there are various bonds, CONH, which are affected by the hydrogen bond. It is very sensitive to the hydrogen bond of the CO. That's why you get it a very broad band from 1580 to around 1720. And being broad, it can be actually deconvoluted that you can get the different secondary structures which are very unique in the protein. If you see, we have here curve fitted our secondary, this amide 1 band, and fitted here for side chains, connecting segments, helices, beta turns, random structures. All these can be fitted, and qualitatively you can exactly look at what is the content of each specific secondary structure in your protein. This is just trying to give an example how a amide 1 band can be used to analyze the structure of a protein. This is a BSA protein only, which is taken the temperature spectra of the BSA at 2 different temperatures. This is that higher 50 degree and this is 25 degrees Celsius. You can just simply by looking at the nature of the amide 1 band has completely changed. And if we curve fit, you can clearly see that these peaks are changing from one spectra to another spectra. So amide 1 band gives you a very nice information about the secondary structures, how they are changing. In the similar way, you have amide 3 band. Amide 1 band is more broad and usually curve fitted to get information about it. Amide 3 band mostly comes from CN stretching with contributions from NH bending, CC alpha stretching and CO in plane bending. This peaks comes around 1220 to 1400 and here information is usually looked at by looking at the intensity at a peak. So this is again just a small example, not going in details about this example. BSA again at 25 degrees Celsius and 65 degrees Celsius, you can again see that there are changes. Amide 3 also gives the complementary information to the amide 1 band. So it is always good to look at both the peaks to corroborate that you are getting the correct information in your example. So this was just a small introduction to tell how Raman spectra of the proteins can tell us a lot. So today I'll be discussing a problem that we have done, that is the stepwise dynamics of unfolding of BSA using Raman spectroscopy and 2D correlation. This is a very simple approach we have taken. We have taken the BSA, we have unfolded it using a chemical denaturant, guanidinium hydrochloride. It could be anything. You can unfold it with temperature, acid or anything else. We have collected the Raman spectra at the different stages and then we have applied the 2D correlation spectroscopy. 2D correlation is the analysis we have done. We have done the 2D correlation analysis on the spectras observed at different concentrations of your guanidinium hydrochloride. Let's just go to what is 2D correlation. As the name suggests, correlation is simply by looking at two variables, how they are changing. If they are changing, if there are two variables x and y, suppose some linear variables x and y are changing, the correlation coefficient in very simple terms can be calculated using this formula. Let's not go in details. So if r is equal to 0, that means there is no correlation between these two variables, they are changing independently. If r is 1, there is a if positive, then there positive correlation. If r comes negative, that means negative means one is increasing, other one is decreasing. The same thing can be applied to the spectra as well. When two peaks are changing. Now in a molecule, if two peaks are changing, one is increasing and the intensity of other peak is decreasing, it is one molecule only. These two peaks must be correlated with each other, that these two changes will not be like independent. Something is increasing, something is decreasing, that's why it's there. So we are using same information here. So this 2D correlation analysis can be applied on your spectras also, that we are applying here on the Raman spectra. So that is little more complex. Here you get such kind of, when you do analysis, you get two kind of spectra, synchronous and asynchronous spectras. That's how they look like. These are three-dimensional plots. If you look at x and y axis, both are the frequencies, and the z axis is your intensity, which goes from positive and negative direction. How we read these spectra? If we look at the synchronous spectra, in the synchronous spectra, this is the diagonal. Along the diagonal, you get red signals. These are the positive peaks. Positive peaks means these peaks are changing. That's why you are seeing positive. And whenever there is a cross peak, that means these two signals are correlated with each other. Their changes are connected with each other. If could be positive or negative anyway. This is possible here. So if there is a cross peak which is positive, means that both the frequencies are changing in the same direction. If there is a negative, both are changing in opposite direction. This is synchronous. Asynchronous spectra gives you out of phase information, which is very important. Out of phase tells you which one is changing before and which is changing after. So that to read the asynchronous spectra, you look at the both synchronous and asynchronous both graphs. So if the intensity of a particular cross peak is positive in the synchronous, negative in the asynchronous, then we will say that nu1, this is nu1 and this will be nu2. For this, if we look at this peak, this will be nu1 and the y-axis will be nu2. The nu1 frequency changes before nu2. Same will be other way around. If negative, positive, nu1 changes before nu2. If the intensity at the sign at both places is positive, positive or minus, minus, then nu1 changes after nu2. Sorry, that will be nu1 changes after nu2. So in this way, we now know about two frequencies, nu1 and nu2, which is changing first and which is changing after. So we can make a correlation. If we have suppose a lots of frequencies coming, we can draw a diagram like for different kind of frequencies to tell the order of change. So I'm not going, let's go to our results. What we did, we took the BSA protein, we denatured it using guanidinium hydrochloride. This is the BSA protein, which is mostly helical, having random structures, small segments. Why we chose BSA? It's very similar to HSA, very simple protein, mostly stable at normal conditions, easy to denature, and easy to work at room temperature conditions in the lab. What is already known so far about it? As I told you, it is not a new problem. It is already a known problem that was there. BSA has 3 domains, and it has been observed that in the beginning concentrations of the guanidinium hydrochloride, it is the first domain 3 which gets perturbed, and as we keep on increasing the concentration of the denaturant, the other domains also get starting denaturating. But what we don't know here, how it is denaturating, because we are saying in the secondary structure, you have helices, you have beta sheets, you have turns. So using the 2D correlation, we will try to understand which domain is changing before or which is changing afterwards. So this is the Raman spectra of BSA. In the Raman spectroscopy, we use very high concentrations of the BSA, like almost 10 mg per ml, which is higher than the fluorescence spectroscopy. This is one way good also to understand at how at higher concentration in the crowded environments your protein is behaving, which information we usually don't get from the fluorescence spectroscopy. What we compared here, like even if we take the higher concentrations, there are no changes in the spectra of the BSA. That means your protein is not getting aggregated even at the higher concentrations. This is the Raman spectra of the BSA after denaturation with the guanidinium hydrochloride. We went from 0 to almost 5 molar of the guanidinium hydrochloride. We analyzed specifically amide 1 band 1600 to 1700 and amide 3 band 1200 to 1300 centimeter inverse. As you can clearly see that there are changes here, but what exactly these changes are telling us? Let's go to amide 1 band, that is the CO stretching band, that is we looked here. We curve fitted for the amide 1 band and looked at the analysis. This is the at 0.25, 2 molar, 4 molar, and we plotted the area of the peak under this most intense pink peak. This is for the alpha helices. As BSA is mostly helical, that's why you have such a sharp peak. As we can clearly see, as the concentration of the guanidinium hydrochloride is increasing, the area of this peak is decreasing because your protein is getting melting, it is getting collapsed and your helices are decreasing. Okay, this is what we understood by just looking at the 1D analysis of your spectra. Same information we will get, as I said, from the amide 3 band also, that your helices are decreasing, your random structure is increasing, your beta sheets are increasing. This we already know in the literature. Now next, what else can we get from the 2D correlation analysis? So in the 2D correlation analysis, we applied at 2 stages. One is the earlier stage, which is up to the 2 molar, where only the domain 3 of the protein is unfolding, and then 2 to 4, where the other domains are also unfolding. That is like more of a global unfolding. So this is for earlier unfold. If you can see, this is the synchronous and this is the asynchronous. In the synchronous, you can see one major peak, one major diagonal peak at around 1650, which is like, that means your own, there are not much changes in other peaks. That means your changes in the first phase of your unfolding are very less. That's why other cross peaks are not coming up too much. We will have small changes from here. There is one cross peak observed here at 1655, 1635. So what we observed here, that loosening of tertiary contacts or properties with respect to your 1630, which is your helices. So this is like a beginning change. Let's go to the other changes, like the more global changes, which is the 2 molar to 6 molar, the higher changes, where we are seeing the global changes, where whole 3 domains are melting. Okay, there we have performed the 2D cost analysis, and you can see many peaks compared to what was available in the earlier. So this is the synchronous spectra and this is the asynchronous spectra. X and Y, both X's are you're representing here frequencies, and these contours are positive and negative intensities, the dark positive and negative. So if we see these contours, these off peaks which are coming in asynchronous peak, they are actually corroborating with the different secondary structures that we have deconvoluted using our band analysis as well. So then we started looking at making the analysis. We are taking two frequencies, nu1 and nu2 each time, and looking at every cross peak. So like we looked at the peak 1688, 1677. This is just one example I'm taking. 1688 is random, 1677 is term. Both here it is a positive, you can say. That means 1688 is changing before 1677. Your 1688 is random, and then your 1677 is your terms. So, and if you look at the cross peaks, this is for the synchronous, this is for asynchronous, positive, negative. We keep on like analyzing each one by one, 1688 to 1677, 1688 to 1650, 1688 to 1641. Both positive, positive, that means 88 changing before 67, 1688, 1655 like random and helices. That means 88 is changing before 1650, 88 is random, structure is again changing before helices. Then again we looked at next cross peak. So in this way, we analyzed all the cross peaks that have been observed in your asynchronous spectra of your this correlation. And the overall all global picture that we observed here is, if we see, one second. So one by one, we went for the unfolding. So in the beginning, we did the correlation with 1669 with respect to the beta sheets. Then we looked at how things are changing compared to the 1677, which is turned, how it is making pattern with respect to helices, with respect to connecting turns, with respect to side chains, how they are changing. Similarly, we went to the next with helices, 1650, with 1641, 1615, and we came overall a global unfolding pattern of these sequence we draw. And what we found out that it is the first random coil and beta sheets which are changing very first after 2 molar of guanidinium hydrochloride, and they both are changing independently, which is followed by decrease in the segment of helices, which is followed by the turns, which is followed by the tertiary contacts, and further which is followed by helices. So we have made a sequence by looking at the 2D correlation spectra of the analysis, which information actually was already there, but we did not know it. By just looking at the Raman spectra and doing the 2D correlation analysis, we could make a segment or the sequence of the image. This information we got. So this kind of simple analysis can give us a lot about the very basic idea about how proteins are unfolding. Another aspect that we have done here, we have that can be done in this. We have done this as an unfolding of BSA. Same thing can be done with refolding, and we can try to see if the same sequence is observed for the same protein for the refolding as well or not. Another problem that can be chased here is you can change your denaturant from a chemical to a temperature, and then again you can see that if your protein unfolding is taking the same path or not. So such kind of interesting problems can be found out by using this simple correlation analysis on the Raman spectra of the proteins observed here. The second problem that we have I'm discussing today is understanding the effect of ethanol on lysozyme using Raman optical activity. Now from Raman, we are going to the Raman optical activity. The simple principle of the ROA is like, as we know that chiral molecules are sensitive to the polarization of a light. If you are shining your chiral molecule with the left or right incident polarized light, in the scattered beam, you will see a difference in the spectra. The same principle we are utilizing in the ROA. Here we are shining our molecules with the incident light with the left and light polarized, and we are seeing that in the Raman spectra there are differences. And the differences are such that which you do not even see in the normal Raman spectra. This is an example I'm giving. This is the Raman spectra of the human serum albumin and human immunoglobulin. If you look at the Raman spectra of these two proteins, there are not much changes here. However, if you see the ROA spectra of these two proteins, lots of differences can be seen here. So it gives more enhanced structure information compared to your Raman spectra. We have utilized this ROA in the case of aggregation of the hen egg white lysozyme and ethanol. As Professor Chandrabhas again before told us, lysozyme is a protein which is already available within us. We are using here HEWL. HEWL is the lysozyme obtained from the hen egg. That has also almost similar structure to the lysozyme what we have in our body. And why ethanol? Because ethanol is an important part of beverages. Again, this is already a problem which is already existing. And we are looking at the interaction of ethanol up to a low concentrations of 30 to 40%, which is mostly a constituent that you find in beverages. Okay, this is the Raman spectra of the lysozyme with the different concentrations of the ethanol. And as you can see simply, this is the amide 1 band, and the peaks which are shown by star are the peaks from the ethanol. And these amide 1, amide 3 band is here, around 1200 to 1300. So there are not much changes in the Raman spectra. That means your structure is not getting changed. Your secondary structure, tertiary structure is not much getting changed if you analyze it from your Raman spectra of the proteins. This is just the amide 1 band, which is shown here again. However, when we went to the ROA spectra of the HCWL, we found that there are significant changes in the band that we can see, which are giving very nice information about the hydration of the protein. Again, we know that ethanol is known to dehydrate the proteins. The same information was observed in the ROA spectra of the HWL in water. This is the normal ROA spectra of any protein would look like. This is the ROA spectra of the lysozyme. This is the again amide 1 peak. Here peaks come in positive and negative because this is the minus you are observing. You are taking the difference of two intensities. That's why you have intensities in positive and negative. This is your amide 1 band. This is your amide 3 band. In amide 3 band, I'm showing here two peaks for 1300 and 1340, and both are showing for alpha helices. However, these peaks are different. One is for hydrated alpha helices and one is for dehydrated alpha helices. And the same information you can get in beta sheets for 1220 and 1240. So although the structure of the lysozyme has not changed up to 40% of ethanol that we did not observe in the Raman spectra, however, the hydration status has changed, which we could find in the ROA spectra of the proteins. So this is the ROA spectra of the lysozyme in the water ethanol. This is the peak that we have observed, the 1300 to 1340 ratio. And as the concentration of ethanol is increasing, your band which is corresponding to the hydrophobic helices is getting increased. That means your alcohol is mostly dehydrating your protein. However, it is not changing much of your secondary structures of the proteins up to the lower concentrations. And that's how it dehydrates. This is what we have done in this section. Thank you so much. I would like to thank, before my time is over, Professor Umapati for giving me an opportunity to speak here. My principal at college for letting me to come here. I teach at undergraduate level, so we have a lots of student load and it is difficult to leave them anytime and come here. And University of Delhi, where I'm currently working, IASc Bangalore, where I have done this work. And I also like to thank organizers, Indian Academy of Sciences, to giving me this platform to present my work. It actually motivates to work further because at undergraduate level, it's difficult to continue the research work. And thank you so much for listening to me.
So we have time for some questions. Yeah, 5 minutes question time. So mic is there. I think I can speak. Any questions? For any of the speakers? Oh, you can hear? Yeah, they can hear. They can understand. So any questions? Yeah.
To Nikki, Dr. Nikki.
Yes, sir.
This disruption of hydrogen bonding with a small amount of ethanol, because your ethanol content is very high. That's why I was wondering whether is it possible to capture or?
No, it did not denature the protein up to 40 concentration.
To
We did not see in even fluorescent studies, also not in the fluorescent studies are very sensitive. You did not see anything there. That's why we have, these are the permissible limits that you see in the beverages also, I think up to 35%. That's why it is so.
And Professor Umapati, any addition, imaging and all, anything about disruption of hydrogen bonding? Raman imaging? Not really. You can't capture.
Yeah. Imaging, is much more complex because it takes time to record, right? So 750 micron by 750 micron takes 2 hours.
Okay, because 40% I was wondering, you have so
Yeah,
much of ethanol.
35% up to I can say that we did not see much change.
40% I think kick and all comes much lower. So what is happening? Any correlation?
You did not see. No, I think I have not shown fluorescence spectra. That is also there and it is already published. As I told you, we have already looked at the same problems. So HEWL with ethanol has been published for this.
Thank you. So we work on both DNA and protein. Many times we find the spectral pattern in Raman for protein is very reproducible. Over the time you get the same spectra of the same protein. But for nucleic acid DNA or self-assembled DNA nanostructural polyhedrons, icosahedron or tetrahedrons, we don't get very reproducible results. So is there any way to do the Raman for DNA or RNA? A special way?
I am still not very clear about why you are seeing a difference. If the DNA is in one of the problems which happens is because of the charge neutrality, because DNA or RNA are negatively charged. So generally what happens is that depending on the environment in which they are there, their helicities are actually affected a little bit. They open up or their hydrogen bondings are actually a little bit affected. So that could be the reason why I'm seeing. But usually you should not have this problem because I have done quite a lot of DNA work and it has been reproducible most of the times. So one basic thing is your buffer or whatever you are using, that should be very carefully looked at while you are doing it. If you change a little bit of salt content or you change a little bit of any of the parameters in that, that will change the spectra quite drastically, both for protein as well as for the case of the nucleic acids also. So that is a general comment I made, but I need to understand what exactly is you are facing to actually give you a much better answer to that.
I will discuss later.
Yeah.
Thank you.
Yeah.
One question to Madam. You have shown many curve fittings, spectra being fitted, showed many Gaussians being fitted. So how do you fix up the width of the Gaussian and how do you make sure that your fitting is optimum? Or are you're not doing overfitting or underfitting?
Yes, that possibility is there, that overfitting and underfitting is possible for the amide 1 band. However, the fitting is correct, that positions is correct, that is clear from your 2D correlation asynchronous spectra.
That brings to my second question is, whenever you try to correlate, there has to be a certain amount of causality. In one of the figures, the last but one figure, you showed a linear correlation, right? Whereas I could fit an exponential to that. So the entire interpretation will change then. So how do you make sure that your interpretation is unique? I'm not very convinced yet.
Okay, can you state your question again, sir?
If you go to your last but two slides, where you show a linear, go back, go up. You show a linear on the left side.
This not
No. Go down.
Forward.
Forward.
So that
No,
further down. Last but two or last.
Second last slide. Can you go to the second last slide? The one with ethanol, I think.
Yeah.
Not in this?
Yeah.
Okay, sir.
Yes. I can fit this curve to an exponential.
This is just to show the trend.
No. I'm just showing that whenever you talked about correlation, but you never mentioned about the causality, except that the same molecule. Now, same molecule may have very fragments which are working very differently.
No, this is not correlation. This is not correlation.
No, but then why did you draw a straight line? Why not an exponential?
Just to give an idea to the eye that there is a trend of increasing.
No, I'm feeling uneasy because it could be an exponential, because then my interpretation changes.
We did not talk here about at all linear or exponential. This red line was put just to give a guide to the eyes that how these ratios are changing. Increasing direction or decreasing direction, that's it.
Okay. Sir, I have a question for
Yeah,
you.
yeah.
You talked about cataract and 10-second window. Can you not use some other dye to make sure that the window is larger so that patient vision is saved? Have you tried that?
I'll definitely, this is a very commonly used dye for staining epithelial cells. Yeah, so it's a dye which most of the biologists are very happy with. So they won't like to change it because they know that this is not going to affect anything else. It's just a staining dye. So they won't change it. So I can't recommend another dye. But 10-second window is not at all a problem because when I was talking to the cataract surgeon, most of them complete the whole capsulorhexis, which is the most tearing of the system. Within 5 to 6 seconds, they can do it without even hurrying up. This is a very easy thing. But the issue is that if you allow this type N blue to remain in the same concentration for a long time with the white light exposure, that is when it starts affecting the complete protein structure. And that is the reason why I said the 10-second window. So they were very happy that why maybe 98% time they are successful is because of this reason. That 2% which was failing was actually because of the difficulty in a particular system where they had to extend beyond that. Because once you actually dilute this type N blue, the effect is much, much longer. One of the simpler example for what you are suggesting I can actually tell is, instead of 5 times dilution, if they can use 10 times dilution, it will actually increase the window. That is what. Yeah, thank you. So we will stop here, and we are all available for during the lunch and other later, except Uma, who may be running away at 3 o'clock. So we are all available, so you can actually ask us questions. Yeah.
On behalf of the Academy President and the Secretariat, I would like to express our gratitude to both Professor Umapati and Professor Chandrabas, and also the speakers, Dr. Murali Krishna and Dr. Nikki, for giving a wonderful symposium, ramen treat to all of us. Now we have lunch ready, and please be back by 2:30 because we have a special public lecture by Professor Ajay Sood. 2:30, please come back here. Thank you all.
Good morning, all. I feel honored and privileged to propose a vote of thanks on this special occasion. First, I would like to thank Professor Umesh Wagmore, the President of the Indian Academy of Sciences, for giving us the opportunity to host the
Good afternoon. Welcome to the special lecture session this afternoon as a part of the annual meeting of the Indian Academy of Sciences. And it's my pleasure to introduce Professor Ajay Sood. All of us know Professor Sood very well, so I won't take long to introduce him, and it won't be possible to do it in a short time either. Professor Ajay Sood was the president of Science Technology Innovation Advisory Board. He's also the National Science Chair Professor at the Department of Physics in Indian Institute of Science, Bangalore. He's of course highly decorated, and we won't go into that aspect of Ajay Sood, but I should express from my personal interaction with him, he's a very rare experimental condensed matter physicist who has amazingly deep insights into the theory as well, and many of his works have actually led to lots of interesting stimulated lots of theories to take on challenging problems. He has made significant contributions to both hard and soft matter, and more recently active matter as well, which shows the breadth of his scientific areas of research and grasp. And particularly notable is his pioneering research in graphene and nanotechnology. Today he'll be talking to us about some of the very exciting new work he has done. The title is Overcoming an Age-Old Thermodynamic Puzzle in Micro Heat Engines. Over to you, Ajay.
Thank you very much, Professor Wagmare. It is indeed a honor and a privilege to be invited to give a talk in academy meetings. I know it's a very rare thing because after you give your first 20 minutes talk in life when you are elected, then only very rarely you get a second chance. So this is like a comet comes once in a while type of phenomena. So when Professor Wagmare asked me last year to come and give a talk in the academy, I couldn't come for various reasons. Even this July meeting also I couldn't come. So this time I did make sure that I don't let go this invitation, which might be withdrawn very soon. So I came, and it's a pleasure to be here. Now the difficult part was for me to choose a topic which would be interesting to a vast section of very intelligent people sitting in the hall. So I thought, these days after I moved to Delhi, somehow people have very good notion in their mind that science is over and I can only talk of policies, which of course is one part of my life now, which is very exciting. Lot of things are happening in the last few years in science and entire ecosystem. That is for some other occasion. But this time I thought since this academy has a very, very strong and healthy tradition of talking deep science, which can be appreciated to a vast spectrum of people in the fellowship and associates, I chose this talk which is based on the work which has been done over the last 5 years or maybe 6 years. I'll give you the one part of that or maybe two parts of that. And this talk we will look at a very well defined age old problem in heat engines, and I'll explain the problem. And for the last 200 years, since the Carnot time, it is believed that this is almost like a given truth or gospel. There is no theorem for it. So I'll tell you the problem and I'll tell you whether we can address it. So experimentally, we have now shown using micro heat engines. I have to explain what these heat engines are, and we show that it is possible to address this puzzle and try to see what lessons we can learn for macroscopic heat engines. So first let me tell you the people who are behind this work. This was the one of the thesis problems of Sudesh, who is now at University of Berkeley as a postdoc. And with Rajesh, I have years of collaboration on a variety of themes and topics. It has been a wonderful collaboration over the years and it still continues. And this work, both the problems which I'll tell you are with Rajesh, and one problem will be with Niloy, who was Rajesh's student and now a postdoc in Germany with Professor Beckinger. So let me explain the problem first, what the issue is. So we all have grown with this heat engine chapter in our thermodynamics class. Namely, if you look at the Stirling engine, which came earlier in 1816, what it says is that if you have a gas in a cylinder, so if you do isothermal expansion when the gas is at a high temperature, you get the useful work done. You can connect it to flywheel and you can get the work done. And after some time, because it's a cyclic heat engine, at this point when it has expanded enough, you cool it, and this is called isochoric cooling, keeping the volume same, and then you compress it. At this time you will not get useful work, but you have to put in some energy to again make it to like a revamping, and again isochoric heating. So this cycle is done at a certain speed, that is called the engine speed, and the cycle time is what will decide what is the speed of your engine when you will get the useful work done. In 1824, Carnot came with this engine, where this part was replaced by adiabatic expansion, adiabatic compression, and using the laws which we now know, I think it is here the gas working fluid stands for 23 molecules, and knowing the first and second law of thermodynamics, Carnot said that the maximum efficiency you can ever get is 1 minus T cold reservoir over hot reservoir. This is the maximum efficiency. But you have to remember this law, this formula applies only for a reversible heat engine, which is very, very important to realize, and you never get this in practice for the reason I'll tell you in the next slide. So what is it possible, instead of a macro heat engine, you can look at a micro heat engine or a nano heat engine with few particles? That was the question which has been asked few years back. And a bit of a history, I thought in academy meetings, it's good to look at this history. This is one example where the linear model of innovation and translation has not worked. Usually in the linear model, you have the basic science, then you do applied science, then you convert to technology and market. This is a linear model. In this case, the engine was done in 1818, before the laws of thermodynamics were put in place as we know today. So just a history, 1824, Carnot
now we call it second law of thermodynamics. In his book, he wrote this. 1860 was a formal way that this was recognized as the first and second law of thermodynamics. And this time the third law came with the Nernst theorem, you know. And 1930, more recently, the zeroth law of thermodynamics is known. So I thought this is one example where the basic understanding in its depth came few years later after the application was demonstrated. So with this history, let me say what is the concept of a nano heat engine. So idea is this was given theoretically by Schmidt and Seifert, and he proposed, this is a theoretical construct, that you can trap a colloid particle in a potential well, namely using a laser. So one particle will act like your substance instead of 10 to the power 23 molecules, and piston and cylinder will be replaced by this potential opening and closing just by changing the laser intensity, which is called an optical tweezer. This is what they showed, that it is possible to get the work done. But the biggest challenge, so here the working gas is a single colloidal particle, and piston is replaced by the confining potential. And they showed that now there is a bigger challenge. Is it just a miniaturization of a macro model? No, because here when you are working with very few particles, and in this case only one, the fluctuations in all the quantities, position, velocity, whatever entropy, whatever you want to measure will be highly fluctuating. So the variance in those quantities is comparable to the mean, which is not the case in macro system, where the averages are very well defined and variances are small. So this is a new paradigm which gave rise to this whole field of what is called stochastic thermodynamics, which I will tell you in a minute. But this was realized a few years later in Stuttgart group, where they really did that experiment and showed that with this expansion, isochoric cooling, contraction and isochoric heating, they could measure the work done using the formulation I will tell you in a minute, and they could show that it acts like a heat engine. It is a heat engine exactly like a macro, which is a surprise. One particle heat engine, it gives the same results as the macro engine, is what the conclusion of this experiment was. And they measure work done and power and efficiency. I will allude to it later. So this was the beginning of this stochastic thermodynamics experimentally demonstrated, and recently even Brownian Carnot engine has been done. The first one was the Stirling engine, and the second one is the Carnot engine, and here the reservoir is water with colloidal particles. So you trap a colloidal particle and change the temperature of water by cooling or heating using a heater, and that's how you generate a Stirling cycle or anything else you want. Now this is one slide to just show you that it is all very mathematically strong. Here you know that the work done will be changed in the potential energy of this potential well with time. That is what you need to vary as you do the isothermal expansion or isothermal compression. You can evaluate it because you know the position of the particle, you know the velocity at every instance, and you know how the potential is changing with time very precisely. And the heat also you can see from the change in potential energy with x dot, and this is again you can calculate, and using the position of the particle in the potential well. That's all the measurement you do, and then you have a cycle time which is called the I will call it the cycle time for a heat engine, and you do that, and they showed that it really follows what is known. So this is the result which I thought in a summary slide I will tell you. If you look at any of the heat engine, whether it is micro or macro, the following thing you can plot. This is the speed or the cycle time. At a large cycle time, when everything is reversible because all the processes have happened and you are doing extremely slowly, everything is reversible, you get the maximum work done and maximum efficiency. as you start decreasing time, which means very, very fast speed, then the system cannot cope with it. The supply is much less than the demand, and they all come down, and a stage comes when it is no longer a heat engine, it becomes a refrigerator. It does not do any work. So this is something well known for all the heat engines in your lives as well as the micro heat engine. Now question is, this is nice, but is it useful? Now if you know the power is what you need from a heat engine, and the power is work done divided by the time, cycle time. Now when the work done is maximum, actually the power is 0. So there is no use to humanity of this such a heat engine. So the Carnot efficiency, which is this value, is not practical. So all the heat engines which you have either in reactors or in chemical plants, everything, they will work at a optimal speed where the power will be maximum, because here it is 0, here it is 0, so in between has to be maximum. At that power you sacrifice the efficiency, and this is the power efficiency trade-off. What it means in simple words, you cannot maximize power and efficiency at the same time. Now this is a 200-year-old story, and now in this 200 years people have assumed this is not possible to break this paradigm. So this is somewhere it stands, and I have given you this value, which is called the Curzon-Albaum efficiency. At that it is 1 minus Tc over Ts square root. You can see it is different from Carnot, and this is what all practical heat engines operate as of today. Now can we overcome? Now this is true for macro as well as micro. I will not elaborate. Even in the Stuttgart experiment, it was shown that it is exactly that form. This is the work done, this is the power, and there is a maximum at an appropriate cycle time of about 7 seconds. This is something verified in Carnot engine as well as in Stirling. Now this irreversibility, which is responsible for it, why it is less than Carnot? Because the system is not, all the processes are not reversible. They are irreversible when you try to do fast. So this is something need to be looked at. Now again I am repeating the question, can we overcome the trade-off between power and efficiency? Now let us realize what is the issue here. Again I am going slow just to define the problem. Here this cycle time I am calling it tau cycle. Now if this is much larger than any relaxation time in the system where the heat is transferred, it will be quasi-static, because everything has happened over this tau cycle, and you have a reversible like condition, and you will get the Carnot efficiency at large cycle time. This is what I told you. Now if at all you want to handle this problem, you need to see at a small cycle time, which is our interest when it starts coming down, can you still make tau r small? If you can do, if I am saying, then even at a faster speed or a smaller time cycle, maybe you can overcome. That was the question. In macro engine, the isochoric time when it goes from hot to cold, it takes longer than in the other time in the isothermal. You can expect, because it has to exchange reservoirs and this thing. In thermal mesoscopic engines, which I described from the earlier experiment, both are equal. Now how do we handle it? So there have been theoretical proposals so far which have come out with very fancy proposals. For example, it says make the infinite fast processes. You don't know how, theoretically you can do, and then obviously it's obvious it can do. Then they said near critical time, something power of a critical heat engine, maybe you can address, again a theoretical concept. Infinite precision, diverging current, I will not go into it, but the last one caught our attention when we were mulling over this problem. This is a beautiful paper for an atomic system, not classical system. Theoretically they have the Hamiltonian. They want to make a heat engine for this atomic heat engine in a theoretical sense, and they have a proposal that you have a system, you have a bath. Now they of course interact, but if this interaction is independent of the system itself, system is the reservoir, please remember, then nothing will happen, you can't do anything. But they showed if you can make it, the Hamiltonian can depend on the the system Hamiltonian can be influencing the interaction. They showed in some part of your cycle you can reduce it from the value which you expect. So this is the atomic system calculation, but this is what caught our attention, Sudesh, Rajesh and myself, and we said how to do it classically. And this is the paper, for those I will not give all the details, came last year, and this year in the January it came out in print. So this is the key word, please take this word, which is what this message is. Engine reservoir interaction depending on the Hamiltonian of the engine, which means parameters of the engine, can imply that you can you can try to reduce tau r. But for our case, it means that temperature and the stiffness, which is the stiffness of this is the system parameter, this is the engine, that if they can make, right now they don't have any connection, because you cool heat or cool, and you adjust laser intensity, both are totally independent experiments. There is no linking. Question was, is it possible at all that you can bring effective temperature of the colloidal particle depend on the potential itself? Earlier, so far they have been independent. So this is the question which we posed, and this is where I will explain how we did it. So now we thought, if you simply heat and cool water with of the reservoir, it will never happen, because this is something decoupled. So we look at the another way to control the effective temperature felt by the colloidal particle. And what is the way? This is something known in the literature, that when you trap a colloidal particle in an optical tweezer, you put two plates, and these two plates like a capacitor, in which you apply a voltage which is fluctuating. It's a random thing with some statistics, and depending on the average voltage, you can show that the effective temperature will be not only the bath temperature, which can be room temperature, but it will depend on the strength of the electrical noise as well as this gamma, which is the damping constant. So this is what we thought could be a way where we can bring the coupling. So just to see what is the idea here. Idea is that in a fluctuating heat engine, which is what we are working with, it is in a fluctuation dominated regime, and the minimum time which is required for heat transfer is this damping constant gamma over K. Just remember this, gamma is the viscosity related parameter, and K is the potential stiffness. This you cannot touch. Now effective temperature, again from the fluctuation dissipation theorem you can show, it is nothing but K the mean square displacement of the colloidal particle over Boltzmann constant. Now in experiments which have been done till now, including our lab, this we never cared for it, and the K was quite large, because it's a good thing to work with a large potential, so you have less experimental problems, and you vary K between K min and K max, but still not very small, or not the range we wanted. For large K, tau r will be very small, and hence whatever you do, T effective will be constant, because it will be like a reversible system. So this is true when K is greater than K threshold, we realize that. But now we ask, if K is less than K threshold, can you now bring additional noise and dictate the process? And this is where we said we will not trust the thermal noise, because that is God given. We will work with electrophoretic noise, which means the electric field which you have applied, which moves the ions and so on, and see whether we can do it. Answer is yes, this was done making the two electrodes and trapping the colloidal particle in between that. This is the simple setup which was made by Sudhish. And what we show now, that if you look at the probability distribution of the particle displacement versus the particle displacement, without electric field, this is Gaussian, and the width of this is related to temperature, which is 297 Kelvin, no surprise. When you apply this random voltage with the Gaussian statistics, it is broadened, and this effective temperature can be as high as 1000 Kelvin, 2000 Kelvin, depending on RMS value of that AC signal. And this is something now you have a control. So you can control the temperature effectively of the colloidal particle using electrophoretic noise. And we sorry, I will not give you all the details which may not be possible in this time. There are various time scales of this problem, because when you put a colloidal particle in an electric field, ions come nearby, they form a cloud. Now when you put a AC voltage, time fluctuating, the cloud has to shift with time every time the voltage changes. So there is a time scale which is called the rearrangement time, which depends on the particle diameter and the ion concentration, and various other time scales are there. Once we know what are the time scales, we do the experiment where we apply the electric noise at 2 kilohertz, which means every 0.5 millisecond the voltage changes randomly, and that's what we do. And sampling time of for the position is 2 millisecond. So this is the very important slide to show. We apply a constant V, and we find that depending on the stiffness of the potential, which means the laser intensity, the temperature is not only what you start when the K is minimum, but it actually varies from 400 or 500 Kelvin to almost 1200 for the same V, same electric field. This, after that it saturates, and this is the region which the experiments have been done in the past. So we realize that this is the golden region where T effective and K are interlinked. So again I am repeating, engine bath interaction in this system has been achieved because they are no longer independent. And once we know that, you can make a heat engine. Just to give you the some numbers, at this is the K minimum and K maximum value experimentally measured. At this K maximum and K minimum, this is the typical relaxation time when you go from hot to cold, 270 millisecond and 99 millisecond. Just keep this in number in mind. This is what usually you will do. Now what we find at large cycle time, 50 seconds, the Stirling cycle is beautiful, no dependence. Whatever T effective you gave from 300 to 425, it's a beautiful rectangle. So you have a isothermal expansion, because this is versus K. So when the K is less, it's expansion. This is cooling, and this is the compression. So you get the useful work done in this this part of the phase space. Now once you do that, I'll give you the final result so that we don't have any suspense here. So here I am plotting the average work done. This is the average work done, averaged over 30,000 cycles. And this is done fully automatically. You have to do a lot of instrumentation to do it. Hats off to Sudhish. I don't think any other student would have succeeded. This is like 4 years of work of his life. So you can imagine the effort. The complete thing was done by him and set up by him. And at large cycle, it is exactly what thermodynamics will predict, exactly that value. But now you comes down, which is expected again from thermal heat engines. But now, moment this starts becoming comparable to these two time scales, tau low and tau high, you can see below that it actually increases. Instead of becoming 0 and negative, which is what was the case so far, actually the work done is now increasing at a very short time, even when it is 12 milliseconds. And this, I'll tell you why is this so. And efficiency also you can measure W over heat, and you can see it is coming down as expected. But in this time scale, other physics takes over, and you can see the efficiency at 12 millisecond has touched the Carnot cycle. The Carnot cycle, which can only, Carnot efficiency, which can only come at infinite time, is now being met at small time. So what you have done, and now you can plot power, because W over tau is power, and this is what the result of this experiment is. So what is happening? The power actually starts coming down as because of the thermal thing, but now it takes over and it really shoots up. It's a very large power as compared to the thermal engines, and eta also increases. So here you have the large eta and large power. So this power efficiency trade-off can be broken and is broken, experimentally shown in this heat engine, by manipulating engine bath interaction depending on the Hamiltonian or the parameters of the system. That is the point which is the outcome. I think again there are matter of detail I will not go into what is happening. So at each point we plot the Stirling cycle, nice and rectangle at 50, but afterwards it will be highly distorted, it will have no resemblance, and that is why this is extremely small work done. And what happened? Sorry. This happens, but when you come to this regime, this changes and again gives you the result. So I think at this stage the main result of this work is that there is something happening at small time. Now why is it happening? So let me just give you the end of the arguments. We measure now how much time it takes to reach the effective temperature from 300 to 425 or 450. We can measure that. There is a way to do it. I will not go into detail. This should have taken 270 milliseconds from gamma over K. Now we show with this electrophoretic noise, it only takes about 12 milliseconds, and in the heating cycle, and this again measure to give it 17 milliseconds. So within 15 milliseconds, you have achieved the change in temperature because of this electrophoretic noise. I'll give you the physical reason for it, because that will motivate me for the next part of the talk. And this is something what is responsible for breaking this power efficiency trade-off. So again, I have done at K maximum, same thing, and the other isothermal part is not affected. So isochoric relaxation time has been reduced from almost 100, 200 millisecond to 12 millisecond. That is the moral of the last measurement I showed you. And now why is it there? Okay, so let me give you a physical picture. This is something we constructed to see if it is correct. So what is happening? We apply a DC field or AC field, but this is changing after 0.5 millisecond. But for 0.5 millisecond, there is a definitive directionality. So the colloidal particle is not moving randomly in the potential well, but it has a directed motion, right? So this directed motion helps to achieve equilibrium instead of randomly moving in the well and then coming to the equilibrium. So the here the summary is that the ballistic time of the driving force, which is the electrophoretic noise, is really helping to reach equilibrium much faster than the thermal equilibrium which is expected. So this something we thought is very exciting. Can we find some use for it? Supposing. So there my next story will come. So this is the summary. I will just leave it at this before I tell you the second part. Maximum efficiency can be reached in finite time for irreversible engines by tailoring engine bath coupling, and the power efficiency trade-off can be overcome for mesoscopic engines. Now the question everyone is asking, including us, how can you translate to macroscopic heat engine in our daily life? Very, very billion-dollar question. I don't think we have a clear answer, but we are thinking of some possibilities where some additional tweaking can help to have a faster equilibration, not only the thermal part. So this is the something which I'll leave it here. Now this second part is built in a way from the previous one. We need some other forces to reach faster equilibrium at shorter cycle time, right? So this question now is asked, what happens when the reservoir is viscoelastic? So far we have water, colloidal particles are embedded, floating in water. Instead of water, which is a viscous medium, now it is a viscoelastic medium, which means it has a elastic part like a solid, it has a viscous part like a liquid. And this is the work which appeared sometime last year, done by Niloy, Rajesh student and Rajesh and myself. So what are we asking here? So here again I think it's a 5-second introduction to viscoelastic part. All your liquids in life are mostly viscoelastic, whether you take shampoo, whether you take cream, whether you take soya sauce, tomato ketchup, all are viscoelastic. What it means is, depending on the frequency with which you shear this liquid, whether you do fast shampoo or a slow rubbing, the properties will change. And that is what is meant by viscoelastic, which means at high frequency it acts like a solid, low frequency it acts like a liquid. And this is well known, it's called viscoelastic part, viscoelasticity, and it has the storage modulus, which is like the connected to elasticity, and the loss modulus. Now we put this medium in our experiments, which is a gel, which I will not go into detail, and you can measure real and imaginary part of the modulus, and the crossover tells you whether in this part it is more like a liquid, imaginary part is high, in this part elastic part is high. So this is the crossover where liquid like behavior is changing to solid like behavior. And we will see when the cycle time of the engine varies this and comes close to this, when it is started becoming a solid, behaving like a solid, can anything happen? This was an open question and that is what we addressed. Let me tell you the result. So how do we do it? This itself is beautiful experiment. 5 minutes to shut up. Okay. Right. No, 5 minutes. I'll finish. Now you cannot change the temperature with the heater, because if the gel temperature changes, it no longer remains viscoelastic. If you heat the shampoo, it will not be a shampoo. So you cannot heat, and electrophoretically also there is a problem, because this gel polymers are charged. So you will have interaction. So here Rajesh and his students came up with a beautiful experiment which builds up on something which was done indirectly by another group. But this is the way it has never been done. What they did, they trapped the colloidal particle like before, but now they put second laser through the same microscope objective, and that laser can really focus not only at the center of the colloidal particle which is trapped, but this red laser actually is fluctuating along this path. So you can make a program where the beam can move at whatever statistics you want. So I call it a photon phantom, because once you do with some statistics, it actually changes the effective temperature of the colloidal particle. So here let me show you the result. You can show theoretically that is the case, and you can see that with this delta A statistics, means where the second small laser is changing randomly with a Gaussian distribution, you can show that the probability distribution is Gaussian, and the effective temperature can be as high as you want depending on the laser intensity. And here with a less than a milliwatt, it can be almost like 1200 Kelvin, right from 300. And when you switch off that red laser, that small laser, it will come to the as usual, the bath temperature. So you have a handle. The reservoir is never heated. Please remember, it is the effective temperature, like in the electrophoretic case, seen by the particle, and that is the beauty of this experiment. And there we show that it is like a probability spectral density is Lorentzian as expected, and all that I will not go into. But the beauty is now you can play with the statistics of that fluctuating position of the small laser. You can show that you can make the distribution highly non-Gaussian. Once you do that from this, you can show that you can get almost any reservoir statistics. You ask for it and we'll give you. So now you have a beautiful control on reservoir statistics. We did that when we started our life in 2016 with Sudesh using bacterial heat engine, where the bacteria motion was changing the reservoir statistics. But this is much simpler and highly controlled. Once we did that, let me go to the final part. You can make distribute highly non-Gaussian, like the red one. Beautiful physics can come out, which we did in this paper, which I will not discuss, where the reservoir engineering allows you to put in place any heat engine idea into experiment. Now what we did in this part. So let me come back to it. In this viscoelastic medium, what we have done is we are varying the tau, which is varying from here to here, which means it is very close to the being a solid. Once we do that, let me give you the final result. Nothing happens when it is water. This is the result. I think I have to complete in 1 minute. What is the result? The average work done versus cycle time, you can see that it is almost constant as theoretically predicted. If it was viscoelastic, this is the result, but if it is only viscous, like water with glycerol, I did not discuss that, and that is a normal thing, it decreasing. So same system, same laser, same effective temperature, you can now play with it, and this work done you can translate to now power and efficiency. And let me give you the final result. This is the final result. This is the efficiency, work done by heat. You can see that it is not coming down, it is as high as the theoretical value, what you expect in the infinite cycle time. And you can see that the power is this maximum, and this is the efficiency. So again, at small cycle time, when this should have become 0, it is again both are extremely high. Question is, what is the reason? The reason is exactly what I told you. Again, this interaction. How do we prove it? What is happening is that the elasticity of the medium does not allow irreversibility. So the particle which has been moving this thing, if it is very close to being a solid, it is again pulled back like a spring. And we showed that experimentally that is the case. And that is again the similar physics of this large ballistic time, which is really playing the trick here. So let me close this meeting, this talk, just to summarize. This mesoscopic heat engines, of course, beautiful playground, and this allowed us to show that you can overcome this power efficiency trade-off, can get some lessons learned. Reservoir engineering we showed, and one example of elasticity playing a role. And now what is the next thing? Useful work from these engines. Can you connect a cargo like in a motor in biological sense and move it? And this is the experiments which are going on to address that. So I think with this, this is what the summary is, and I will not I will just close to say that once again, thanks to this brilliant collaboration, that I could give you the talk. Thank you very much.
Thank you, Ajay. A very interesting work and the talk. We have time for a few questions.
First of all, excellent introduction to non-experts. I have a question that in case, another example where noise helps, reminds me, in stochastic resonance, I mean, if
Correct.
you add noise, signal to noise.
This is
ratio,
another example.
This is another example, like noise helps rather than.
Noise is actually controlling the energy, engine bath interaction. That's exactly what.
Okay.
Yeah. It's another example. Sushant.
Very beautiful talk, Ajay. So I just want to see whether my understanding of your statement of the effective temperature, depending not just on the reservoir temperature, but also on the system parameters, agrees with my understanding. So what we're dealing with is an open system where you have a system with parameters, as you said, and then a reservoir and a coupling between the two. Usually, one assumes that this coupling is weak so that your Gibbs measure is kind of separable between the system and the reservoir,
Correct.
and therefore the system eventually
Correct.
acquires the temperature of the reservoir. However, if you can manipulate the reservoir the way you were saying, then what will happen is, and the coupling becomes in a way strong, then this decoupling of the density
Does not
matrix does not work. So,
That's correct.
and then the effective temperature will actually depend also on the system
Precisely.
parameters. And
This is, you have summed it very well.
And the last bit of is ingenious, I think, on your part and your collaborators to make the reservoir a kind of a Maxwellian
Damon.
viscoelastic system where you have partly elastic, partly viscous, depending on the frequency and time scales.
Yeah.
So
this viscoelastic part actually is not only a theoretical interest or something, because in biological sense, when the motors are there, you will know much more than me, they are in a viscoelastic medium. They are not in a viscous medium. So that is how this motivation also came. So we feel that this, see, the internal time scale of the reservoir itself is an important parameter when you are working with this other time scale. That's the precise.
We have one
Yeah,
last question.
one question. Very nice talk. This electrophoretic noise, you have basically that is corresponding to Debye ionic screening length, because double layers are from the metal side of electrode plus phoretic.
Absolutely.
So when you put a noise, it is you are fluctuating the double layer size actually. So
Absolutely.
that
No,
is
actually
something
not
that-
only fluctuating, it also moves, because when come positive, negative, negative, positive, it moves, and that is the relaxation time tau s I called.
That's electric double layer usually relaxes faster than millisecond time. So time you are looking, that is very long time. It's in equilibrium. That's why you are getting that time scale.
Absolutely.
So if one plays with the ion size and the
So
ion
we
charges,
played with it. A good question. We played with it. That can you really play with this concept? So what we did, instead of 5 micron particle, we took 2 micron particle, where the this relaxation time is slower because it's a small distance, and this effect becomes less. And now we put lot of salt. When you put lot of salt, things are screened electrostatically, and this relaxation time becomes very small. So then you can never get this result. So we showed that T effective K relationship, which I plotted, is negligible when you have lot of salt in the system and when the particles are very small, for the same reason.
one thing you have to correct, there is under screening phenomena when you put lot of salt.
I know. Today, actually, I learned, but
So
this is not
that
in
causes again increase of
Yeah,
this
yeah.
device
Yeah.
screening.
We are
level.
not in that regime.
Okay.
So
All right. I
you
think thank you, Ajay, for a very nice talk and work, which stimulated lots of good interactions. But we have to stop now. Please stay on the stage because we have one more request for you
Yes,
for
yes,
a book
yes.
release, and I hand over to Rinne.
Thank you.
Me. This is yours, but this you can remove. It's mine.
It's our very pleasant duty to, now that we have Ajay sort of captive for a few hours, we thought we'd also get him to release a book that has been jointly published by the Indian Academy of Sciences. And this is a book on the trees of Bangalore, written by Professor Shankar Rao, whom I'd request to come onto the stage, please. And Professor Shankar Rao is from the Indian Institute of Science in Bangalore, retired from the Department of Biochemistry. But as you know, a scientist, particularly like him, never retires. And I think he went back to his love of botany. And with that love of botany, he has produced several books on the flora of Bangalore. We are releasing a book today. He's done an online flora of the South India, right? A flora of the entire country, which is online on the Center for Ecological Sciences website. So today we thought that we would have the book that has been published, released, and Dr. Shankar Rao has been very ably aided in this by two students, Aditi and Pradiksha. So I request them also to please come up. And I'll hand it over to Dr. Shankar Rao, who will say a little bit about the book. Are you okay with that? Or you want to
No,
stand?
it's all right. It's all. I wanted to make it. Despite its garden city tag, Bangalore surprisingly lacks a comprehensive knowledge of its trees that would become necessary at some point of time for management, public education, and environmental advocacy. And hence this book, The Trees of Bangalore, the biggest ever mapping or inventory of tree diversity in the city, featuring every species in vibrant color photography to assist instant recognition of the species. More than 800 species are profiled in 1,100 pages across 2 volumes, something that started as a hobby, then it became a passion, and then later on it became a compulsion. And I brought out this. The book, therefore, introduces you to every tree you're likely to come across in the city and its surroundings, and forms an admirable baseline of information on the fascinating tree flora of Bangalore. A must read for everyone passionate about trees, sustainability, and urban ecology. The book also is a tribute to the main architect of the green infrastructure of Bangalore, a German horticulturist, Mr. Gustav Hermann Krumbegel. Furthermore, the book explores various facets of urban greening and ecology through a series of articles catering to both amateurs and professionals. This is a work of this nature, magnitude, cannot be put together without generous help by many people. I have a very efficient and devoted team of people. I'll just read out the names, that's all. Abhishek, Pratiksha is here, Aditi, Dr. Sringeshwara, Professor Niranjan Joshi from the Center for Ecological Sciences, then Dr. Sujata Mohan Kumar, Vaishali Kulkarni, and Raman Arunachalam in particular. I thank Indian Academy of Sciences publisher for facilitating publication of this book, and Center for Ecological Sciences for their moral support, and Pragati Offset Printers from Hyderabad for bringing out an excellent reproduction of the book. My books are all released by great scientists. One book by Dr. Abdul Kalam, second book by Professor C.N.R. Rao. Now I have a great privilege of having this released by another great scientist, Professor Ajay Kumar Sood. And that is it.
Congratulations.
post retirement. I had nothing else to
Yeah,
do, so
no,
I had.
so-
Yes. You have two volumes. We can get through. Mr. Shankara, you please come. And two of you, please. Please. Go on that side.
There is Umesh. Umesh, come. Come.
Yes, I will. Shankar Rao, you.
Should we
Just
take it out?
hold. Yes, yes, you can. You have two volumes. Two volumes are there. So just hold it. That's okay.
That. Umesh. Yes. Congratulations.
Oh, thank you so much for her. Well, you can have a copy of the show. We will see. We will see. Yes, we will.
Thank you very much.
We will. And we wanted you to hand over the volumes
They were so particular
to
that
them.
they received the
Can we
book
have
from
a
you.
picture, the photographer, please?
Sorry, I want.
Is the photographer here? Please, just give one these volumes. Come.
Yeah.
You take
They come,
and give
they come all the way to receive it from Professor.
and the other two, where's the other two?
So they need one more set.
We need
for
one
for
more
a
set to
second.
give.
Yeah.
Give me a set. And again,
This is okay, sir? Yeah. Yeah. One that doesn't spray. It's like
Okay, thank you so much.
Can you,
Arjun.
I'll fit in my office.
that's a great privilege of mine, sir.
Yes.
The book is going to your office.
A lot of people come, so I can.
Yeah.
Thank you.
Yes, thank you very much for this lovely ceremony. And now I hand it over to Vijay, who will take us through. Vijay?
Good afternoon. After this special lecture, we go ahead with our normal programs where fellows and associates will give talks. So for this session, may I invite Professor Shivaram from IISER Pune, whose name is synonymous with polymer science and technology, to chair this session. We have two lectures, and I request Professor Shivaram to introduce the speaker, and we'll go ahead with the program.
Good afternoon, and thank you, Vijay, and the Academy for giving me this honor to chair this session. We are perfectly on time, so I hope that we will conclude this session also on time. No, I don't need a mic. 17 minutes. Can you get a so we seem to be on time, and we'll try to conclude this on time. So I think the bio of the speakers are already printed, so I'm not going to read them out. So the first lecture is by Anantavaradhanan of IIT Mumbai on distinguished representations.
Already I have given to Ms. Rajita. Second. It's not connected. Okay. Okay. Oh, that's forward. Okay, it's other way. Fine. Okay. Okay. I hope all of you can hear me. So let me start by thanking the Academy and the Program Committee for giving me the opportunity to speak here. So I'm a mathematician at IIT Bombay, and the title of my talk is Distinguished Representations. What I plan to do is, so these are the central objects. So this broadly belong to group theory, representation theory, and particular representation theory with applications to number theory. So these are the central objects in the so-called relative Lagrange program in number theory. So I will not get into technical details in this kind of a talk, but I will try to give a flavor of some aspects of the subject without getting into technical details, as I said. In the first part of the talk, I will introduce the broad area that I belong to. So I do work in a narrow area of this broad area. So I'll try to give a flavor of this talk via the pictures of a few mathematicians. I'll have only photos and then I'll say a few words. And in the second part, I will introduce one particular mathematical object. After all, it's a maths talk, something I should say about maths. One particular mathematical object which all of you can easily follow. This was studied 200 years ago. So this is one thing in common between the last talk and this talk. 200, there was a trade-off, power efficiency trade-off, and this was also 200 years ago. And narrate a story, this also via two pictures. At the very end, I'll state a few results in which I am involved without getting into all the details. Photos are all from the internet, mostly from the Wikipedia. So let me start with these two mathematicians. Of course, Srinivasa Ramanujan, everyone, anywhere you go, all of you know about him. And so that's Srinivasa Ramanujan on the right. And Harish Chandra, in this audience, maybe everybody knows, but maybe not as famous as Ramanujan in India, but a very famous Indian mathematician. By the way, last year was the 100th anniversary of Harish Chandra, which was celebrated at the Harish Chandra Research Institute in Allahabad. It was a major international conference there. So there are many things associated to these two famous mathematicians, but let me give one particular thing which is associated to Srinivasa Ramanujan as what are called modular forms. Let me not define, but just the word modular forms. And Harish Chandra, the main thing that gets associated with his name is representation theory of groups, group representations. Now comes, so I use this word relative Langlands program, and this comes from Langlands program, and that is associated to Robert Langlands, born in 1936, a very famous mathematician. That is what is called the Langlands philosophy and Langlands program, which unifies a whole lot of sub-areas of mathematics. In particular, it connects group representations associated to Harish Chandra and modular forms associated to number theory, to Ramanujan with number theory, and this was in the 1960s when Langlands had this visionary conjectures about unifying various areas of mathematics. So roughly mid 1960s. That's when it started, and today it is one of the most influential themes in mathematics, and also, since I have not written down, but in parts of physics also. But since I don't know much about it, I have not put it here. So now let me come to the relative Langlands program. So recall that it involves, one aspect of it involves studying representations of groups. So let's say, put a notation G for a group, and a relative variant of the Langlands program is a so-called relative Langlands program, where I belong to. And what you need to remember is, earlier in the Langlands program, analysis is carried out on one particular group G, or one particular group meaning there is a group G on which it is carried on. So these are specific groups coming in mathematics. And in the relative version, it is what is given to you is not just one group G, but a pair, a group G together with a subgroup H, and the analysis that is carried out is on this quotient space G mod H, which need not be a group, but on that space is where all the analysis is carried out. So relative Langlands program takes looking at one group and its representations to a group with a given subgroup and the quotient G mod H, and which representations of G may contribute to doing various kinds of analysis, Fourier analysis, harmonic analysis on this space G mod H. And the title, the distinguished representations in the title are precisely those representations of the big group G which contribute to this analysis on these quotient things. So that's a very vague introduction to the title. The origins of the relative Langlands program can be traced back to the mid-80s. The Langlands program itself was mid-60s, and this could be mid-80s. But the word is very new. In fact, this coinage of relative Langlands program may be 10 years, maximum 15 years. But it was there. Its essence goes back to, though the terminology is much newer, the main contribution started in mid-80s. And it has acquired even more vigor and verve in more recent years, and in particular this nomenclature of relative Langlands program, thanks mainly to, there are a number of works, I will just highlight two of those, again with a few pictures. So this is the famous asterisk series of the French Mathematics Society, very distinguished monographs they publish. And these are two volumes which put relative Langlands program, in the limelight. One is volume 346 in 2012, the other is 396 in 2017. The first one is on the conjectures of Gross and Prasad. So that is Gahn, Gross, Prasad. So there are these Gahn, Gross, Prasad conjectures, and it's a lot of it was solved by Walsperger and Mogla, and all this together was this volume. And the other one in 2017 is by Yannis Sakellarides and Akshay Venkatesh. So these two major works, kind of recent works, have made a relative Langlands program even more a central subject. These are the volumes, and these are the people involved in those two monographs. This is Vitek Gan, who is in Singapore in US. This is Dick Gross, who used to be at Harvard, now at San Diego. And Deependra Prasad is from my department, IIT Bombay, who used to be at TIFR and before that at the Harish Chandra Institute. And this is Walsperger, and this is Mogla. So the Gan-Gross-Prasad conjectures, a lot of it was settled by Mogla and Walsperger. And this is the other volume that I mentioned, Akshay Venkatesh, by the way, a Fields medalist, and Yannis Sakalaridis. Okay, so that was a quick introduction in terms of some photos and pictures, and the word is Relative Landlands Program, and Distinguished Representations, which is my title, are the key players in the Relative Landlands Program. Part 2 of my talk, here I will narrate this 200-year-old story, and then I'll quickly come to some of my results towards the end of the talk. How much time I may have? 7 minutes, that's good, yeah. So part 2 of the talk and the story promise from 200 years ago. This starts with Carl Gauss, one of the greatest mathematicians ever lived. And the story is as follows. So let me just put something very quickly. All of us know what a prime number is. Fix one prime number and consider clock arithmetic, modulo arithmetic. Do addition and multiplication modulo p. So just take the remainder after dividing by p. So let me use the notation z mod pz for 0, 1 up to p minus 1, p many of these numbers, and I'm going to add them and take the remainder after dividing by p. Modulo p, I'm going to add them, and then that's a group, that's an additive group. There's a group with respect to addition modulo p, and let me take the non-zero numbers, and they form a group under multiplication modulo p. So these are two basic groups. One is with respect to addition, the other is with respect to multiplication. These are two very different structures, right? Addition and multiplication are completely different structures, and you can mix them up. What do you mean by mixing up addition and multiplication? We do it as follows. So take a homomorphism is just a map which actually preserves the structure. So this is an additive structure. This is just complex numbers non-zero with multiplication. So that's a multiplicative structure. So this is a homomorphism, which just means if you take any, let me not get into that. Many of you know, otherwise it doesn't matter. It's just a story. So take homomorphisms of the additive group and the multiplicative group and mix these by considering this particular sum. So chi is multiplicative. The first one is multiplicative and the second one is additive, and you take both and put them together and sum it up. So you are mixing both these structures in some sense, and this is what is called the Gauss sum. So Gauss studied this for the first time, and he had a lot of curiosity around this particular object, and it's not such an easy object because you are mixing two very different structures. So it should not, I mean, one will assume that it's not such an easy object, and it is not. But what is not very difficult to show is that you can evaluate this up to, so when chi is a quadratic character, meaning order 2 character, then one can evaluate that after normalizing, this Gauss sum is, so the prime number, almost all the primes are odd numbers, and it could be 1 mod 4 or 3 mod 4, and this normalized Gauss sum is either plus or minus 1 depending on the parity of p, or plus or minus I is square root of minus 1. This is not very difficult. This can be there in any textbook. The question that bothered Gauss was, can you figure out the sign? Why plus or minus ambiguity? Can you fix the sign? Can you say it is plus 1 or minus 1 depending on something? And this was a question which was of great interest to Gauss, and let me go through it quickly. So it's a theorem of Gauss published in 1811 that you can actually fix a sign, that minus sign does not come. It is plus 1 and it is plus I. And Gauss did say that at length we achieved a demonstration of the very elegant theorem mentioned before in 1801. Gauss thought about this. 1805 he could do it after taking 4 years, and he finally published it only in 1811. So this is what is called the sign of the quadratic Gauss sum, and here is one more slide. Just this is from this particular book, this quotation. He said that it was not until 4 years later that he found a proof. On August 30th, 1805, Gauss recorded in his diary that a proof of the very elegant theorem mentioned in 1801 had finally been achieved. And then he wrote to one of his friends that seldom had a week passed for 4 years that he had not tried in vain to prove his conjecture. And finally, he said, as lightning strikes, was the puzzle solved. So it was one of his favorite results. Now I'll say a few words about my own work. I just said this Gaussum just to have this introduction that a lot of my work which belongs to this relative Lagrange program is in the spirit of fixing the sign. So there are objects. So basically put oneself in a situation where there are arithmetic quantities. Figuring out up to a sign is not all that difficult, just in the case of Gaussum, but fixing the precise sign requires a lot of work, lot of technology. So some of my results can easily be phrased in this paradigm, and the problem where we fix the sign of certain Gauss-like sums, so they are analog. I mean, Gauss sum is one of the most basic cases of these kind of arithmetic constants that come in number theory. So the problems where we fix a sign of certain Gauss-like sums involve distinguished representations of the title. They come in the relative Lagrange program. So here is, I will not say much more, but I don't know where the point is, but anyway, it doesn't matter. So for example, this was a conjecture from 2008. These things are Gauss-like sums, and again, it was not difficult to show that it's plus or minus 1. That follows from the basic theory. And then one conjectured that it is in fact plus 1, just like the Gauss sum sign was fixed. And this conjecture was proved, so this was in 2008, this was proved by Nadir Matranj and Omer Roffin. In, I think this paper was 2017, a few years later. So it is indeed true. And these representations are, whatever distinguished means, these were distinguished, and that's when one is able to fix a sign. Here is another instance. This is another Gauss-like sum. This particular, this thing is slightly different from the other one. And here also in the same 2008 paper, I predicted that it should be again, sign should be fixable. And this took much more time. And in fact, this is quite recent. It got published in 2021. And this required a lot of collaboration. So this is with Rob Korinchuk, Nadir Matranj, Wanson Sechet, and Sean Stevens. So here also plus or minus 1 is easy. Easy meaning not very difficult, but fixing it is plus 1, it takes a lot of work. In fact, it takes very recent developments in representation theory in order to fix this problem. Maybe I'm almost, time is running out, so I will only splash the last thing. So this was just the definition of distinction in the context of finite groups. But now that the time is not there, I will skip this slide. And they were again, some other contexts where this sign having a meaning in some more contexts. And here all that I wanted to say was a result of Deependra Prasad from 1996. So again, this one is plus or minus 1 is easy, and plus 1 had a meaning, minus 1 had a different meaning. And I will just stop by saying one of my works from this year, 2024, generalizes that observation. And here also this epsilon being plus or minus 1 is not difficult, and we give a precise meaning to what is plus 1 and what is minus 1 in terms of distinction with respect to some of the groups involved, some of the subgroups involved. I think I hope I stayed in time, and thank you very much. Okay, thank you so much. Yeah.
I had a question. Is there any physical reasoning for why is it easy to come up with the magnitude, but more difficult to come up with the sign? Any physical or simple explanation for this
So
difficulty?
physics I will stay away, but maybe there is. But mathematically it is true, because what these constants do is, what is called, so there is always some other object in the background. For example, something like Riemann zeta function, something what is called L function in the background, which are more relevant for number theory and in physics. And these have, a certain symmetry, again a word used by physicists, and appropriately normalized, it is taking s to 1 minus s, and therefore, having this line at half, real part of s equal to half as the center of symmetry. And a functional equation typically is L1 minus S as this particular constant times Ls. So this captures the symmetry, and then one can just play around with, a functional equation you apply twice, and you will get something equal to something with this square coming in. So square is one is easy from the symmetry of the thing. So I think this is, that's not very difficult. So, but then fixing that thing is not easy at all, and fixing that thing has applications. For example, if you have something equal to minus of something, then that something is zero, right? Obviously. And typically these L functions having zeros are related to points on elliptic curves and, all kinds of applications in algebraic geometry and various other places. Thank you. Yeah. Yes, because these things come in representation theory, and in some sense, representations are collectively studying a lot of transformations together. So a representation is infinitely many transformations put together. So that is there at the very beginning itself. Yeah.
Thank you,
Thank you.
Professor Ananda Varadharan. I think you made a very difficult topic simple with some stories, which I think is much appreciated. Thank you very much. Can I have the next speaker, Dr. Anup Krishnan? He's been selected as associate of IASc this year, and he will talk to us on artificial intelligence for end-to-end materials modeling and discovery.
Thank you. Great. It is indeed a pleasure and honor to be here, and thanks a lot for this invitation where I can present my talk on artificial intelligence and machine learning for end-to-end materials modeling and discovery. I'm Anup Krishnan from the Department of Civil Engineering and from the School of Artificial Intelligence at IIT Delhi. I'm currently a Humboldt Fellow at Friedrich Schiller University at Jena. So as we know, materials form the backbone of the society. Right? The civilizations are named after materials. We have Stone Age, Iron Age, Bronze Age, etc. But if you really think of it from an industrial perspective, the design of a new material is not economical at all. It takes from the conception to actual development of the material somewhere between 20 to 30 years, right? And that's very optimistic. So the question that we're trying to ask is, can we really accelerate this process in a scientific fashion? And why is this important? Because if you look at it from a United Nations Sustainable Development Goals, at least 10 of the 17 goals can be accelerated or addressed by key, discovery of novel materials. Right? So, and these areas include energy, infrastructure, healthcare, CO2 emission, etc. And in this talk, I'm primarily going to focus on this region, right? When a material is very simple, material complexity is very low, then with some time, we can actually develop this material. But when the material complexity is high, you can still develop it, but it will take significantly more time. But can we get to this region where we can actually have very complex materials discovered or developed fast, and that too not from a black box perspective, while also understanding the underlying mechanisms of how these materials behave. So in order to discuss that, this is primarily the three key areas that I'm going to focus on, which is what our lab has been working on in the last 7 years. So let's say as a user, I come and then say, okay, I'm using PFAS for the development of my materials, or I am a doctor using particular materials, but I want a replacement for a new material. How can I come with this? Right? So that's a user query. So we are trying to think of an end-to-end pipeline that can address this user query. How do you do that? The first one is that you need to go into the literature and understand what's been done thus far in this area, right? It's basically scientifically you have to go through literature. So we can read at max maybe 100 papers. But if you have millions of papers, just to give you the magnitude, thus far cross-reference has 136 million papers in its database, right? And it's humanly impossible. If you even take the smaller area of materials, there are 36 million papers published thus far in materials. So it's humanly impossible for us to really go through any of this or a fraction of this. So how to extract this information, and from this information filter it down and come up with candidate materials. That's the first part, which is scientific natural language processing. Now let's say I have a few candidate materials, great. But how do I know if these candidate materials are meaningful or not? And that's where simulations can come handy. You can have in silico models. It could be atomistic models. It could be quantum simulations like density functional theory, or it could be finite element simulations at a much coarser scale. But this in silico simulations can give me an idea about whether these candidate materials are truly useful or not. And then the final one is actually experimenting it, wherein you actually make the material and then characterize the material and then see if it's feasible or not. And maybe it is feasible, maybe it's not. And in that, if it's not feasible, then you again go through this loop by adding this new data points that you have received into your literature, right? So these are the three broad pillars that we are working on, and I'll try to give you a few examples of each of these three pillars that we have been doing in our lab in the last couple of years. Okay, so the first one is scientific natural language programming. When we started off, now everybody is familiar with ChatGPT, so I don't need to tell you what a language model is. But when we started off back in 2020, there were really no language models for materials. So what we did was we developed the first ever language model for materials. It's called MathSciBert. We trained basically, we took around something like 200,000 research papers on materials and then trained it for almost 15 days to develop a material science aware language model. What do I mean by material science aware language model? The language model understands the context of words. Let me give you a simple example. Let's take the word bank, right? I say I go to the river bank, or I have to go to the bank to withdraw cash. I'm going to bank on you. See, each of this, I'm using the word bank, but depending on the context of the word bank, the meaning is completely different. So the same way, many of us say, I'm not feeling energetic. Now this is very different from ground state energy that we are talking about in materials, right? And so on and so forth. So need to understand the context of that word to understand and extract information in a meaningful fashion. So we developed that language model MathSciBert, which understands the context of material, and this could be used for so many interesting tasks like named entity recognition and relation classification, abstract classification, etc. So, okay. So what do I mean by this relation classification, abstract classification, etc.? So let's take this simple caption. The comparison of XRD patterns of glass ceramic heat treated at 725 degrees Celsius for 5 hours, blah, blah, blah. Some sentence is going on. What are the key entities that are present in this? So if you look at it, there are applications, there are characterization methods, there are descriptors, there are materials, synthesis method, property, and symmetry and phase label. When you pass this sentence through MathScibert, it automatically identifies that rhombohedral is a symmetry or a phase label, BA4GD3F17 is a material, glass ceramic is a descriptor, and heat treatment is a synthesis method. So basically it gives you coarse-grained information, and with this information you can now actually meaningfully develop a database of synthesis method, characterization methods, materials, and properties, right? So, and this is something that's very useful. When you want to develop a new material, you need to have an understanding of each of these aspects. Then we went on to develop a database from information extraction from tables. On a lighter note, the reason why we picked this topic was because we thought it's a very simple topic, okay? Apparently not. This is because as scientists, we really do not have any consistency in how we write tables, okay? And I'm just going to give you a few examples of that. When we started this problem, we realized that people can just randomly add rows or columns in the middle while writing a table. And these are distractor rows or columns. Orientation could be column-wise or row-wise. People use different units for the same property. They sometimes use material IDs like this, but sometimes they don't. Sometimes you have nominal composition, sometimes you have experimental composition, sometimes both. Sometimes everything is written in a single cell like this with a formula, and one has to understand, put the equation and understand what that formula is. And sometimes it's in variables. Sometimes percentage add up to some up to 100 or not, blah, blah, blah. It was really a challenging problem. And it took 2 years for us to solve this problem. We came up with a framework called DiscoMat, which stands for Distantly Supervised Composition Extraction from Materials Tables. What we essentially did was, you have an AI model. I'm not going to go into the details of this, but that takes the table as an input and extracts the compositions and properties as the output. And it took a lot of pain to develop this model because we manually annotated 5,000 tables. We took 5,000 tables and manually annotated each of the quantities in it and then trained this machine learning models. But that did yield some very good results. So from around 100,000 papers, we are now able to extract 83,000 compositions and 302,000 properties, which was not there in the literature, which was not there in any database thus far. And we've been able to construct one of the largest database for oxide, ceramic, glasses, cementitious materials. We went ahead, ChatGPT came in. We thought, can we have a materials ChatGPT kind of a model, right? And that's at a much larger scale because it can actually do a lot of things like writing a paper on its own, for instance. For this, what we did was we took around 3.4 million papers from Elsevier and 0.6 million papers from Springer Nature and trained a large language model on materials and then tested it on a much larger task list, okay? Now this one includes open-ended question answering, open-ended generation, like asking to write an article about any material, etc. And what we found out was, in comparison to all the models, the model that we developed, which is LaMAT, which is large language model for materials, outperforms even GPT-4 if we use it for material science specific task, okay? It will surely not outperform GPT-4 in any English task because that's not the intention. But if you take material specific task, it really outperforms GPT-4. And even more interesting was we were able to generate new crystal structures by simply asking it to generate a new crystal structure, and it was able to generate really new crystal structures which were actually stable. So we did molecular dynamic simulations on crystal structures and even density functional theory simulations on crystal structures and found that the 50% of the crystal structures that the language model developed, that the language model spit out, was actually stable. So this means, there is really a long debate going on whether language models can develop world models, etc. We don't know about that, but at least it can generate crystals. And it can generate meaningful crystals when trained on a large database of crystal structures. Changing gears, I'm now moving to material simulation. So I think I have convinced you that you can actually extract information and using language models from literature. But once you have those information, how do you actually validate or understand the behavior of materials and use that to develop new materials? So if you look at this multi-scale model, there are multiple length scales where you can do the simulations, electronic, atomistic, microstructure, and macro scale. But what we need is we need to have an accurate knowledge of the interactions, right? And meaningful energy functionals if you're doing density functional theory. And then you have long time scales and length scales. So how do we address these challenges? For those who are not familiar, this is a very simple idea of what molecular dynamics simulations look like. So you have positions of atoms and some function that describes the energy. You take the gradient of the energy, you get force. From force, you get the acceleration. From acceleration, you get the new position. And you continue in the loop. This is what molecular dynamics simulation is all about. Getting this energy functional, this particular thing is the most crucial part in molecular dynamics simulation. So you might use very simple spring-like harmonic potentials, which is half kx squared, or much more complex functions as depending on the accuracy that you want. But what we did was, can we actually learn these interactions directly from trajectory? And for this, we developed a framework called a Hamiltonian graph neural network. Essentially what it does is that it combines the Hamiltonian equations of motion with a machine learning model. So what happens is that, a model can always predict energy, but we don't know if the dynamics of the system conserves energy or is it Hamiltonian in nature. So we put this inductive bias of Hamiltonian equations of motion in the architecture itself, so that the dynamics that is predicted by the neural network respects the Hamiltonian equations of motion. Now that's very interesting because you can see we tried it on multiple systems like spring, gravitational system, and even Lennard-Jones systems. So you can see this is the kinetic energy predicted and kinetic energy actual, potential energy predicted and potential energy actual. And this is without training on kinetic energy and potential energy. This is by purely training on trajectory. So we are able to learn the energy of this, and not just that, we are able to learn the energy function also. For example, if you look at the Lennard-Jones system, you can see that the red line shows the actual function and the blue shows the predicted one. So you can actually recover interaction loss without even knowing anything about it by simply allowing a neural network to learn the interaction loss while respecting the laws of physics, right? And going forward, you can in fact use symbolic regression and even get the equation out of it. So if you don't know what is the equation that's kind of combining or allowing this particle to evolve, you can simply directly use this approach and recover the equation, fundamental equation. So it's not a black box AI method. It actually gives you insights into what is the functional form and allows you to actually predict, use that to make meaningful predictions. Going beyond simple systems, we tried it on realistic materials like silica. So here is a small example. And with our LGNN, we are able to reproduce the pair distribution function, angular distribution, etc. Simply put, we are able to replicate the structure directly without training it on energy or forces, but directly by looking at the dynamics of the system. We went ahead and then tried to understand the energy landscape of the system. And this was even more interesting for us because we were able to develop a method to visualize the underlying energy landscape. So you can see that this is really a complex landscape, and even in this landscape we are able to identify stable configurations that are kind of the minima and even face jump between multiple wells like this. Okay, and then the next approach that we have been looking at recently is called differentiable simulation. That means you have a simulation, but many a times what we want are gradients of different quantities. And what we do typically is you do finite difference and things like that. But can we actually differentiate the simulation itself? And this idea is called differentiable simulation. And recently we have been able to do this very interesting approach with which now we are trying to bridge the gap between experiments and simulation. So if you have an experimental observation, for instance, you have the phonon density of states or vibrational density of states or phonon dispersion. So if you use the interatomic potential, this is how the density functional theory and the molecular dynamics looks like. But you can actually minimize this error directly and then tune your interatomic potentials using differentiable simulation so that you can actually reproduce these properties. Either it is from experimental simulations or from first principle simulations. With this, I close the second part. I have been able to convince you, I hope, that you can actually use simulations, AI with simulations to get meaningful insights and not just as a black box. And the last, which is the most ambitious and the one that we have been doing very recently, is automated experiments. Can we make large language models do experiments alone? Now, why did I try this? What is the motivation? I am not an experimentalist. I don't know how to do experiments, but I wanted experiments to be accessible for people like me. Yeah, I will wind up in 2 minutes. So we created a database, like it asks questions in English language like this. Set the image and capture parameters in the AFM software as follows, or set the file name to be this, etc. And there is a large language model agent that actually interacts with the AFM and then translates this to a code, executes the code, takes the image and put it back, right? So that's the broad framework that we have, and it's a simple expression. So we try to evaluate multiple language models for it. I'm not going to go into the details of it because I want to really show you this video of how it actually works. So here is a small example of atomic force microscopy being done automatically by simply giving a human prompt, right? So the AFM software is here. This is the human prompt. So you can see, you can just give a simple message. First set the image size to 5 by 5, then scan that image. After that, open the image file and you will see this, right? So this is a human prompt, that's all. Now you press this, it's automatically operating. We are not doing anything. First it changes the image size, it automatically starts the scanning. So you can see it's the scan is showing up, the image is being taken, scanning progress, and then finally you will get the complete atomic force microscopy image. And once you have such an image, you can even analyze those images. Great. And with this, we have now been able to really optimize even atomic force microscopy parameters, which takes 2 to 3 years of training, at least 1 to 2 years of training for a person to know how to operate atomic force microscopy. This was done pretty much in like a few hours, if not minutes, and it gave images as good as a human would. Now this opens up really a lot of windows for exploring different things, automated experiments, high throughput experiments. But in summary, I hope I have convinced you that AI and materials discovery go hand in hand, and you can know at least 3 of these pillars: scientific NLP, material simulation, and self-driving labs in tandem can really accelerate and push the frontiers of materials discovery. And I want to leave it at this broad thought. It is initially AI for science, then science for AI. We really don't know what the new frontier is, what are the new areas that we are going to explore, but it's really an exciting time, and we look forward to what's coming. And of course, I need to thank my collaborators, funding agencies, students. This has been done with the support of a lot of funding agencies, and most importantly, the work has been done by all the PhD scholars. So thanks to them. I'm just a presenter, the credit goes to them. Thank you.
Thank you, Dr. Anup Krishnan. I think it is a fascinating talk as the future of the way we kind of design and build new materials. Thank you very much. Can I have a few comments from the audience? Yeah.
Yeah, very impressive work. My question is that when from the trajectory, you try to infer the potential landscape, if it's very rugged and there are deep minima, how long a trajectory do you need to get the entire landscape?
You cannot get the entire landscape for sure, because as you rightly pointed out, for a very simple 7-atom Lennard-Jones system, the number of minimas are anywhere between 10 raised to 60 and 10 raised to 230. So it's impossible to explore all the minimas. But what we can do meaningfully is go to a minima and explore around that minima. And this is possible. And another thing that we have tried to do recently is to come up with methods that allow us to go to lower minimas. So basically we train a machine learning model to just explore the landscape, and then when it finds a new minima, then it tries to understand what are the patterns that leads it to a new minima, and from there you keep exploring. So this has been quite successful. The idea called reinforcement learning, I have not talked about it, but that's a different work we have been doing. I think that is possible, but if we want to enumerate all the minimas, I think that's still a really big challenge, open challenge, something worth pursuing as well.
Yes, I have a question. You have been successful in differentiating, you have been successful in optimization. Can you solve any mathematical problem, any mathematical theorem using your neural networks?
Sorry, can you repeat the question?
You have solved two basic mathematical problems, differentiation as well as optimization,
Sure.
by using neural networks. Can you solve any differential equation, any integral equation of mathematics,
Okay.
or any other mathematical problem like Gauss's theorem?
Right. So I think you are giving me too much credit. I have not solved differential equation. I have not solved optimization. I have rather been using
My question
tools.
is, can you?
I have been rather using tools that allow us to address this problem. And I think the answer to your question is, as the context is set, within a context, within a very well defined problem, we will be able to solve it to a reasonable extent, right? But if it is, I mean, there are several challenges. For example, fracture. You think of it as a very simple problem, but it's a very complex problem and it's not solvable, whether you use optimization or differentiation, because the field itself is non-differentiable at that point of time, right? So I am not sure I can give a sweeping general statement of that sort. Yeah, sorry. Yeah. Absolutely. So you are setting the context for it. So we are talking about linear elastic fracture mechanics. In that case, yes. Right. Yes, absolutely. So there is a paper which we have already written on linear elastic fracture mechanics, where you can actually predict the stress fields and things like that with, it's not neural network, it's Fourier neural operator, but you can do that. But yeah, I think we need to set the context and the problem very clearly. And if you do that, I think many of these problems have become tractable. And I would leave it at that, right? That
Thank
whether
you.
it solves or not is an open challenge.
Thank you so much. Thank you very much. I think it's been a very interesting talk, and we conclude this particular session. And I thank both the speakers for their very, very informative and interesting lectures. Thank you very much.
Let us thank Professor Sivaram for chairing this session. And tea is outside. Please come back by 16:40. So we have one more exciting session and the public talk. Thank you.
आपकी मम्मी की और दादाजी की दवाई, वो भी
Okay, thank you for coming back after tea. And we've got two lectures by fellows and associates before we have a little break and then we have the public lecture. So I'm very happy to invite Professor Saraswati Vishweshwara from the Indian Institute of Science to chair this session. Saraswati. Yeah, you can.
I thank the organizers of the academy for giving me an opportunity to chair this session. This is we have two speakers in this session, and each one is 20 minutes, 17 plus 3 for lectures. The first speaker is Dr. P.G. Kubendran Amos from National Institute of Technology, Trichy. He's going here, right? Oh. I just wanted to make sure that you are here. Okay. Dr. Kubendran is going to talk about was NASA's microgravity experiment on material coarsening ill-planned, insights from AI-assisted material research. So we know that the future of science is going to be dominated by AI. Already we had a sort of a taste of that from the previous talk. And now we have Dr. Kubendran Amos also will take up that route.
Thanks a lot for the introduction, madam. All right. Okay. Yeah, thanks a lot. So,
well, the details of biodata is given here, so I didn't spend much time to talk about it.
Right. Thanks a lot, madam. So, learned audience, good evening. This talk, when compared to the scientific rigors of all the others that preceded, is going to be rather a walk in the park, and it is by design. Imagine you are a highly decorated military officer. One day you receive a call from your superior to conquer an enemy land. So you come up with a wonderful strategy, execute it flawlessly, and you occupy pieces of this enemy land. After a while, it becomes rather abundantly clear that the war has reached an impasse. Neither you are able to proceed further, nor your enemy is able to make you retreat. So at this juncture, the officer of the enemy army visits you, and he concedes that the land that you have captured so far belongs to your nation. On top of it, he makes you an offer. He says, I'll allow you a period of ceasefire, wherein if you choose, you can consolidate all these pieces of land that you have conquered. Now, what would you do? Would you choose to take up the offer of the enemy officer? Now, irrespective of what you choose, when you consolidate your pieces of land like this, there is an aspect that you cannot negate. That is, when you choose to consolidate these pieces of land, the high tension boundary that separates your land from that of your enemy significantly reduces. This cannot be easily avoided in your decision of whether to take up the offer or not. Now, this reason is something similar to what drives some material changes, particularly at high temperature. If you consider any material and look at it at the microscopic scale, you will observe that the seemingly homogeneous material comprises of several submaterials. And this, in the microstructure, the structure at the microscopic scale, we refer to them as phases. Now, when you have a material that comprises of just two of these phases, one of these submaterials or the phases, we refer to them as matrix, and the other two as the precipitate. Now, under favorable condition, such as high temperature, this matrix and the precipitate, they tend to evolve for the same reason why we would choose to consolidate our territory. That is, the interface that separates my precipitate from that of my matrix is an high energy region. Now, when we allow the larger precipitates grow at the expense of the smaller ones, what we essentially achieve is rather reduction in this high energy interface, thereby reducing the overall energy of my system. So, as the thermodynamic panacea goes, my system always wants to settle down in the lowest energy state. So therefore, the precipitate, which are the larger ones, they tend to grow at the expense of the smaller ones under favorable conditions. Now, even though this phenomena in itself is something wonderful to observe in a material system, there is also a physical component to it. When you compare a material with large number of smaller particles or precipitates with that of a material with a very few larger precipitates, the material with larger number of smaller precipitates, they appear to be stronger, or they are noticeably stronger when compared to the other material, while the other material is flexible in nature. So all I have to do is, if I want to change the property of this material, of this two-phase material, I just have to increase the temperature and change the size of my precipitates. However, in order to do that, I need to know the rate at which this happens, the rate at which the larger precipitate coarsens. Now, as opposed to other microstructural changes, the driving force for this coarsening is rather innate, meaning it is the curvature difference between the larger particles when compared to the smaller particles that governs the rate at which this happens. So if you want to simulate this particular microstructural evolution, when you set up the initial condition, there in itself, you are setting up the driving force. So therefore, when compared to other microstructural changes, this is going to be sluggish, meaning I cannot completely rely on experimental techniques to understand the rate at which the coarsening happens. So therefore, from the very beginning onwards, theoretical approaches have been taken to understand the rate of this coarsening. And one of the first theories is what we refer to as the LSW theory here. The LSW theory is founded on the fact that in some material system, the rate at which the coarsening happens is primarily due to the rate of mass transfer from the smaller precipitate to the larger precipitate in the closed system. So material, the ones that surround you, they are closed system. Very rarely they allow external particles to interact with them. And when the larger particles grow, the mass should only come from that of the small particles. So that was the foundational expression along with the closed system. They were able to come up with an elegant expression that described how the size of the precipitate changes with time. Now, the size, they estimated it in the form of an average radius. Now, this being rather the foundational theorem or a pioneering theorem, there were several assumptions made to it. The first assumption was the classical one. The particles were assumed to be spherical in nature. The other assumptions are as follows. The second assumption was the atoms of the precipitate, they have no strain, they have no misfit between the atoms of that of the matrix. The third assumption was that this theory considers only those time periods that are far away from the initialization of the coarsening. Once you take this material, rise the temperature, this theory focuses on a steady state condition which happens far away from the initializing state. And one final assumption they made is that the behavior of these particles depend on their own radius, their own size. It is independent of their neighbors. Now, as you would not expect me to behave in the same way as I behave on this dais when I'm at home, the same way, this is one such assumption that was deemed to be rather completely unphysical. So therefore, in subsequent theoretical approaches, this particular assumption was attempted to relax. Now, when attempts were made to relax these particular assumptions, the theory became more and more complex, ultimately changing the elegant nature of this expression here. So what they wanted to ultimately achieve was an expression of this form wherein the kinetic coefficient is governed by the volume fraction of the precipitate. So what it essentially means is when the volume fraction of the precipitate increases, the distance between the precipitate, they tend to decrease. So it means the particles or the atoms that constitutes these precipitates can move faster, ultimately increasing the rate of coarsening. But that they were not able to capture in the existing theories. So therefore, they looked for an alternate approach wherein they thought of coming up with a material system that satisfied all these three assumptions, and we can manually play around with the volume fraction, ultimately through experimental observation come up with this kinetic coefficient that depended on the volume fraction. So ultimately, we need a material system wherein the precipitate are spherical in nature, that doesn't have any tussle with the matrix. The atoms does not misfit with the atoms of the matrix. And finally, the steady state should be easily achievable in the practical sense. So they were able to achieve such a material system. So that material system is rather a composite material system, a solid liquid mixture of tin and lead. So this material system was able to satisfy all these three conditions. And when they put that into practice, they observed that there was one behavior that made this particular system, even though it satisfied all the assumptions, rather unapproachable. That is the difference in the density of the precipitates when compared to that of the liquid matrix. Because the precipitates were denser, they began to settle down. In order to address this issue, they took a drastically different route of getting rid of gravity. So once they were able to get rid of gravity, they now had these precipitates scattered in a way that is close to ideal. And now they wanted to perform these experiments in region wherein we can experience this microgravity, and that is where NASA comes in. So they performed these experiments in microgravity glove boxes that were housed in a space shuttle and also in International Space Station. And thankfully for us, the outcomes of these research was made available to us in this portal, for anybody can download it and analyze it. Now, these were the different volume fractions they have considered. So starting from 10 to these different fractions of precipitates, they analyzed, they built, and they were able to study how the kinetics were changed when you increase the volume fraction of your system. Now, even though this report was published in 2013, and the scientific or the way they built this particular experimental system was published in 2011 and 2013, the first report on analyzing or arriving at the kinetic coefficients and how it influenced or how it was influenced by the volume fraction came only in 2015. And even that report was not convincingly received by subsequent researchers, primarily because of all these different volume fraction. In the study that reported the influence of volume fraction on the kinetics, they only considered the first three. And that too, they showed that the kinetic coefficient significantly changes between 20 and 30. So this was heavily criticized by a team that published their work in 2021, and they offered their own theory, which we'll get to it in a minute. To our understanding, the reason for the delay was primarily because this information about their experiments, they were not numerical data which we can easily feed into a machine learning algorithm and then come up with a model that can describe how the kinetic coefficient changes with the volume. They were not numerical data. Unfortunately, these were images like this. So for every volume fraction, for every time steps, there were a couple of 100 images like this. And in every images, there were a couple of 100 precipitates like these. So if you want to understand comprehensively how the kinetic coefficient changes with volume, you need to understand how these precipitates, the size of these precipitates, these individual precipitates, they change with respect to time. And humanly speaking, it becomes an arduous task to do that. So what we essentially did was, here we introduced our artificial intelligence. Now, what we did is we need two factors in order to calculate the average radius of the precipitate. One is the area fraction assumed by the precipitate and the number of precipitates that are present in the system. So we use a technique called a segmentation technique to identify the area fraction assumed by the precipitate, and we extended a detection algorithm to count the number of precipitates. So irrespective of how many number of precipitates are there in a given image, which we call it as microstructure, the algorithm is able to detect it precisely. So once we did it, now we were able to calculate the way or the influence of volume fraction on the kinetic coefficient. But to our dismay, we found that there was no significant influence. Even though the theory was rather straightforward, with increasing the volume fraction, the distance decreases, so it means the atoms can move easily, fastly, so the rate at which the coarsening should happen should increase, but this was not reflected in the results that we got. So here is when the theory proposed by the discontented team came to our aid. According to them, in addition to the distance traveled by the atoms, the assimilation of these traveling atoms into the precipitates also govern the kinetics of the growth. So if you ignore this, you will not be able to completely capture the kinetics of the coarsening. So essentially what it means is, when we focus on the assimilation aspect of it, we have to look into a completely different theory, and that is exactly what we did, because the existing LSW theory focused primarily on the movement of atoms. The other alternate focused on both the movement and also the assimilation of atoms. When we included the assimilation, we found that for all the volume fraction that we have considered, our kinetics matched up with their empirical relation they observed. So essentially what happened with the research of NASA is that they assumed a wonderful material. They were able to arrive at a material that satisfies their assumption, but they thought this material is going to behave following the LSW theory. But unfortunately for them, it did not. It followed a less well-known TIDC theory, wherein rate is governed by not the movement of atoms across the matrix, but the movement of atoms across the interface. Because this was rather a solid liquid system, the interface was not that sharp, it was rather diffuse. So the movement of atoms were rather sluggish towards the precipitate, thereby becoming the factor that governs the overall kinetics of this evolution here. So ultimately, to tie this all up to our analogy before, if you want to come up with a ceasefire duration during which you can assimilate all your pieces of land, it is not only important that you focus on how fast you can able to transport your people, but you also have to focus on how quickly you are able to formally assimilate them into your state. So to answer the question, was the NASA's experiment on capturing the kinetics, was it in planned? In a way, it is. Thank you. So I was told that I would be having 15 minutes of time, so I prepared accordingly and I finished it. So
Thank you so much. Any questions?
In LSW theory, R is cube equal to KT. When that is controlled by volume diffusion. Now you are telling that they came to a conclusion interface controlled. What is the power for
okay,
R?
if it is surface diffusion or interface control, it will change to 3 to 2. So that is how it is governed by surface diffusion. But what we observe, or what happens in this material system, is it is trans-interface diffusion. So it is going across the interface, which is rather diffuse. So that is the primary difference between LSW surface diffusion when compared to trans-interface diffusion control.
Yeah. So coherency strains they are able to measure?
No, this is a solid liquid system. So there is no role of any strain, and that is the reason why we choose this particular system.
Yeah, okay.
Thank you, sir.
Yeah.
Yes, yes.
Yeah. So I couldn't understand when you say diffusion across the interface. So it is going into the minority phase from the surrounding majority phase, or from where are they accumulating?
Okay, wonderful. So essentially, the system we have is a tin-rich system, and your precipitates are tin-rich. So if this precipitate has to grow, these atoms need to move from one precipitate, and they accumulate on the surface of the precipitate that wants to grow. And this happens faster. And this accumulated atoms, they need to traverse into the interface so as to increase the size of the precipitate.
So that is the rate limiting and not the diffusion. That's what you are saying. But it's probably not appropriate to say that LSW is wrong, because in the derivation, they always assume that the volume fraction of that minority tending to 0, basically negligibly small.
Exactly.
So that remains valid. It is just that it cannot be applied in this regime that you are talking about.
Exactly. That's absolutely right. LSW theory is never wrong. It's just the material system they chose, they kind of messed it up.
Solid. It is for solid, which has been developed. Now
yes.
you are applying for solid liquid.
Liquid, yes, sir. But solid, you always have the constraint of the strain between the precipitate and the matrix. So that needs to be avoided. So they chose the...
It is a big claim that LSW theory is wrong.
No. It's never claimed that LSW theory is wrong. In order to prove that, they chose a material that did not follow LSW theory. That is rather my point. I'm sorry if it got converted a different way. Of course, it's not completely not applicable. It belongs to TIDC theory. Yes, the material this system is different. Yes, sir.
Yeah, I was also thinking about when nucleation is so different, shapes are so much different. So volume percentage, if you look at it, may be a very crude way of representing because you have all type of shapes, 10% to 20%.
Definitely.
Some of them are triangular, some are spherical, some are rod-like. So I was only looking at how.
It's absolutely right, sir. So again, here's where the material system comes into play. So when you have a combination of solid and liquid, and you have a system with isotropic boundary condition, you cannot have, be it elastic isotropic or because of the interfacial energy, you cannot have a different shape except for the spherical one. And the statement here is NASA went wrong in choosing the material system, not with the theory.
Okay, but all were spherical, maybe it would fit better?
Of course, it would fit. Of course, it should fit because the theory is right.
Okay.
The material system is kind of not matching with it.
And Ostwald ripening and conventional theories, are they not valid?
Of course, they are valid, sir, but they go into the thermodynamical aspect and they talk about chemical potential, how it changes with curvature. But this is purely using asymptotic analysis at t tends to infinity. They arrived at this expression.
Okay, thank you.
There are no questions. I have one small question.
Yes, ma'am.
You were saying that it was ill-planned. Have you come up with something to get over with that and then make it correct?
The simple answer is to come up with a different material system. Like in the talk before me, I can use an AI technique and find out a different material system wherein that can be used to rather find out the kinetic coefficient for this LSW theory.
So you have thought about it, is it?
Of course, yeah.
Oh, okay, thank you very much.
Thank you, madam.
Seems there's
Yes, sir. We are not real. Definitely, sir. We will take it. Thank you.
Okay.
Thank you
very
madam.
much.
Thank you.
Next speaker is Dr. Shubhadeep Chatterjee from Center for DNA CDFD's Center DNA Fingerprinting and Diagnostics. Okay, Hyderabad. Is the person around here? Oh, okay. On the stage. Oh, okay, you're already there. Okay. He's going to talk about understanding the social language of bacteria. Speak or not to speak. Please go
ahead. Okay. This pointer, right? Laser. Okay. So I will take you through the hardcore material science to actual living biology. So I will take you to the mysterious world of secret language of bacteria, like those tiny microbes. And maybe at the end of the talk, I will convince you that they have a very sophisticated language and communication system. And that is very important for the present day health as well as the microbiome, what we talk about, like in the modern medicine, that we think that our health is hardly mostly dependent on the microbiome effect, so that person to person medicine varies. So this is all the microbes, how actually they govern the. It's not changing. So if you see the response by communication is a very important part of all living organism in the earth. So all living organisms have, on the course of evolution, have developed the methods of communication, and along with other living characteristics like growth, reproduction, heredity. So response by communication is a very important trait which has been developed in all living forms, and that is because by response
they communicate with their fellow mate what is coming, so that they will be more tuned to what the environmental fluctuation. So if you see the mode of communication from the sophisticated human language to many other life forms, so they have different modes of communication. And you might be fascinated that the honeybees perform a dance movement, the dancing language. The firefly blinks, and this blinking it does in terms of a pattern which tells the fellow mate whether they are ready for the mating or not. So different forms of life have evolved different modes of communication in order to better coordinate their social behavior. So if you now think about a bacteria, so the size of the bacteria is in micrometer, like 2 to 3 micrometer, and you can't see them in the naked eye. And the obvious question which arises, do unicellular organisms such as like a bacteria, which is such a solitary living organism, which is 2 to 3 micron, 4 micrometer in length, do these bacteria have a social structure? So they also have, like other animals, they have a social structure, or they have a communication method. So the clue came not from a scientist, but from this fellow. This is a squid. Okay, it stays there in Pacific, and in Pacific, when the fishermen and the marine biologists saw this squid, this hunts in the shallow region. In the night, it produces a light, which is a luminescent light. Okay, so this is called the light organ of the shrimp, the squid, and this light actually causes it to helps it to see its prey, and also it attracts the shrimps towards it. So, but surprisingly, what they found, the light which is produced by this squid is not its own light. It is the light which is produced by the squid is by millions of bacteria which colonizes its organ, the light organ. Okay, and this is one of the fact. The more surprising fact came that they only produce light. So now they will produce light by the bacteria. They will only produce light when they are in large in numbers. So when the bacteria is less in number, they don't produce light. So when they are in large in number, they only produce light. And how these numbers are related to this form of light communication, that they started trying to figure out. So then the process, what was discovered is a quorum sensing process. Okay, so the quorum, that means in a normal meeting when you have a majority, so you have a quorum and then you decide to do a function. Similarly, in very small organisms such as bacteria, they produce signaling molecules in a density dependent fashion. So this is very important. When there is less in number, they will produce in less amount of signal, and as the number increases, the concentration of the chemical also increases in the surrounding, and when it reaches a particular threshold, it tells the bacteria, now you are high in number, now you do this function. So it is actually the concentration which is driven by the numbers, which actually governs the social behavior of the bacteria, what it should do at low cell density and what it should do at high cell density. So basically bacteria can count and recognize each other by their language molecules or the chemicals. And this is a very simplistic model by which the bacteria can produce and sense their signaling molecules. So there are enzymes which makes the signaling molecule, and as the density increases, the amount of the signaling molecule also increases, and then this signaling molecule, when reaches a particular concentration, as I was telling, then it binds to regulators. These regulators are nothing but they regulate our expression, like the gene expression inside our cell, like what we should make and what we should not make. So basically, this is a concentration dependent behavior of the cell is regulated based on the low or high cell density. So you can't listen to this language, but you can see the language. So what we do is develop biosensors, okay, the bacterial biosensors, which can detect these different form of bacterial languages, and that you can see it in terms of a fluorescence, okay. So in the two plates, if you see, there are plenty bacteria. So this bacteria is not talking, and these bacteria, when they are fluorescing, that is indicating the biosensor they are talking to each other, okay. So it's as complex as human language system. So many of us are bilingual, or we know many languages. So the bacteria also confuses us. So some bacteria are very complex, such as cholera, the Vibrio cholera, which causes cholera. It speaks in two different languages. Okay, one language is for their private talks between themselves, and the other molecule which it produces, it communicates with the other gut microbes which are there in the. So they know then who are their neighbors. So this way they actually modulate the behavior, and sometimes they are much more clever. So they don't spend energy on speaking. Okay, so they have receptors to listen to what others are speaking. Okay, so there's again another degree of sophistication, that you don't speak and waste your energy, but you listen to others and change according to what is happening outside. Now, why these bacteria and these small microbes talk to each other? So there is a very simple concept in the evolution in terms of cost and fitness. Okay. So now I will give you an imaginary situation. Now suppose there is one thief and he is trying to break the wall and is firing the bullets. Okay. The wall is so strong and the firing power of one or individual is so weak that it is a waste to fire to break the wall, because if it breaks the wall, then it will get lots of nutrients and lot of valuable things which are there. But if there are many number of thieves and they all fire at one time, the firing power of that group is more cost effective and fitness, it has a fitness advantage, that when they fire together, the firing power is enough to break the wall and the whole group benefits. So this is called as inclusive fitness of the individual is less compared to a group behavior. So when you perform certain functions in unison, so the rewards are more. You can do the function when you are individual, but the returns will be not that effective. So in our laboratory, we work on pathogenic microbes. These are particularly plant pathogens, and which are very important for agricultural diseases. Okay, these are called as Xanthomonas group of plant pathogens, and this is a typical example which causes disease in rice, and it's a very important disease in rice. India, not only in India, all Southeast Asia, and it is a very, it causes even in the season, in the humid season, 60 to 70% yield loss. And this bacteria forms a yellow color mucoid colony, and many years ago, some years ago, we identified a quorum sensing signaling molecule. So I am not going much into detail, and we call it as DSF, diffusible signal factor. It's a cis enoyl fatty acid. So okay, fine, this is an organism, we have found a language and it is able to communicate with itself. But surprisingly, what we saw, if you knock out, if you disrupt the signaling system in this bacteria, it completely loses its ability to cause disease. So that is indicating it has integrated the communication signal to prepare itself to cause disease and to organize themselves to attack the host. And when you again put back the signal, it again restores the disease. So these are typical disease symptoms in the rice. What happens when the bacteria enters through the vessels and it causes the drying of the leaves, and after 14 days the whole field goes. You have to burn the field. There is no other remedy. So we started looking more inside how the bacteria is communicating inside the plant. So using high resolution microscopy, I am not going much into detail. Now you can track the bacteria where they go and form. So the long pipe-like structures which are you are seeing are the xylem vessels, okay? So for conducting of the water, and when in a infected plant, you always see bacteria in a group. Hardly you can see very solitary bacteria. Mostly they form a biofilm kind of structure, and that is indicative of a communication, because if you take a mutant bacteria which is not able to have the signal, so it is not able to cause disease, it is dispersed in the plant. So now I am not going much into detail. So we work on the mechanism of quorum sensing, how it actually affects the disease, and this is what we modeled. That is a very complex model. It has a biphasic lifestyle, this pathogen. At low cell density, the low amount of quorum sensing signal actually triggers the bacteria to move towards the door or the entry point. And once they enter, the medium range of concentration of this signaling molecule actually induces the bacteria to start low firing power weapons to disrupt the host without much alarming the host defense response, so that little bit of nutrients can be released and the bacteria grows more in number. But when it reaches high in number, then it causes the maximum destruction, because it can count each other. Now we are more, even though the plant will mount a defense response, 70% will be killed, but this 20% will survive. So those will cause the disease. And using molecular genetics approaches and several biochemical approaches, which I am not going, so we have trying to dissect out the signal transduction machinery of this bacteria, how they, the take home message you don't have to remember, these are all transcription factors, genes what we have isolated in the course of our work. So but what it tells is the bacteria utilizes a very complex and sophisticated information processing system and to perform various social tasks. So now the most important evolutionary question comes. So with every evolutionary advantages, so there come disadvantages, and how nature takes care of it. Yeah. So as I told that quorum sensing is very good when you want to do some task in unison, but it is also a double-edged sword. Okay. So imagine a population in which they are talking and they are performing certain tasks, and certain cheaters arise in the population. Okay. So now these cheaters, they don't do quorum sensing, but they take all the benefits from the performers. Okay. And if this system continues, altruism, then it will cause conflict and soon the system will collapse. Very similar to an examination. Okay. So this guy is cheating, others have worked, but in the next exam, others will be also cheating, and this whole system will collapse. So how actually the altruistic kind of quorum sensing system takes care of this cheating, that I will answer in what we discovered. And the second most problem is that too much talking is also very bad. So you can alert the host security system. Like if thieves started singing and dancing in front of bank, then obviously the security system will be alerted. So how actually bacteria takes care of these two problems? So what we identified is the bacteria maintains two different population inside the host. So these are stochastic non-genetic heterogeneity which it maintains. 80% of the population performs and this 20% of the population doesn't perform, and they are actually the one which colonizes and to a new area, and the population which actually performs, they stay there, and in that way they do a division of labor. This gives an advantage to the bacteria to escape the host by switching between talking and non-talking form. And then how this is my last slide, and how they actually avoid the host alarm system. Actually, as I told, indeed this bacterial signaling molecule is detected by the plant and it can mount a defense response, what we showed. But this bacteria is very clever. Actually, although it mounts the defense response of the plant, it also secretes suppressor which can suppress the defense response of the. So it has some moles in the CBI. Okay. So there is alert, CBI gets alerted, and you can suppress few of them. Okay. So it is a constant evolution, arms race between the host and the pathogen. And this is our CDFD in Hyderabad. So we have two units, one involved in basic research in bacterial genetics, cancer and cell biology and other thing, and we have services wing which the name comes from, DNA fingerprinting and diagnostics. And these are all my lab members, and I thank you and also the academy for giving me a chance to speak in this.
Thank you very much, Dr. Chatterjee.
Yeah.
Any questions? Two hands. Okay, you can start.
See, as far I'm not a biologist, by the way. So
Yeah,
as far as I knew that during evolution,
Mhm.
so social behavior started only with these four social insects. But what you were saying, can then one say that during evolution, even bacteria develop some social behavior?
That's what we are telling. If you go to archaea, which is the most. Actually, the problem is very kind of a big. 99% of the bacteria we are not able to culture still till date. The one which we are able to have some information is that 1% which I am talking about.
And this 20% or something that you said.
Yeah.
Okay, is this specific to only this bacteria or this?
Now other quorum sensing system also we have. So we have found a switch which actually stochastically switches off because of the epigenetic. I am not going into much detail. So it is a random event. So 20%, around 20 to 30% of the population, there is an unequal distribution of a protein which causes it to switch. And the nature has designed in, and if you genetically alter the switch, then you can make 100. So we put this circuit and put it in normal bacteria, the lab bacteria like E. coli, then you can make 100 and 0, and that is less fit compared to that 80-20.
Here's another question.
Yeah, I mean, nice talk. During the course of evolution, what do you think how do these bacteria decide about the threshold in terms of the numbers? Because as you said, it's a double-edged sword, right? It can go either way.
Yeah.
So how do they decide about this threshold?
Actually, if you see in terms of evolution of host and the bacteria, so bacteria initially, as per the evolutionary theory, if you see the evolutionary scale, bacteria were earlier only environmental. Okay, so they were living on different, just little nitrogen or some source. So soon they started, the plants evolved. Okay, so they started getting landing on the plant leaf or etc. and started getting little more nutrients. And in that condition, because the mutation rate in bacteria is very fast, because the doubling time of bacteria is very fast compared to a eukaryotic host. So there is always variants which keeps on coming, and some variant got selected which can better utilize the host resources, and that got selected. So in the course of its natural setting to the host colonization, the quorum sensing evolved, but it didn't take care of the alarming system. So when they started landing on the plant or an animal, then the alarming system, and then again selection happened. So it selected those bacteria which can suppress that innate immunity. So it is a constant co-evolution which is happening between the plant and the or any bacteria. And you will be surprised to know human body has 30 trillion cells, and an average human organism has 30 trillion cells. How many bacteria is there in our body? If anybody can guess.
The gut bacteria.
No, I'm asking
Number, I know you're
numbers. 3 times 30 trillion. So actually our whole body mechanism is also getting influenced by the microbiome.
Rene, do you have any question? You also not with bacteria, but you do plant pathogen. Okay. Anybody else? Oh, yeah, there's one more question on the other side.
So, hello, sir. So you find the DSF, right? The quorum sensing molecule. So usually, like in many research, they usually do quorum quenching or something quorum tricking something, so that they will not communicate and hence virulence gene will not on. And
so actually that is our ultimate aim. So now people are talking about social drugs. So antimicrobials actually will target a single protein or single gene. Getting a resistance is very easy. So you have a counter mutation, then they will be resistant. But now people are talking about social medicine, like if you target the social communication system, then the whole many of the other signaling system will be crippled. So ultimately our aim is to evolve strategies. I didn't present it because of the lack of time. So what we also do parallelly in our lab to identify quorum interference strategies. And what we found out, if you express certain bacterial genes which can quench the quorum or can modify the quorum in plants, so we created transgenic plants. So those transgenic plants are highly resistant to the disease. And since in India the transgenics is not much encouraged, so we have developed also a ectopic application based system which we collaborate with ICR people, and it is in trials now in Hyderabad.
ectopic as in like what exactly it is in ectopic? Like
Ectopic is the derivative of the quorum sensing signaling molecule that will that act as an analog, and it will saturate. It is just like you just block the mouth of the bacteria.
Thank you, sir.
One more question.
Yes, wonderful actually on microbe, their behavior. Can you highlight something on gut microbiome, how they behave, the different food habits or cultures or ethnic habits?
So you have asked the most difficult question. So in the scenario of gut microbiome is such that they are now finding correlation to disease, diabetes, everything. But actually speaking, if you think of gut microbiome, and when you do metagenomics or you compare it with the whatever you can culture, 80% or 90% you can't culture. You don't understand. Only you get what you get is sequences. So it's so complex. So only for 10 to 15% of the gut microbiome, and very complex communication goes on, like interspecies, intraspecies, communication between the host and the bacteria. So it's a very complex interaction. On microbiome, there are many groups, but on understanding what is the biology, there I don't think. because it requires multiple expertise. Like you require system biology expertise, microbiome, and also this in the whole of the world, like we don't understand 90% of the microbiome.
Okay, if we don't have any question, thank you.
Thank you,
Dr. Chatterjee, for a very interesting talk. And also, let's thank both the speakers. For the first one, Kubendran Amos and Chatterjee. Thank you.
And thank you to Saraswati, of course, for chairing. Yes. So now we have a short half an hour or less than half an hour break. And our speaker is already here, the public speaker. So you can stretch your legs or wait. And at 6 o'clock sharp, we will start the public lecture. Yes? So hope to see all of you back and bring your friends who have been wandering around.
of Sciences. It's my pleasure to welcome you here to the first public lecture organized as a part of its 90th annual meeting this year. Indian Academy of Sciences was founded in 1934 by Sir C.V. Raman with a goal to promote and support the cause of science and its progress. And each year the Academy organizes its annual meeting in different part of country. This year we are delighted to be here in Bhubaneswar and glad that the National Institute of Science Education and Research here has been our host. Through this public lecture that we organize as a part of each annual meeting, we as scientists want to learn about the areas which are at the interface between science and society and on the other side of the boundary from the society as well. These meetings give us opportunity to connect with the regional scientific community as well as general public, learn about various aspects of their life and science and society. So it's a really nice occasion for us to have a public lecture in the evening, which is also live streamed, and lot of audience can access this lecture in the future as well. So the lecture will be live streamed and will be available on the YouTube channel of the Academy. It's a pleasure to have with us Sri Jagadananda as the speaker of the public lecture today. He is a civil society leader and an activist. Sri Jagadananda is a mentor and a co-founder of the Center for Youth and Social Development, Bhubaneswar. Formerly, he was the State Information Commissioner, Odisha, and a member of the State Planning Board of Odisha. An active campaigner for people-centric decentralized planning. He, as the convener of Odisha Development Initiative, facilitated organization of Odisha Development Conclave, a multi-stakeholder platform. He was also a member of the Committee on State Agrarian Relations and the Unfinished Task in Land Reforms formed by the Union Ministry. He has held offices as the chairperson, Voluntary Action Network India, WANI, the largest national network of social development agencies in India. He was a chair of Credibility Alliance, a national forum for promotion of accountability norms for civil society organizations, and the chair of Sadhan, a national network of community development microfinance institutions with membership spread across the country. Presently, he is a member of the Standing Committee and as an expert in drafting the National Vision 2035 document at the Niti Aayog on institutionalizing partnership between civil society and the government. He was a visiting fellow at Civicus World Alliance for Citizen Participation and worked on the issues of legitimacy, transparency, and accountability within civil society at the Kennedy School of Government at Harvard University. His publication, Civil Society Legitimacy and Accountability, is widely available in English, French, Spanish, and Arabic languages. A notable one among his publications is The Organization Behavior, a framework for non-government development organization and an organization self-assessment tool for NGOs, the OSANGOs. It's a pleasure to have you with us, Sri Jagadananda, and we will be listening to you about the participatory governance and the need to promote and nurture active citizenship. Over to you.
What is necessary if I move around? Okay. Okay. कर दिया वेट तो रहे बिना okay. This one is working. Yeah. Okay. This is forward. This backward. This one.
will work like that. Put down, it goes. This
Okay.
is the next.
Okay.
And here is pointer.
Okay. Thank you. First of all, good evening. I must compliment your energy level actually. What is the energy level in the room? 1 to 10 scale? What is the energy level? This block? You know, after a day-long scientific session, and where each member of the scientific community would like to share the beautiful findings, the formulas, you know, all that, and with limited time, of course. So then, evening, there is a public lecture. I definitely would like to check the energy level so that I readjust my timing and the intensity of my conversation, right? So let me just check. What is the level? Very high? No, 1 to 10 scale, sir. 1 to 10 scale. 10. 10. So compliments. Let me compliment the Indian Academy of Science and all of you. And a special welcome to be in Odisha this time. And we are delighted that all of you are here. And 90 years is not a small time, actually. It's a great time. You know, that speaks volumes about the experience, insight, the maturity of an academy and its community, actually. So I'm so happy to be with all of you this evening to share some of my thoughts, some of my feelings, and some of my appeals to all of you as to how, you know, as citizens, you know, when we put our citizen hat, how do we activate that citizen hat, right? From a professional hat, when you come as citizens of this great country, you know, what is that we can do? And I'm so delighted to be with all of you. So again, good evening, everyone. It's an honor to be here at this annual convention to discuss a topic that holds profound importance for the future of governance and society, that is participatory governance, and where promotion of active citizenship is so important, so important. Today, we are living in a world that faces unprecedented challenges. You can see them, you can feel it, you can touch it now. 30 years ago, when we were discussing about the climate change challenges, people used to call us like, these are a bunch of pagals, right? And so they are saying there will be a sea rise, glacier is going to melt, the climate is going to be hotter, and issues like that. So we were going on, and I have seen even in international fora, right? I had the rare privilege, opportunity, and also the possibility of going through a major, what you call international events at the United Nations in the 90s, because 90s was a time when there was all these summits were taking place. The Summit of Social Development, the World Summit on Social Development, the Copenhagen one. Then there was the Millennium Summit. Then the Sustainable Goals, the SDG Summit. And then in between, there was a discussion that, well, we have agreed on a set of goals, we have agreed on a set of indicators, we have agreed on a set of timelines. But where is the finance actually to implement all these plans? So there was a major event also on World Conference on Financing for Development. And I was very fortunate to be part of all that at some point of time. And I have seen the debates, seen the conflicts between various blocks. I have seen also the consensus which emerged out of this confusing chaos at some point of time. And for me, 90s was a time, that was a time when we had political consensus and political commitments coming. Because unless you have consensus, you can't get into a commitment. Today, at least, the development mantra, the SDG goals, which is in front of us, at least there is a clear consensus. There is no disagreement actually. And how we look at our planet, how we look at the people, how we look at, the institutions through peace. And to do that, what is the kind of prosperity we would like to see? So planet, people, prosperity, peace, and if you want to achieve this, what is the kind of partnership which we needed? That also came out very vividly, very clearly. So it was a wonderful time to build consensus around the world that what is ailing and what can be done and how we can do it together actually. Partnership between the government, civil society, partnership between scientific community, ordinary citizens, community-based organizations, partnership between the West and the East, partnership between the South and the North, the developing countries and the developed countries, and the most prosperous group of countries and the least developing countries. It was a fantastic opportunity to really discuss, debate, and do that actually. But the challenges which I see, and all of you, I can believe, I believe that you also feel so, which ranges from inequality to climate change. That is the range actually now. Inequality is growing actually. You can see that very, very clearly. Very, very clearly. And climate change is no more a rhetoric, it's a reality now. I used to be in Nagpur during one of my career plans. By the way, I was introduced with many things, but I was part of the university system during my formative days. So I belong to the academic group. Not in the science, I was in the other side, the humanities side, but I grew up in the campus. But the day I decided to leave the campus, I was feeling that, at that time, my feeling was, you get tremendous autonomy, independence, and opportunity to do things for the society, staying in the campus, and you can do that. But, after some time I realized, and I was hounded by some very radical thinking. And if you have heard about it, Mao Zedong, I'm not a communist by the way, let me tell you that, right? Mao Zedong has said something very good. He said, graveyards are immobile. Graveyards are immobile. And next to the graveyards are the universities, right? Because universities would not know what is happening outside their wall. They are so engrossed in their own, affairs. So there is a disconnect between the community and the university, the college and the village actually. So therefore, he gave a very clarion call at that time during the Cultural Revolution in China that, you should break those walls. Professors, you come out and do something. And, and to remind my university days, this morning I got a very interesting offer from one of the university here, public university, who appointed me as a professor of practice. So now this new concept, professor of practice. So I was very surprised when I got a deal letter from the vice chancellor. And she says, now, we can do quite a lot of things by nominating you as a professor of practice. And I hope you'll be able to give us so many days in a year, this, that. But the point I want to drive is, today, the kind of climate change inequality debate and the technological disruptions which has happened, very good, constructive, positive disruptions, and the political unrest. And now more than ever, we need to find new ways to engage citizens in shaping the societies and its future, actually. The societies we would like to see. The societies you and me, we would like to see. If we don't engage, this is not going to happen. So therefore, participatory governance is not just a theoretical ideal, but a practical necessity at this point of time. Very important. It means that citizens are no longer just passive observers, but active participants in the decision-making processes that affect their lives, actually. That is important. Let me, I promise that evening sessions should not be boring, actually. Evening sessions and a public lecture of this kind and size should be interactive. It should not be a monologue, it should be a dialogue, actually. So therefore, I would be engaging all of you at some point of time, and if we get into a meaningful dialogue, maybe we can find something towards the end of our conversation. Before I proceed, I would like to just check with all of you, how many of you voted during the last elections? Congratulations. You have exercised your franchise as a citizen of this country. You voted, fine. My second question to all of you who voted, how many of you checked the antecedent of the candidates to whom you voted? That means their qualification, their criminal antecedents, their assets, and their liabilities. They are supposed to declare this through an affidavit. Now, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm coming to that, sir. So at least 10 of you who have done this, 10, 11. 11 of you who have done this, you have checked the antecedent of the candidates. Big compliments. And all of you who have been outside this 11, I would like you to join me in giving a clap to them, actually. They're active citizens. That is one active citizenship model. And for some of you, you may be thinking how this happened, actually. It didn't happen on its own, right? Very few of us, we were almost about 10 of us, who were part of a campaign in this country called National Campaign for Electoral Reform. National Campaign for Electoral Reform, only 10 of us, not many. The ADR, Association of Democratic Reforms, right, took the lead, galvanized many of us. We joined hands, and the challenge was the voters have a right to know also the antecedent of their candidates before voting, before exercising the franchise. They went to the court. Delhi High Court gave a wonderful ruling, and Mr. Lingdo, who was the Chief Election Commissioner at that time, he implemented it. All political parties, they came together, and then there was an uproar in the political circle. They said, who are these people? Why the court is interfering in our work, etc., etc. And the decision was challenged. It went to the apex court. The apex court heard it, and the ruling had not come. Then suddenly, the government in power at that time, 2000, 2001 to be precise, they decided that at least, this is going to be a little dangerous for the country and the political system. So let us bring an ordinance to neutralize this. They brought an ordinance. I remember that time President Kalam was the president. So the National Campaign for Electoral Reform, Justice Sachar, who was the Chief Justice of Delhi High Court, who is no more, he's in the heaven. Kuldeep Nair, some of you would know him. He was a media, what you call, very highly respected media professional. He's also somewhere up. And there are 3, 4 actually, they're all up. Maybe I'm not a lone survivor, but few survivors in that group actually. So we went to meet the president. We went to Rashtrapati Bhavan. We were given time. And when we met him, we said, President, there is an ordinance pending in Rashtrapati Bhavan. That is our information. Right? These are all concerned citizens who have come because we feel that the voters have a right to know the antecedent of their candidates whom they are voting, because electoral politics in this country has to be cleaned actually. And we would like to know, and the reason why you have come together, because we think if a person's liability is more than his assets or her assets, and the person becomes the finance minister of this country, I'm sure the banks will not be safe, actually, to be honest and candid. So therefore, we would like to know who is sitting where and what is there. And it was a lovely day, and as you probably know, President Kalam was a people's president. He welcomed all of us. And then he said, then, our argument was, I said, President, if you sign this ordinance, this will be one of the blackest ordinances in the history of democracy. So people will remember you. President, if you are able to refer this ordinance to the apex court, there will be a message that all is not well. So people will also remember you. So choice is yours, President. It was a very interesting, and before going to Rashtrapati Bhavan, I still remember, we had a meeting amongst ourselves. We said, today, we'll not allow the president to drift away, actually. We'll focus our discussion. So, in between, because I went from Odisha, he was in Odisha DRDO, and he was very familiar with the Odisha terrain. So he was asking, well, how is Balasore? I said, President, today is not Odisha day. We will discuss about Odisha if you invite me sometime, and I will be delighted to come, spend some time, we'll discuss about that. Today is the National Campaign for Electoral Reform. And he was baffled. The ordinance came back. When the ordinance came back from Rashtrapati Bhavan, nationwide there was a message that it's not well actually. And then one major political party, I'm not naming any party, they came forward, they said, yes, there is a sense what is there. But friends, let me tell you, it was such a frustrating experience for some of us. All political parties met. Parliament was reconvened. It was reconvened. People's Representation Act 1951 was amended by 2/3 majority, nullifying all that we were pleading for. There was an amendment. When there is an amendment, what do? The law has changed. The courts can only operate within the ambit of law. This gentleman who was in our group, Mr. Alek Padamse, right? He was advertisement, in that world from Mumbai, Justice Sachar. I was very frustrated. I said, many of you are in Delhi, you can fly, you can spend time. But for me to come from Bhubaneswar in the early 2000, we had one Indian Airlines flight. Midday, only one flight. Very expensive ticket if you want to go by flight. You go one day, next day meeting, and you come third day. So 2 nights of mandatory stay in Delhi if there is a serious business to be done, because only one flight. He said, Mr. Jaivanand, if you are fighting for a just cause, there cannot be a defeat actually. There cannot be a defeat. Win is yours, ours, and there will be a win. So don't worry, we will win. So then ADR went back to the apex court again, and the ruling came in 2002. Then they had, in the meantime, in a hutch-patch, this amendment had been done in Parliament. 2003 they went back, and 2003 ruling from the apex court was Constitution, Article 19, which is a fundamental right, right to express. And the interpretation of law at that time was right to know and right to express. They're both sides of the same coin. So therefore, without knowing, expressing, your freedom to express is not going to happen. And therefore, the amendment made by the parliament is made ultra virus. That was a win. And so those of you, those 11 who checked the assets, who checked the qualification, who checked the criminal antecedents, are the result of that national campaign for electoral reform. So friends, the point I want to drive is, things do not happen on its own, right? If you would have also slipped into passivity and behaved as passive citizens, then things do not happen actually. So active citizenship is all about asking right question at the right time in the right way. If this doesn't happen, we have a tendency, because the bulk of the population is passive actually. We love to be in the passive world, and we want someone in the active world to appear and make some change so that we can benefit out of that. We would not like to plunge into that. In Odia, we have a kahavat, right? किचड़ में क्यों जाएंगे और कीचड़ को क्यों मुझे लेना है, दूसरे कोई ले ले, देख ले कितना पानी है, उसके बाद में जा सकता. I am not going to get into that. And that is a very clean, what you call passive citizen. And passive citizens, what they do? They will criticize when everything is done. It should have happened like that. It should have been done like that. By that time, everything is over. Right? Active citizen is, they are proactive actually. And I will go a little further there. So, with this, it means, citizens are no longer just passive observers, but active participants in the decision-making process that affect their lives actually. The second one is, let's go a little deeper. Why participatory governance? Why participatory governance? Understanding participatory governance. Friends, let me tell you, many of you would have walked into a public authority which is run with your money, my money, our money. Public exchequers, money is involved in a public authority. And came back with a very exciting experience that you were given a red carpet. Somebody was waiting for you. Brother, tell me, I was waiting since morning to welcome you and to listen to your pains, frustrations, your agonies, your dreams, your aspirations, and tell me how I can help you. How many of you had such a wonderful experience in a public authority? Wherever you have gone. From Thana to Tehsil to any public authority which is run with our money, your money. One hand, at least? No. So, we didn't have a good experience, that means. We didn't have a good experience. And I would like to remind you, anyone from Andhra Pradesh here? Andhra Pradesh? Some of you. And from people who are from Andhra Pradesh, even from Tamil Nadu, you would know this gentleman called Dr. N.G. Ranga, right? He was a veteran parliamentarian, and between 50 and 95, until he died, he was almost in the parliament, right? He would be either in Lok Sabha or Rajya Sabha, right? That means if he is not able to enter the Lok Sabha, he will be somehow get elected through something to Rajya Sabha. That means he was a permanent member almost in the parliament during the first 50 years of our golden time post-independence. Dr. N.G. Ranga, and he was an agriculture scientist himself, studied in Oxford. He was awarded Padma Vibhushan also during his time for in recognition of his great contribution to agriculture science and all that. Dr. Ranga, in the parliament in the 50s, he had made a very interesting statement. He had said, Speaker sir, now we have our constitution. We have the rule of law of the country is very well established. And in this case, and the colonial rulers have gone Our own people have come, taken the mantles of administration, which is a great thing which has happened. But if some fundamental course correction is not done, from tomorrow onwards, from chowkidars to secretaries in the department, each one of them will behave like nababs, like jamidars, like rajas, like maharajas, to whom ordinary people, including an elected representative like me, have to go prostrate before them to seek some attention, yet will be denied attention. It's a prophetic statement in the parliament. In the 50s, so that means Dr. Ranga, at that time, he could visualize if there is no fundamental course correction in the system of administration, then, you will not be treated equal, actually. You will not be treated as somebody like a master. You are the master. We are the masters, actually, of the system. So I remember when I was the State Information Commissioner, one fine morning, I was walking into my office, and it's a statutory position. It's an office of ombudsman, right, to mediate between the citizens and the state. I saw, when we walk, and in our complex in Bhubaneswar, it's a complex which is all such statutory bodies are placed, like the Election Commission, the Human Rights Commission, the Office of Lokpal, Lokayukt, and Information Commission. So we have well-guarded system, security is very tight. I saw a bunch of people, bunch of women, tribal women, standing outside the gate and taking photographs. So I stopped my gadi, went to them, asked them, where are you from? They said, we are from South Odisha, very deep South Odisha, from a tribal pocket, which is still underdeveloped. I was very fascinated to see them in Bhubaneswar. And I said, how long you are here? I said, 3 days. We are doing a sightseeing of the state capital and all that. I said, would you be interested to come with me to my commission? They were very happy. They said, police is not allowing us to go beyond the gate, actually. And you are asking us to go inside. I said, please come. So I asked the sentry police and everyone. I said, hello, I have some guests. Right? The 16 guests will come with me. And then they went. I went inside the commission. I asked my secretary and others. I said, hello, some very important guests have come today. Right? Open the conference hall. And to tell you the truth, we had a brand new conference hall, which was never opened up until that day. They were preparing how to open up beautiful, fully furnished, air-conditioned, lovely conference hall, and one of the best in that building, actually. So, in the office, some of them, they came, they said, sir, these are all Adivasi Mahilas. They have come with their children also. So something, if happens on the seat, it will be very awkward, sir. New furnishing, new things. Then I looked at one of the officers. I said, hello, today the masters have come. Today the masters have come to see how their servants are doing their work. And since they have come, it's our duty, it's our responsibility to give them the most coveted hospitality, which they would never have got, actually. Open the door. No, don't worry. If there is anything, we'll change the seat. We'll do the new upholstery. This can be done. But let them sit. Offer them a nice cup of tea, coffee, everything. Give the children, organize some chocolates, etc. And towards the end of the conversation, to cut the story short, when I told them what is right to information, etc., etc. And towards the end, I said, what did you understand? And I was doing it in the vernacular language so that they can understand. Towards the end, what they said touched my heart, actually. So when masters know their roles, their duties, their responsibilities, they are not ordinary. They become extraordinary. So this evening is dedicated to make all of us extraordinary, actually. That is what my expectation would be. And for that, if there is any other post-lecture engagement also, I don't mind spending 15 minutes in the corridor, etc., etc. I was also invited for dinner, right? So I can forego the dinner, but engage with all of you, because I want each one of you to become extraordinary citizens. That is the purpose of spending some time in the evening. Now, in the participatory governance, you see, we have seen, sorry, the matured part. I will come to that. I will come to that appropriately. I'll come back to that. But the beauty of participatory governance is, if you have heard about this concept called participatory budgeting exercise in Brazil, Porto Alegre, right? It's a small little town, Rio de Janeiro, close to that. In Porto Alegre, the citizens come together to discuss the municipal budget system, articulate their own priorities, and in a very consensual manner, the municipal budget is drawn up. So therefore, the participatory budgeting exercise of Porto Alegre is considered as one of the best participatory budget making process, actually, when ordinary people are able to join. I still remember Bangalore, those of you from Bangalore, there was a proof campaign by one organization called Janagraha, right? What they were doing, ward-wise, they will calculate how much tax has been collected for the Bangalore Municipal Corporation, and ward-wise, what is the expenditure being done? And that, that becomes public, and then the people start talking about, well, this particular ward is a very ward of elites, right? Very high-end rich people stay here, but the tax collection is so low. So then there is a public pressure on them, and at the same time, there are wards in which tax collection is good, but the public expenditure is low. So there is a conversation. In Mumbai, there is an organization called Praja. They do an analysis of Bombay Municipal Corporation budget, actually, and regularly on a systemic basis. And they set right as much they can do through public pressure. So I think some of these small examples does throw sufficient light as to if people are organized, if people start questioning, if people start looking at things change actually. And So, but there are challenges, my friends, to promote active citizenship in India. These are possibilities, these are great possibilities. Social inequalities, still we are in a country where I see there is a India, thriving India, flourishing India, and there is a Bharat also. There is a Bharat, and some of you see them very clearly, and some of us, we put blind curtains and appear not to see them actually. I travel around the country. I travel so vividly within Odisha. I can see how my tribal pockets, the development in the tribal pockets are so lopsided. You can see them, you can feel them. Last 7 days, we have been discussing why tribals are eating mango kernel, and 3 lives were lost last week. It's a TV debate, it's a media headline stories. It's a question challenging the government why people after 70 years should eat mango kernel and die, right? Because there is a food poisoning and etc., etc. Right? And what is the food and nutrition security guarantee in this country? But that goes on and on. But that economic disparities, that social inequalities, and that lack of civic education is still a big challenge. So therefore, active citizenship in India is a difficult preposition at this point of time. Then the other point is, which I already said, there is a sense of apathy actually with many of us. Many of us. We would not like to get into the mud and gaze how much mud is there, that little Udiya example which I gave, right? So, even distrust, what can I do? I'm a very ordinary soul. Is there anybody who is going to listen to me? What can I do? And then the system is so bad, corrupt, even in the most corrupt office, if you go, there will be a discussion on corruption also in the office, right? Everybody would be talking, well, the country has gone to dogs, this, right? I said, hello, are you doing something here? So, these are all challenges actually. And from there, so, if we move, why active citizenship matters actually? Active citizenship is participating in decisions that affect our life, our livelihood, and the society. Participatory and active citizenship is all about holding public institutions accountable, ensuring that policies reflect the needs of the people they serve. Policies are not value neutral. They should serve. And to do that, if there is an enabling environment where citizens feel empowered to speak up, to challenge, and to contribute, that thriving ecosystem drives active citizenship. And it can go on. And friends, let me tell you, active citizenship goes beyond voting every 5 years. You feel great as a citizen of this country when you go to vote actually. And the citizenship ends on that voting day. Next 5 years, and you are waiting for that voting day to come to feel great that I am a citizen, I have I have some great franchise responsibility and I go. Or we feel very happy when we follow some great news that something has happened. But active citizenship is taking responsibility for your community, staying informed about local, global issues, and participating in decisions that affect your society. It's about holding public institutions accountable and ensuring that policies reflect the needs of the people they serve. In a democratic society in which we all today are, governments are not the only drivers of change. Government is not the only drivers of change. Citizens are equally important actors with the ability to influence policies and ensure that governance is fair and equitable. Friends, I would like to just draw your attention to the Constitution of India. You see, Constitution is something, it's like a Quran or a Bible or a Gita, right? We keep it in Odisha villages. We, the Gitas, we put it in a red cloth and worship it. Don't read it. We keep it and worship it. And it's Bhagavat day when the Bhagavat, one of the birthday of Bhagavat, we do some khichdi, kheer, all that and feel very happy. But what is there inside that Gita? If you discuss on that very day also, very few will be able to do. If I do a constitution test, even I will also fail miserably. Next 15 minutes, if we do a quiz competition on the constitution of this country. But the beauty of our constitution is, the constitution starts with we the people. That is the foundation. That is the foundation pillar. We are giving these responsibilities. So, as we the people, citizens have a great responsibility. And what is the constitution which has given us? Democratic representation and accountability is very clearly defined. Very clearly defined. Decentralization, local self-governance is very clearly defined. Fundamental rights and enablers of participation. As citizens of this great country, we have a right to form association. And today, you are here as part of your associational right or as part of your professional associational right. It's a right actually. It's guaranteed. Right to know is guaranteed actually. Therefore, the Parliament's 2/3 amendment, which I mentioned in the beginning, was turned down by the Apex Court, saying that it violates the Article 19, which is the right to express. And right to express and right to know, they are two sides of the same coin. So the amendment made by the parliamentary is made ultra virus. So that means we are protected. Directive principles of state policy, civil society in which we are all members, right? Government, corporate world, and then all of us, the academic community, the community-based organizations, the media, the research world, we are part of civil society actually. So that we can question the system, we can question the authority when it's abused. And then, so therefore, I think let us not undermine this with the people part. Now, let me move further. How do we do it actually? If active citizenship is so important, in which participatory governance is possible and we can do something, I see there are 4 key pillars actually. Participation, transparency, accountability, and inclusion, including those who are normally excluded. Right? These are the 4 pillars of what you call participatory governance, and they are guaranteed in the constitution, and there are plethora of laws also which has happened. But the question is, are we connected actually? And my third question to all of you would be, how many of you participated, those of you who are from the rural areas? Are we okay with the energy level now? Yeah? Okay? 1 to 10 scale? 10? 9.5. Sir, Kamal. So happy to hear this. So, now the point there is, those of you who are from the rural areas, 73rd, 74th constitutional amendment, which happened for Nagar Palikas and the Panchayats, the local government. Imagine, constitution is same, the source of power is the same. The source of power is the same, and from that source, the parliament draws power, the legislative assembly draws power, and the panchayats also draws power. And it's only the power is defined, the territory is defined, the boundaries are defined. In that, and nobody is inferior, nobody is superior. So therefore, and then in the panchayats, you have these Palli Sabhas or Gram Sabhas. In many states, there is Gram Sabha. Gram Sabha is a permanent parliament in that village, where elections doesn't happen. All eligible voters are members of the Gram Sabha. So my question is, those of you from the rural areas, have you ever attended a Gram Sabha meeting, which is a constitutional, what you call, sanction, and a great window of opportunity for a citizen to go express, question, articulate priorities, and so that the program, the development agenda is, is driven from that source actually. Anyone who has attended? No one. Okay. Same law, if you come to the city, 74th constitutional amendment, every ward in the municipal corporation, in the Nagar Palikas, even in small towns like Jatni where we are located, this is a notified area council. It's not even a full municipality. We have ward sabhas in theory. How many have attended a ward sabha ever? No, no one has attended. So friends, you see, the participation is not automatic actually, unless we avail those opportunities, avail those small window or big window. Things do not happen. So we don't connect actually there. So, but ward sabha, in Odisha we have Palli Sabhas, because a panchayat will consist many villages. And at the panchayat end there is Gram Sabha. Every village has a Palli Sabha. And I will tell what we are doing, how do we make this active citizenship possible. Participatory budgeting, we have said. Every year, the organization which I lead, which I founded 43 years ago, we do a meeting before the budget. What is that the citizens are expecting from the budget? We get our finance secretary, we get the finance minister, we get some of the legislators, we get some of the members of the parliament, we get some of the vocal community leaders, and they articulate. And then we submit something to the government. And then we always insist, why are you not opening up the budget conversation? Why budget is becoming a secret document? It has to come in a briefcase, nobody opens, you will be closeted in North Block or in some of the assembly finance departments. Why is it so close? After working systematically for almost 14 years, Odisha government has opened up now. Every pre-budget, there will be a public consultation. Earlier, we used to have it in our place. We used to invite officials. Now, government is inviting. Come on, hello, if you have any proposal, you come. So, that is participatory budgeting. So, participation, there are a small, big window of opportunities. I still remember every law, every rule, when they are enacted, there are parliamentary standing committees or legislative standing committees in the various states. They will call for feedback from the citizens. Right? I have attended several, and it is abysmally very poor. Very few people provide feedback. But when the law is done, when the rules are promulgated, people complain that it was missing somewhere. It should have been something like this, right? So we don't connect actually. So that is participation, and there are some possibilities where we can participate, we can articulate, we can also share our frustrations, share our concerns, articulate our dreams and aspirations. Transparency. Transparency, you have right to information, and I told you that I was the State Information Commissioner of the first when the law came up. It was a very interesting law. And how many of you have used right to information ever? No one has used? Okay. So I think after this meeting, I would expect some of you to use right to information. Because, you see, this is the preamble of the Right to Information Act. The preamble says, democracy requires an informed citizenry. Democracy requires an informed citizenry and transparency of information, which are vital to its functioning and also to contain corruption and to hold governments and their instrumentalities accountable to the governed. That is Right to Information Act. So during my court timings, if there is any confusion between the law and the public officials' view, I'll go back to the preamble, because preamble sets the purpose of this law. When this was piloted in the floor of the parliament, Prime Minister piloted this law. And I have seen the then Prime Minister saying, and it's recorded in the parliamentary proceedings, he said, there will be a new era actually. After this law, I wish this could have come immediately after independence. And this, the kind of what you call cover, the corruption and corrupt practices, how do you open? So Right to Information is a Sunlight Act. It's a Sunshine Act. All robbery, all dacoities happen in the dark night. Mostly. Nowadays, of course, during day also something happens. But it happens when it's dark. It's a Sunlight Act. So, in this, what does Right to Information? It's a transparency is very, very important. Very important. You can inspect work. Suppose there is a road being constructed. When I was coming, I saw there are 3 damaged spots on this road. Very badly damaged. Then I was telling my driver and asking me, I wish there is somebody who asks for an inspection opportunity of this road when it's constructed. I'm sure people, after the road is complete, they will question many things. But when the road is being constructed, any citizen, if a road is being done, a junior engineer is involved. The assistant engineer can inspect. If the assistant engineer is involved, executive engineer, superintendent engineer, chief engineer. Today in the Right to Information era, each citizen is a chief engineer material. You can ask for inspection. I would like to inspect the road between so and so. For 15 minutes it's free. For an hour, I have to pay about maybe 25 rupees. It differs from state to state. In Odisha, you have to pay I think for 2 hours of inspection, you have to pay a fee of something like 45 rupees or so. And you are officially allowed to inspect. And imagine, so inspecting work, inspecting documents and records, take notes, extracts, certified copies of documents or records, take certified samples of the material. Imagine somebody is asking through right to information the copy of a tender specification document, where the specification of the work is all recorded, the price of everything is done. Using that tender specification document, ask for inspection of the work. When a building, public building is done, public road, any public construction where corruption is big. So watch it. And finally, when this is done, you are also entitled to get samples. Ask for a sample of the road, a cross section of the road. I have seen beautiful active citizens asking samples, taking samples, and then their RTI application will be, I would like to know, since the work and the sample report doesn't conform to the work specification of the tender, I would like to know the name of the public official who was responsible to release money from the public exchequer, despite the fact that the work was never done as per the specification. You are fixing the system actually, fixing the system. What a great opportunity. And so these are the 3 rights which are available. And the uniqueness of the Right to Information Act, from secrecy, earlier we had the Official Secrets Act, right? That has never been repealed, but Right to Information supersedes that. It's a essential tool to fight against corruption, time-bound mandate. You ask for information, information has to be given. If it is not exemption information, in 30 days' time. And for every day of delay, the officer has to pay a penalty, right? Officer has to pay a penalty, very strong penalty. I must have imposed penalty not less than 2 crores, which has come from the pockets of public officials. It's not a small money, right? And then I still remember somebody who was a food inspector. Every time he will come to the court, and he would be always in a hurry. He would say, sir, I'm in a hurry, sir. Do I deposit my penalty amount in here or somewhere? I said, no, you don't have to deposit. There is no cash transaction here. So we'll deduct it from your salary actually. So I saw when I joined as the commissioner, first year I saw him, second year also I saw him, and towards the end of my tenure, I also saw him. That was his 3rd time. And that was the 3rd district. I said, hello, you have become a habitual offender now, right? And he was in a hurry. He said, sir, where do I deposit, etc., etc. I said, by now you should have known the procedure. But, gentlemen, now since you have come 3rd time, the commission can only impose a penalty up to 25,000 rupees. He said, sir, my provident fund is khali almost. Because you have already imposed twice, 50,000 has gone. And this time also, I think my mistake is also going to, I'm going to pay 25,000. I said, now, apne sudhra nahi abhi. So therefore, I have also a power, section 20, subsection 2, where I can recommend disciplinary action against you. In my final order, I still remember, that was the final year of my stay in the commission, before my retirement. I said, this gentleman who has committed mistakes 3 times in my eyes, he must have committed 30 such mistakes which has not come to my attention. So therefore, in a transparency era, these kind of officers don't fit into the system right now. Therefore, I'm directing the principal secretary so-and-so department to take disciplinary action against this gentleman, because this fellow is not fitting into the system now, and examine the possibility of dismissing from government service, because in the transparency era, these are all black holes in the system. Then he came to sense. He said, sir, I said, you have earned this gentleman. Go face the music. Then I never order that kind of orders, stringent orders. But finally, I had to say, right, the principal secretary, so and so department, must come on affidavit within 4 months of the action taken in this regard. And officials, they always feel little scared when they have to come on affidavit, because affidavit calls for perjury if it's a wrong affidavit. And perjury is 6 months jail at least. So, that is the power of Right to Information Act. And, I'm sorry, yeah, 1 second. That is the transparency law. Imagine, and the budgetary financial disclosures. Each one of us have the power, and through us, another 300 family members, community where we connect, right? Using right to, such wonderful tools when they come and they are not used, they become obsolete actually. Tools, if they are not used, right, for a long time, they acquire dust, they acquire all that, right? And now in Odisha, on the accountability, if you see, right-based development, 2005 onwards, you have right to work, the Mahatma Gandhi National Rural Employment Guarantee Program, where 100 days of work is guaranteed to any able-bodied person above 18 years. 100 days of work is guaranteed. And if the state is not able to provide that work, the state has to give an unemployment allowance. But to the other side of the story is not a single one has got unemployment allowance under the provisions of this act. It's a right which is given. The National Food Security Act, it's a right. Why should somebody go and eat mango kernel? It's a right under the National Food and Nutrition Security Act to get certain entitlements, and it's all available. There is a right to education, right to information, Forest Rights Act. You think of anything between 2005 and 2015, there have been plethora of rights-based laws which fix the system because there are accountability laws. If the state is not able to do that, citizen can go and take the state to task. There are enforceable laws. Public interest litigation. When there are some community concerns, there are issues, one can go to the court, use public interest litigation. There are n number of constitutional bodies, right? From right to information to the Women Commission to the Scheduled Tribe Commission to whatnot actually, range of them. And recently, one of my friend was the Lok Ayukt here, so he's retired. So I invited him and I was asking him, how was your tenure? He said, I had a lovely tenure, 5 years I spent, and 2 other members, one from the police fraternity, one from the judicial fraternity. We had a lovely team, but cases are not coming, sir. People are so scared, they don't bring cases. If they don't bring cases, you can't do much. So, if Justice Hegde would not have been there in Bangalore as the Lok Ayukt that time, the Bellary case was never, there was no possibility to expose that. And can you believe Reddy brothers inside the jail for so many months? It's because of the Lokapal Lok Ayukt Act. It's a very powerful law, but if you don't use, they remain as instruments, unutilized instruments. Social audit, Whistleblower Protection Act. When somebody says, sir, Dubey raised a corruption case in Bihar, for which this Whistleblower Protection Act came. And he was killed by the mafias. So many people come during my tenure as the Information Commissioner, and I always say them, I said, hello, I will only tell you the Sole dialogue, and that is your Dar Gaya or Mar Gaya. Right? Because you are doing independent struggle when we are fighting for independence. Imagine how many people have lost their life, right? If you are fighting a second independence to free this country from corruption, some people have to leave, lose their life. Yes? But I will take it up. So every Monday, I used to hear those cases of harassment by vested interests. I'll ask the Director General Police or the Principal Secretary Home to do a special inquiry, file a report in 15 days' time. What is the extent of threat to this gentleman? What are the issues? When it is dealt at a higher level, then system gets set up actually. But Whistleblower Protection Act is supposed to protect such whistleblowers. Nobody uses. Nobody wants to become a whistleblower in this country. Public Service Guarantee Act. In Odisha, Rajasthan, I'm sure many states, I have not kept a calculation of how many states have done this. All petty places where we are supposed to pay a bribe, right? Public Service Guarantee Act ensures that you don't pay a bribe. If within the timeline, if the service has not been made available, the officer will be penalized. But provided somebody takes it up, somebody uses this law, somebody goes to Lokpal, Lokayukt, and finally, inclusion, including those who are excluded. There is affirmative action. There is equity-based development through the various rights-based laws. And Agenda 2030, which I said in the beginning, that is the Sustainable Development Goals. The tagline is leaving no one behind. No one should be left behind. That means all those who are supposed to be left behind, we should identify them and deal with them. So, your answer to that question, what did this lady said that day? He said, sir, I knew that in district headquarters, there is a vigilance department to catch corrupt officers. But today, after this conversation in the conference hall of the Right to Information, each villager is a vigilance officer. If we use our right appropriately, and if we also take up our cases appropriately to its logical conclusion, each one of us is a vigilance officer. I think that was a fantastic, what you call realization from a poor tribal lady, right, who is not even fully literate, is semi-literate. Friends, so then the other part is, in the science technology, how do we really look at participatory governance? I have done 2/3, 1/3 is left. Rapid technological advancement and science technology have fundamentally transformed how we think about governance and civic participation. Digital platforms, social media, e-governance tools, these have made it possible for citizens to engage with governments in ways that were unimaginable even a decade ago. Unimaginable. Like now there is a change.org. If you want to file a petition and you use change.org, you think that this has to be done and you are feeling scared actually. That if I raise it, maybe I will become a victim. So ask somebody to file a complaint in the change.org. And through the system I just saw during COVID, we wanted to deal with the returning migrants who were biggest sufferer during the COVID. And we realized through change.org, we could file a petition to both union government and state government. There were almost 1 lakh petitions around one issue because of technology. So crowdsourced platforms allow governments to gather data and feedback from citizens at unprecedented speed and scale. Big data, the artificial intelligence are now being used to enhance transparency, tackle corruption, and make governance more efficient. But to make this possible, we need informed citizenry. This is, very critical. The need of an informed citizenry. This blend of science, technology, and civic engagement in reshaping governance offers us a remarkable opportunity at this point of time. I can see that. To build systems that are more inclusive, transparent, and responsive. Now you may ask me, is it really happening? Is it a very, fairy tale or it's happening? I come from an organization called CYST, which I founded 40+ years ago after I resigned from my university job. Then I joined another international organization, very good job, but I left it because I wanted to become a change agent actually. That was my passion. So we have been thinking, how do we do it? We operate in about 11 districts. And the organization is Center for Youth and Social Development. You can do a Google search leisurely when you leave this place or anytime when you have. You will see that. What we do, I said, how do you build, what you call active citizenship? Every village where we work, we have a young community leadership program. And there are about, I was just calculating before coming here, there are 420 boys, 437 girls or women. This number, they're all volunteers actually. Nobody gets a rupee from anywhere. The villagers have selected them because they are socially concerned. They would like to do something. And we only provide them training, provide them some support, provide them some, and the training is 3 pages. My skills, what are the skill sets I have? My leadership competencies and my community organization in the village. And once this is done, these young community leaders, they activate Gram Sabha, Palli Sabha, regularize the CBO meetings in the ground. More Mahilas come, more women come, participate. Before that, women would not like to come and join a Gram Sabha meeting, join a Ward Sabha meeting. Monitoring public services, ensuring social audits, facilitating community plans, linking people with entitlements. Today, government has a lot of schemes, but still there are people outside those schemes. How do you link them up? And right information sharing, using right to information. Right to information. And whenever I go to the field, each one would have about 15 questions. How do I use? What is the right way to frame the question so that I get the right information to set up the system? And the last mile issues. Friends, this is my last but one slide. There is a changing role of citizens now taking place after these new changes which has happened. From silence to voices, right? From a complete silence to people are raising voices. From shouting to counting. Earlier the shouting was, crore rupiya phas gaya yahan, kha gaya koi, kuch aur, nothing has happened. That is not true. Right? Maybe few lakhs have been spent there. You can count them now because information is available. Quantify the voice and feedback. From reaction to informed action and from sporadic responses to organized action. If 10 of you come together and would like to do something constructive, something creative, that is also possible today. And then my last slide is, I don't, conclude anything without Gandhiji, because he's my, and many of your, what you call, guru. Gandhiji had said something very interesting, and that applies so good, so well today. He had said, the real Swaraj will come not by the acquisition of authority by a few, but by the acquisition of capacity by all of us, to resist authority when abused. That is the power of active citizenship. That is the power of active citizenship. And active citizenship is what? Asking the right question at the right time in the right way. Not at the end, not when everything is done, but in a proactive way. In conclusion, participatory governance is not just about systems, it is about people, it is about each of us recognizing the power we have and the responsibility that comes with it to shape the world around us. As I leave you with these thoughts, I urge you to consider how you can take personal steps towards becoming more active citizens, engage in your community, participate in local governance, and above all, stay informed and critical. Together, through the combined forces of civic engagement, science, and governance, we can build a society that is more just, more inclusive, and more resilient. Thank you so much. I'll be very happy to take 1-2 questions and then we can close. If you have. First of all, does it make any sense? Or I was going somewhere trance actually. Right? Does it make any sense? Please raise your hands.
Yes, go ahead.
if it made any sense actually, right? Can we do something?
Yeah.
Thank you. Thank you.
Yes, you have a question?
Yeah, any questions you can ask. Floor is open.
Elections have become professions for the elected persons. They remain elected election after election, year after year. And they have their own group of people around them. And if anybody tries to say or do anything, ठोक देंगे.
So what is your question, sir? You have given the answer also. Right? What is your question?
Give something.
The question is...
How do we deal with this situation?
Yes, that
Okay.
is the question.
Anybody else? Any other question? You can also respond to him. You know, I'm not the source of all answers. Yes?
You know, recent Andhra Pradesh elections is testimony for active citizenship. What is your comment about it?
Sorry?
Recent Andhra Pradesh assembly elections is testimony for active citizenship. What is your comment about it?
Okay, I will definitely comment. Anybody else from this side? Give the microphone there.
So, as somebody from Gen Z, how do we transform climate anxiety into climate action? Because frankly, it feels very we feel very powerless. And although we can, of course, do Fridays for Future or like even actions like throwing soup on monuments or Mona Lisa, which I do not agree with, but I do understand where it's coming from. So, other than this direct action, which causes more outrage than action, what is it that the younger generation can do to transform their anxiety into action?
I think let me begin from there and then I go to these two questions. Yes, I can see the frustration, I can feel the frustration, and I can also see the impact of these frustrations. What can be done? I come from Odisha, and those of you who are from Odisha, I'm sure you know it, the scientific community knows it very well. The per capita carbon emission is highest in the country in Odisha, double than the national average. Right? And during the next 10 years, the new coal blocks which has been sanctioned, you know, when all of them become operational and they get without any major breakthrough in the technology, they get into thermal production. You can imagine the carbon emissions which is going to happen in Odisha. What can be done? I think, friends, first of all, you have to recognize the problem. Today, many times, we don't recognize the problem. The system doesn't recognize the problem. Because we don't recognize the problem, we don't deal with the problem. And the problem remains under the carpet until it becomes a very big problem. So recognize the problem, get into small steps to deal with that problem. Right? Just before coming here, I had a lovely meeting with few youngsters in my office and others, to discuss with them what can we do actually on climate action. I said, can we set up a Odisha Climate Action Practitioners Collaborative? So, and when we decided to do that, then we identified 4 areas. You have to break the problems into workable solutions actually. One of the area was renewable energy, right? Yes. Rooftop, solar, this, that. If that is not done in a big way, we are still dependent on the thermal power. And thermal power comes with a huge carbon cost to all of us. Second, what do we do with the mines which have closed 20 years ago, but the mine closure plan has not been approved by the government, so there are empty mines. Land repurposing, which can happen there, and those land can be converted to solar generation plants, that is also not happening. What do we do there? So some people have to work around mine closure, land repurposing, and in the new land, can we think of fruit-bearing trees, anything there, right? Can be a lot of work. What is happening to the coastal ecosystem? In the coastal ecosystem, the mangrove forest, wherever there has been some, gaps between the nature and habitation during, the cyclones and the natural disasters, they show their mighty wrath, right? So what can be done there? Can we do some small things there? I think, friends, for every problem, there are small steps which has to be initiated. And until some small steps are initiated, and by just sitting on the fence and waiting for somebody to come and take action, that is not going to happen. So I would like many of you, the new generation, the X-Gen, right, to take such small steps, and such small steps will become a bigger step at one point of time. Instead of sitting, watching, we have to get involved actually. And there are many, what you call, initiatives happening around the world, right? I have traveled very widely. I have seen in countries like, small island countries like Fiji, Vanuatu, Tuvalu, Tonga, those small little island countries, they are so vulnerable to the climate crisis, right? And youngsters are making a change. And we have to learn from each other and drive that change. On the political part, sir, when people are under election, or for that matter, people who have taken election as a profession actually, right? It's a profession, right? They don't want to get out of anything, right? And age is not a bar there, right? So there is no retirement age. So you continue doing what you want to do actually. I think people have to rise up actually. And wherever people have taken steps, things have happened actually. We just completed the election here 4 months, 5 months ago. The party in power had no iota of thinking that they will be losing actually. The new government who came to power, they had no imagination that they will win actually. That is the swing and that is the power of the people. People are also watching. You can't undermine people. But at the same time, I think a time has come where scientific community, leaders from academic world, civil society, media, they have to also come. We should not shy away from politics actually. Right? So we would like to shy away from politics because we feel politics is a dirty game. Politics is not dirty game actually. Right? So how do we do that? Recently, I was looking at somebody who was a parliamentarian in Norway. I said, what do you do? He said, I'm a postman actually. I said, you are a postman. You are a parliamentarian also. Now my term in parliament is over. I have come back to postmanship. You see, I like that. When a teacher goes to the parliament, and after the parliament is over, or legislative assembly, comes back and starts teaching actually, and consider that phase as a phase where he or she has contributed something, the chemistry of politics will change in this country. Today, anyone going there would not like to come back actually. That is the trouble actually. So I think this generation, the Y generation, our time is up actually, my friend. We have done, right? More than 2/3 is done. Life is gone. And there is only one life, friends. There is only one life. I don't believe in second life. Only one life. If we do not do something during this life, and Gandhiji had rightly said, if you want to see a change, be the change yourself. And that is so true. That is so important, so critical. Right? We have to start acting actually. Act fast. Time is running out. And we can't be, waiting for some Naya Suraj to appear somewhere actually. We have to make that appear. Thank you so much.
Thank you very much, Dr. Dananda, for a very enlightening and stimulating talk on You kept the most of the audience highly captivated with very important messages. We are very grateful to you for your ideas and sharing thoughts with us. On behalf of the Academy, we are delighted to honor you with some memento.
Okay, let's go there.
Sure.
I'm just fresh out of Kerala from the Arya Vaidyasala Kotakal because my knee is paining actually. But I didn't know how I stood for maybe half an hour, 40 minutes because I am not supposed to stand such long time. But when I saw the energy level was very high, 10 to 10, so that motivated me actually. Thank you. Thank you. Thank you.
Thank you all. Please do join for a dinner across the street.